これはお肉だ。面白い。あ、何？いや、疲れた。
Hi, Professor Franchi.
Hello, good morning, good
Hi.
afternoon.
Hi, good afternoon. Hello, Dara.
Okay, shall we begin?
Yeah.
Okay, ladies and gentlemen, it's a great honor for me to welcome all of you to this wonderful event. And on behalf of the organizers of the International Conference on Medical Imaging and Computer-Aided Diagnosis, MICAD 2021, I would like to express my most sincere gratitude to your participation. And now it's my pleasure to invite our conference chair, Dr. Ridan Su, to give the opening remark for us. Okay, welcome, Dr. Ridan Su.
Thanks, Dara. Will you please stop the share screen, then I can share my screen? Yeah, thank you. Yeah, can you see my screen now?
Yes.
Okay. Thank you, and good afternoon and good day, everyone. Welcome to the 2021 International Conference on Medical Imaging and Computer-Aided Diagnosis, MICAD 2021. I'm Ridan Su, Assistant Professor at the Shanghai Advanced Research Institute, Chinese Academy of Science. Actually, welcome all of you to Birmingham for MICAD 21 on behalf of myself and the organizing committees. Welcome. Actually, I was very much looking forward to welcome everyone in person to Birmingham this year. However, due to the pandemic, we have to switch this event as a virtual conference. I'm thankful that you have joined us for this interactive virtual event. From another point of view, it should be an interesting experience to have this MICAD 100% virtually. It allows our new and old friends and people to join us in a much large number. Before we start, please allow me to briefly introduce the MICAD conference. 3 years ago, when I met Dr. Liu Han, who was a research fellow in Cardiff University at that time in Shanghai at an AI International Conference, we and several professors talked about the emerging AI applications in radiology domain and medical imaging, which we believe that will be some challenges still there, including technical innovations, algorithms, data ethics, policy, and regulation. Then we decided to start this MICAD as a community to promote research imaging, computer-aided diagnosis, and healthcare, to bridge the state-of-the-art research in medical imaging and clinical trial. Then we had an inaugural MICAD conference and clinical trial. Then we had an inaugural MICAD conference and clinical trial. Then we had an inaugural MICAD conference. Sorry, there's some problem in my computer. Can you see my, Dora, can you see my screen? Yeah?
Yeah, Ridan, it's all okay.
Yes.
Okay, thanks. Yeah, then we have an inaugural MICAD conference in Oxford University in January 2020. just before the pandemic broke out in that end of in the end of that January. The first MICAD conference is much more a workshop than a conference. It is tiny, but with great success. I'd like to thank Professor Zhang Yudong from University of Leicester, who helped greatly in the first MICAD to make it a success. Also, Springer supported MICAD as proceeding publisher. This year, we are very proud to announce that the second MICAD conference attracts over 700 registrations from computer scientists, clinicians, physicians, bioscientists, engineers, and other researchers from 43 countries. We will have 37 great presentations in MICAD21. It is the first time that MICAD to be held combining Zoom and live stream through YouTube and Bilibili. The Zoom will enable interactive questions between speakers and participants, and YouTube and Bilibili to ensure easy access to a large number of participants. Here are the committees of MICAD21. I'm very grateful to all the committee members who made great contributions for the MICAD21. Special thanks also go to Professor Zhang Yudong, Professor Frangi, Professor Reinhardt, Dr. Liu Han, and Professor Hamamoto. I'd like to thank all the TPC members and external reviewers that review the submitted papers and selected the final program. A huge thanks for their help. And here is the brief program for MICAD21. There will be 4 oral sessions, as well as 4 keynote sessions during the 2 days conference, based on the thematic topic. As will be seen in the brochure, 37 speakers will give insightful presentations and sharing their cutting-edge research and experience. I would like to thank all the speakers for their great support. I know that some speakers make presentation during midnight time or very early in the morning in different time zones to support this global event. Thank you for your efforts. And appreciations also go to those who contributed this conference, including authors, reviewers, session chairs, delegates, media partners, academic partners, and organizing committee members, especially the conference secretary, Ms. Dora. And we believe that MICAD21 will definitely offer a professional and meaningful chance for the experts and scholars from all over the world. We hope it will be a bridge to make the closer interaction and cooperation between academia and industry. Last, if you have any ideas, suggestions about MICAD, please feel free to contact me or the committee. My email is shown and on the screen, and you are welcome to join us in different ways. Again, we'd like to thank and welcome everyone and hope you will enjoy MICAD21. Thank you.
Okay, thank you, Dr. Su.
Thank you.
Thank you, Dr. Su. And next, it's my pleasure to invite our program chair, Professor Yuji Hamamoto, who is the representative director of Japanese Association for Medical Artificial Intelligence, JMAI. And JMAI is also the academic partner of MICAD. Okay, let's welcome Professor Yuji.
Thank you, Dora. Can you hear me?
Yes.
Okay. Good morning, everyone. Thank you very much for your participating in MICAD 2021. As one of the program chairs, I am so happy to know that so many people participated in the second conference. I am currently the representative director of the Japanese Association for Medical Artificial Intelligence, and the number of members of the Japanese Association of Medical Artificial Intelligence is rapidly increasing because expectations for medical AI are rising in Japan. Indeed, many members of the Japanese Association of Medical Artificial Intelligence are also participating in this conference. Recently, more than 60 AI-based medical devices have been already approved by the United States FDA, and several AI-based medical devices have already been approved in Japan too. This field is expected to become more and more important worldwide in the future. I sincerely hope that by participating in MICAD 2021, you will be able to obtain the latest information, and that will be a very good opportunity for international exchange. Thank you again for participating in MICAD 2021, everyone. Thank you.
Thank you, Professor Yuji. And now we will begin our keynote session. Let me introduce our session chair, and he is also the program chair, Professor Alexandru Frangi, and from University of Leeds.
Good morning, or good day for everyone, in whichever time zone you are. Yeah, I think you can see the screen now, right?
Yeah.
Okay, perfect. Yeah. So thanks a lot to Ridan and Rigi for the kind introduction, and for Dora for all the hard work on the background to get this event up and running. And I'm delighted to both introduce the session where my colleagues Leo Joskovic and Eric Meyering and myself will be providing keynote lectures. And without further ado, I'll start with the first talk, which is entitled From Medical Image Computing to In Silico Trials of Medical Devices. And Ridan and Rigi made a very good case to the combination of both AI, medical imaging, and the importance in the context of medical devices. And that's essentially the main context of the INSELEX project, which is a Royal Academy of Engineering chair in emerging technologies, where we are trying precisely to study the interaction between all of the different technologies. And I'll try to report some of the work we're doing and the vision behind. So the medical device sector is roughly a $500 million market, and is acting in a quite changing demographics where we have aging going on, but also in particular for the UK is quite important because there is quite a a large industry in that context. There is a 5% increase year on year of the sector, and there is particularly interest in the context of both cardiovascular orthopedics devices, and there's also quite a lot of work in medical robotics going on. However, there is a number of challenges that are affecting the sector, and drivers as well that are making it grow. I mentioned about aging. I mentioned also the changing lifestyle. There is also a complexity on medical devices that is growing, and a technological convergence, which is making devices more and more complex, and therefore we need to have better ways to assess and develop them. But there is also quite a lot of downfalls in that context, including increasingly reported serious adverse events, which has reduced the trust in the sector, and therefore the shareholder values from these companies. And there is a need for actually rationalizing more and more the R&D cost and reduce the time to market. So if we compare this sector with the automotive sector, which is about 4 times larger, we see that over the last 30 years, there has been an impressive change in the technology and the types of automobiles that, for instance, we utilize. And we went from a sector where we used to utilize a lot of experiments. So these are wind tunnels and the old way to now being done computationally fully.
Excuse me, Professor Banchi.
Yeah.
Can you full screen your slide? Because in my side, it's a very small picture.
Okay, so let me see if I can do that.
Yeah, full screen.
It is in full size, but I think it's another problem. Give me just 1 second. I'm afraid.
Now it's good. Yeah.
It's good now.
But,
okay. Is it better now?
Not now. Not now. Or maybe you can just leave at this page and.
So give me 1 second, because now I think we may have made it more complicated.
Or you can just keep it like this. I think this is better, but.
Yes,
yeah,
I need a moment. Okay. Is that better now? Can you confirm it's better now?
It's good. We can.
Yeah, it's good. It's good.
Yeah, but we can see. Yeah. No, good,
okay.
Good.
So.
It's good. Good.
Okay, so I will have to be told if there is any comment, because I cannot see anybody now. Okay, so yeah, so I was explaining how this in the automotive sector has changed. You know, the use of modeling and simulation has changed the way we develop man-made objects like cars, but also any other type in many senses. We also use virtual prototyping and, you know, even AI in the context of self-driving cars. Per counterpart, if you look, for instance, to the medical devices, is still largely incremental. And if I show you the same 30 years, 30 years to today, years of development on a particular device that I will talk later in more detail, you'll see that there is still a bunch of wires in large extent. And what is quite, crying out essentially for change is the fact that after the 30 years, we still have large complications rates, large mortality rates in relative terms. So one would say, well, why cannot we use the same technologies to actually develop devices so that we can, for instance, computationally look at ways that we can insert those devices and understand their behavior. So this is what the InCellX project is trying to do, is actually see how we can disrupt this life cycle of medical device development, which has a number of phases, from the conception of the device to the optimization of the design, to then assess the product in potentially in virtual populations, to then redesign or understand the root causes of failure modes once we go to market. And the interesting thing, and also particularly calling our attention, is that in spite of a massive growth rate, so we are talking about medical devices and drugs for which the same ideas could apply, between 5 and 6% year on year, which actually is larger than the automotive industry growth at the moment. Yet the number of devices that are going through FDA or CDA approval is actually stagnated, and both medical devices and drugs has stagnated over the last 10 10 years or more. So clearly we have a demand which is growing, but not necessarily providing the best and the latest technology due to this problem. So the ambition basically is what would happen if we could utilize imaging, modeling, simulation, AI to actually improve the way we develop those devices. And we could essentially use this for what is called the 3 Rs, for refine, reduce, and replace conventional trials by actually thoroughly understanding devices and running them on virtual populations and potentially under operational uncertainty as well, which is more realistic that we can do nowadays. So imagine we would be able to have a library of anatomical models of whichever organ. I'm using here aneurysms as an example. We could then virtually implant devices and study, for instance, how the hemodynamic is changing in different anatomical conditions. We can do the same in terms of looking at different operational regimes like rest and exercise. And we could also look at different device configurations and different device designs and what their performance is for all of those. So this means we could develop virtual trials, virtual populations, where we could study thoroughly a particular device in different anatomical regimes, different physiological regimes, and each of those elements becomes what we know as a virtual experiment. So let me now go in a bit more detail, explaining this in one exemplar, which only tries to be an illustration of a much wider concept, but to be able to ground it in a concrete problem. So the example I showed you already a bit before is brain aneurysms. This is cause of hemorrhagic strokes, which are about 20% of all the strokes we know. People don't really know exactly why these aneurysms are generated, what makes them grow, or why eventually they rupture. But what we do know is they tend to like to be built around bifurcations in the circle of Willis in the brain. And that once you detect that one of those aneurysms is present, you have quite a lot of dilemmas. One is whether you need to treat or not. And the second is which best treatment you could apply. And there is a number of treatments going from clipping, which is a very invasive surgical procedure, to endovascular and minimally invasive procedures like coiling with a stenting, or flow diversion. Now, what we have worked over the few years, probably about 15 years now, is in developing tools for interventional planning. And we develop techniques that allows you to assess parameters that have to do with the risk of different types of interventions, so that you could compare them and help to aid the decision of what treatment to go by understanding the potential life expectancy that you're adding to the patient, in comparison, on the other hand, by the risks that you're adding through the intervention procedure itself. We also develop tools that you can utilize for then planning hemodynamic changes that are induced by the presence of devices, therefore complementing medical devices like imaging systems with information that they cannot, in an interventional setting, easily provide. And that led to the development of a number of pipelines that allows you to go from images all the way to do segmentations, develop mesh generators, setting boundary conditions, solving physics equations like flow, and then visualizing those results of the simulations in what effectively are virtual images, and derive from those parameters that can be used for decision making. Now, what we found out, or what we realized, is that you could utilize the same pipelines with a number of important improvements that you need to do subsequently for virtual trials, as I mentioned before. So, but still in the context of interventional planning and interventional and diagnostic problems, what you can do is, if you are able to have pipelines which are effective to run at really larger scales, you could develop high throughput analysis pipelines from digital databases like hospital databases or population data sets, where you can extract information of a very large phenotype of both morphological, hemodynamic, but also complementing that with lab and clinical history, and therefore develop those systems for decision making that I mentioned before. Now, just to give you a pictorial index of what could my talk be today, but I will go to only one part of that, is we've developed algorithms to go from images to segmentation in detail. And this is something where we're working again a lot more now with new techniques based on deep learning to be able to do automatic analysis. So we want to be able to run these data sets on tens of thousands of images and be able to run reliably segmentation pipelines. And that's an aspect we are working on. We also are able to do morphological analysis and morphodynamic analysis. This is important because shape and dynamics of shape have information about disease and about potential treatment outcome. We develop also pipelines for doing numerical simulations, particularly blood flow and blood clotting, and I'll comment that a bit. And we also develop techniques to do virtual interventions, particularly virtual stenting and virtual coiling, so that you can simulate the different types of intervention. I will talk today mainly about virtual stenting, but we've done quite a lot of work as well on virtual coiling. So let me focus primarily on perhaps the least familiar part for this community, the part that is less medical image computing, because to some extent what I'd like to explain is what can we do with the sort of techniques that are going to be discussed in this conference if we were able to scale them up really at large scale. So back in 2012, when we were doing quite a lot of this work, there was a guideline by the American Heart Association and the American Stroke Association, where they started reviewing the evidence in different type of biomarkers. And it was quite telling for us at that point that for the first time, these guidelines indicated that in addition to just the basic biomarkers that were used at that point, which are age, health status, and size, and location of the aneurysms, morphological parameters and hemodynamic parameters of aneurysms were becoming to be more and more relevant. And there has been only growth in the realization that those are important components. So we developed the pipelines that I mentioned before. And that there is a lot of science behind that. There's probably 40 journal papers that back all the work we've done over the last 15, 20 years. But just to give you some of the main highlights, you need to make very careful assumptions regarding your simulations to be reliable. And those assumptions were tested very, very thoroughly. So we did quite substantive sensitivity analysis where we looked at how, for instance, parameters that are relevant, like wall shear stress, were depending on the morphology of the aneurysms, the type of assumptions we do on the modeling, whether we use Newtonian or non-Newtonian models, how they were sensitive to inflows and outflow conditions. We also, and one of the main conclusions there was actually that the main source of variability was anatomy. So having very accurate segmentation algorithms was actually quite an important element of that pipeline, and that was published back in 2005. This work. So it's quite a lot of work we put in that. We also looked at the difference of image modality. So what happens if I create the same model on the same patient using 3D rotational angiography, which is a technique you do have during the intervention, versus if you do that with computed tomography angiography, that you only have it preoperatively, but usually not in the follow-ups. And there are major differences. So 3D array tends to be, is isotropic. It tends to be higher resolution. So you miss parts. So you have under segmentations, you lose some vessels, which, as you can imagine, for fluid dynamics is important. And you also have changes in aspects which are quite important in the features of the aneurysms, like the neck area, for instance. So we did quite some detailed analysis of all of those parameters, comparing, in a database that we had both rotational angiography and CTA. We did a head-to-head comparison, and we came up with a number of indexes that, again, were critical for that, and also how you should design all the biomarkers in order to be less dependent on the modality by utilizing, for instance, relative quantities rather than absolute quantities, and also using semi-quantitative parameters rather than fully quantitative parameters. We also looked at how you could use those to actually, those parameters to characterize flow and characterize them in different locations of the aneurysms, and characterize them not only statically, like with mean average flows, but also dynamically by looking at the variability of flow over the cardiac cycle. And that led us to understand also how some of those parameters were related, for instance, with rupture. So what you show here is 4 different flow types that we came up with for clusters of flow, and where it's clear that one of those has more likely to having non-ruptures, while some of the other ones are more split. And also we looked at things like, for instance, the impingement size of the flow jet into the aneurysm dome itself. And what we observe is that when you have a smaller jets of impingement, that tends to be higher correlated with rupture than when you have a very, when you have a concentrated jet is more dangerous, let's say, than when you have a much wider gentle pressure jet. We also did a number of studies where we looked at how flow correlates with risk of rupture in different flow patterns. So we found that, for instance, in a particular study with different types of aneurysms. There was, which were all terminal aneurysms, so all at the end of a vessel. This particular flow pattern was, well, there was these three patterns that were present primarily, but that this one was the one usually most associated to rupture. So this is quite important because understanding what hemodynamic drivers lead to rupture is, as you will probably imagine, critical in then deciding objective functions to optimize devices, because you're trying to change that pattern and put that into a pattern that is less prone to rupture. The other thing which is quite important is that we tend to do all of these simulations in pretty much, even if we do transient simulations, we tend to do that with boundary conditions which are in one time point in the life of that patient. And we as individuals are changing all of the time our physiological conditions when we run, when there are seasonal changes, when we are sedentary. So one thing that is becoming more and more important is how we link those technologies with wearable sensors so that we can actually inform the highly detailed anatomical models that comes from imaging with highly detailed temporal models that as they come from wearable sensors. And then the other question is how you go about bringing the physiological variables that you measure, peripheral from the body with wearable sensors into boundary conditions in specific locations of your aneurysms, which is the part that you're actually interested in studying for devices. So there is a whole study about how you propagate boundary conditions and how you develop multi-scale models that are detailed in the area of interest, but they are sort of lower dimensional and faster and more efficient elsewhere. So one of the things we did in that context is we worked in a European project that I had the pleasure to coordinate with quite a lot of partners around Europe. We had what we call a sub-study, which was called a Lido sub-study because it was done in the Lido island in Italy, where we collected about 100 subjects, which were all elderly, of which some of them had mild cognitive impairments and some of them were controls. And we did physiological measurements with wearable sensors for 24 hours using Holter in a number of variables, including also gait and other parameters that we are not using here. And this is just the descriptive analytics from all of those subjects in the study. But what we did is we also took measurements of blood flow and blood pressure, and we developed using machine learning, and in this case using Gaussian process models, sophisticated models of the boundary conditions for flow that allows us to understand for a particular individual how does the pressure wave change over 24 hours, and therefore what is the average pressure wave, but also the uncertainty that we have as marked there in gray. And we also made we could parameterize this curve so that we incorporated the elements of body mass index and age into these models. So we now have generative models where we can automatically generate boundary conditions for specific ages and a specific body mass index. So what we have now is a mechanism, is a generative model to synthesize flow waveforms in ways that are consistent with things we observe in real patients. And why that is important? Because what we observe is that actually physiological variability can have an important factor. So they are related with systemic conditions, but also with lifestyle, with aging potentially as well. And we could look at, for instance, how flows in the same aneurysm depends on whether you're in rest conditions or you're in exercise conditions. And we did some studies purely looking into biomarkers of risk of rupture, where we observed that although that variability had limited effect in certain parameters that are used in the literature, like time average wall shear stress parameters, they actually have quite some large effect in instantaneous oscillatory shear index and transient wall shear stresses, which are actually used quite a lot. And that the main thing that although these parameters can be on time average way insensitive to the physiological regime, if you look at aspects like the wall shear stress and you look at the harmonic content and the directionality of the wall shear stress over the cardiac cycle, that actually dramatically changes between with or without that physiological regime being accounted. And we think that has to do as well with how this affects some of the inflammatory processes on the wall. And therefore it can have quite a major risk. And in fact, we show that in a small database of about 20 subjects, about 4 of them flipped their status from rupture to non-rupture risk just because of the change in these in this boundary, in this physiological regime. So small set, but nevertheless worth mentioning. So we also developed techniques for doing stenting. So I don't have time to go into a lot of detail in terms of, how different vessel geometries, operator skills, can lead to different outcomes, even with, the same device and the same geometry, and also how, malposition of the devices can generate in-stent thrombosis, for instance. But what I'd like to show is that, when I was doing this work some years ago, one of my interventional radiologists from Switzerland, I asked, Daniel, how do you actually think about these devices? And he said, well, we normally put a stent in a particular direction that will reduce the blood flow going to the aneurysm, producing a stasis and therefore flow, blood clotting. But there will be a still low resistance distally to the vessel, and that will generate that there is still a flow going through the struts of the stent down, so I don't close this vessel. So, okay, that's fine, but how do you know that you need to put it that way and not the other way? Or you need to put two as well? That's experience and, lots of other things that he wasn't able to easily articulate for me, and that he recognized for new people who are new interventionists becomes challenging. So what we set forth is to do the following. So what about if we develop a system where we can actually test all those different alternative treatments, and we look at how the magnitude of the blood flow changes, the pressure drops, the wall shear stresses, and you can make up your mind. So I said, well, that would be brilliant. So we came up to develop techniques now to do virtual device implantation. So techniques which are very fast using simplex and deformable, simplex meshes and deformable models that try to capture some of the physics, but without being fully structural mechanics models. So they can run within a minute. We compared those. So how you validate it? And the other thing that comes about is how you validate such technique. So we had to go developing experimental systems where you could put different types of stents. And we had a pump with a circuit where we could compare a virtual with a real circuit. So this was done with 3D printing for making, digital replicas of and micro-CTing, the devices, and generating a CAD model of the devices and a physical model of the stent, and putting a physical model of the stent in the physical model of the aneurysm and a virtual model of the stent in a virtual model of the aneurysm. And then what you can do is compare, for instance, our fast virtual stenting with other techniques, which are finite elements, which are, take several, many hours compared to the fast virtual stenting, but are supposedly more accurate. And what we found out is that for most of the purposes we're interested in, they're equally applicable. And then in terms of the hemodynamics, the hydraulic circuits that I showed before, what we had to do is compare the virtual sort of reality with the real reality. And this is for two different stent designs. And then looking at things like time dilution curves, where what we observe, what you see there in pink and in green, is a sample volume in the middle of the aneurysm in the real and in the simulated one, and showing the time dilution curve, so the amount of dye as a function of time, and you can see that they're pretty much spot on. The blue one is a sample at the feeding artery, and we use that for control, for reference. So incidentally, for those of you more curious on that, as you can imagine, this is not just solving flow equations, but you also need to solve the transport equations, and you need to model the transport, propagation through the bloodstream. And then you need to do a digital ray casting to actually mimic the X-ray and then have the same viewpoint to the real X-ray and compare both, which is basically what we've done in that exercise. So then you can have these sort of things. You have a device, a real aneurysm with two different types of stents, stent 1 and stent 2, and now we can compare, different types of relevant parameters like sluggish flow, residence time, so all the parameters which are relevant for device design. And then you can go and show that into, do that in a real database of patients and start studying how certain devices perform on a small population set. And you can draw conclusions for those which are, relevant from a clinical point of view. Now, I explained to you before this first dream that we had, some years ago. Now, one thing you will notice is that we had only modeled physics so far, but actually what will be very interesting is to also model biology. So add to that flow the biochemistry, because ultimately we are putting those devices to produce a stasis and produce clotting, and that's ultimately what will dictate the quality or not of our device. And it has been shown in the literature that it's not enough to rely on radiological or angiographic success, or what is called angiographic occlusion, which means that you put a stent, you see that the aneurysm is not visible anymore in an angiographic study by putting contrast agent and seeing that the contrast doesn't get into the aneurysm anymore. Well, the only thing you've shown there is that there is no contrast coming in, but you don't know the quality and the type of clot that has been formed. And it has been shown in the literature that there are cases where with a delay time, those aneurysms rupture, and people don't really quite understand why that has happened. And we believe that that has to do with the quality of the clot, and you know, together with a number of other authors that have reported similar findings in the literature. So we had to develop a technique that actually allows us to model the biochemistry in addition to the physics. And the idea is, you know, I don't have the time to go in detail on this here today, but the idea is that there are two types of clot. There is what is called the red clot and the white clot. And the way to understand it as engineers, that most of us probably are, is that the red clot is like a gelatin that you can redissolve by, you know, additional pressure, by additional, you know, things that happen in the aneurysms. While the white clot is a combination of the white clot contains also a lot of platelets and fibrins that generate a mesh together with the thrombin and make sure that that thrombin gets solidified and gets kind of in a scaffold, so it doesn't re-dilute easily again. So what we came up with one of my students that is a chemical engineer, he developed together with some collaborators a model for understanding the proportion of red clot and white clot that is being generated. And what we can do now is actually provide density maps of the clots. And to be frank and helpfully, what I show here in red is actually the white clot, and what I'm showing here in more whitish is actually the red clot. So it's kind of inverted in terms of color scale. So be mindful about that. And we compare that with physical experiments where our predictions show similarities with those results. I want to show a last thing, because I recognize that we have had some technical issues and I'm running behind schedule now. But one of the things we are very, very excited, and we recently made that available as a preprint, and is currently in review in a major journal, is what I consider one of the first in silico trials fully validated. And what we have done is what we call FDPAS as trial. What this trial we've done is we've replicated the populations using a large database we have of aneurysms of 3 conventional trials that have been published in the literature: the PUF trials, the ASPIRE trial, and PREMIER trial. So what we did is we are not using the same patients as those. This is not a twin trial, but what we know as a chimera trial, which I haven't introduced, but is essentially we find a matched population and we build a digital model for each of those members of that matched population. And what we have shown is, in a nutshell, that by utilizing these in silico techniques, we could replicate the results of the 3 previous conventional trials and explain failure cases that they couldn't explain, therefore demonstrating that in silico trial is not just a replica and therefore can save time and risks, but also can provide additional insights. So this is, for instance, one of the trials that we compare to the PUF trial, and this trial took 8 years to decide from design to publication, with 6 years of recruitments just to get 108 patients. Okay, and we could do the whole trial in less than a couple of years, and that was the first time that we were doing it, where we had to develop a lot of tools on the way. So this is, again, just some results. I mean, we work with epidemiologists and with interventional surgeons, so we make sure that from a clinical trial design point of view, they're consistent. And these are just some of the results, which again, and the benefit of time, I'll probably skip. but I gave you the main gist of it in terms of ability to save time, save risk, replicate results, and provide additional insights. So in summary, computational imaging and physiology can be used for the management of brain aneurysms. This technique is descriptive. It can help to understand the disease, but is also integrative and predictive because it brings different modalities together and allows you to do predictions of scenarios you couldn't actually image. Translation clinically is not just about bringing this technology, it's about validation, validation, validation. And I haven't had the time to show all the details of validation work we've done, but trust me, it has been quite thorough. And I gave you a couple of examples of areas where we did a bit of that. And also that industrial translation is fundamental to actually supporting the medtech industry because, there is a lot of technologies, and probably you also already saw a few through the presentation, but there is, way more of those. And unless we bring these multiple technologies together, the challenges of building the next generation of medical devices and medical technology in general is going to be massive, both in the complexity of the devices, but also in the time to market, and therefore the cost that we will be paying for being able to, to enjoy the benefits of those technologies. And with that, I'd like to conclude, giving a big thanks to quite a large team. These are more the historical team and some of the current members. Lots of the work by Tony and Ali more recently, but we have now quite a large team that is also working on the next wave of work that is coming up. So stay tuned. So thanks a lot. So I'm trying to gain control of my screen again. So maybe what we could do, given that I've introduced already a bit of delay, and I don't want that affect Leo and his presentation, is I would put in the Q&A my contact details in case someone wants to follow up with questions. And I'm also happy to answer questions through the chat, but feel free to come to me and get in contact. And if you agree with that, I'll hand over to, well, I'll introduce first Leo, and I'll hand over to him. So it's a great pleasure to introduce Leo. He's a great colleague and friend, and also we have some common roots as well in Latin America that we share. But Leo is a professor in the School of Computer Science and Engineering at the Hebrew University in Jerusalem in Israel, and he's fellow of IEEE, ISME, and MICAD Society, and he's president at the moment of the MICAD Society. And he's in the editorial board of a number of journals, including Medical Image Analysis and the International Journal of Computer-Aided Surgery and Nature Scientific Reports, and has served in numerous program committees. So for me, it's a great pleasure to introduce Leo to give us his talk on accelerating deep learning medical image analysis in radiology. And without further ado, Leo.
Thank you, Alex. Do you hear me okay? Yes? Okay. Yes. Okay, and you see my slides as well? I did share screen.
Have you shared them already?
No. Yes.
I don't see them, but that could be my fault. So,
does anybody else see my slide?
Yeah, we can see the slide, but I'm not sure if your screen or Alex's screen. Maybe it's your screen.
Okay.
No, you're seeing Leo's screen if you're seeing it. Perfect.
Okay, thank you very much. Thanks, Alex, for the very kind invitation and the kind words. It's an honor for me to give a talk after yours. Very impressive work, very nice work. Welcome, everybody. I'm happy to be able to share with you some thoughts about accelerating deep learning in medical image analysis in radiology. Thanks for the invitation. So this is I'm gonna present to you some an idea and some joint work with a number of people here in Israel. If you don't hear me okay, or you stop seeing my slides at any moment, please make a lot of noise so I can know that something is wrong. Thank you. So if we look at the world of clinical radiology, we clearly understand that the number of patients is increasing rapidly. We do observe a manpower shortage. Clearly, the number of radiologists grows slower than the number of patients and images. And of course, the images become more and more complex from different modalities. The treatments are becoming more complex and diverse. And this creates a great pressure on the health system, and especially on radiologists, which are in shortage and therefore required to do more and more work. Never mention, of course, the issue of the COVID, which has even strained even further the work that our colleagues, the radiologists and different clinicians have to do. On the other hand, if we look at the technical factors, we now live in a connected world with a high bandwidth and the ability to transfer data easily and have this wonderful teleconference, which was unthinkable several years ago. And of course, the computer and networking power has increased very significantly. And the focus of my talk is, of course, what you're familiar with is the new AI technologies. But the bottom line is that really what you're looking for is to optimize the automation and workflow, because this is what happens when you have great pressure in a certain industry. If we take two parameters, the radiologist time, it can be a radiologist or a clinician, of course, and let's say accuracy in any way you would like to measure it, okay? And of course, you don't always need 100% accuracy. You need sufficient accuracy so that you oversee the clinical requirement. So for example, if you're doing a follow-up of tumors, you only need to be precise to a certain degree. And what we observe is that in the current practice, most of the assessment is still done manually. In other words, even if there are computer tools to visualize the images, to zoom in and do different things, most of the quantitative assessment and qualitative as well is manual, and it is not clear what is that clinical requirement. So different subspecialties and different diseases have different values for what this clinical requirement is. And we observe that in many cases, because of the shortage of radiologists' time, if a radiologist has to read 20, 30, or even more scans per day, obviously there's going to be a time pressure. And in some cases, the current practice is going to be below what this clinical requirement is. The goal for the paradigm shift, what we're looking for in this new practice is basically, with the help of computer support, to move this graph to the left, meaning you reduce the time and increase the accuracy in such a way that you exceed the clinical requirement. And you can also quantify that. And then you have really help doing something about the workflow. Note that the goal is not full automation, but rather to engage the clinician in a way that you can provide effective information. So we're looking for less time, we're looking for higher accuracy. And a third parameter, which is very important, is the observer variability, because there is no such thing as an absolute ground truth. And this is also, of course, patient-specific and scan-specific. So there is a margin that contains this clinical requirement, which is the observer variability. And we observe that in the manual case, this is quite wide. So if you see the band around the variability for the manual assessment, we know that it can be quite large. And the goal with our computer support would be to also both quantify the observer variability, but also to reduce it. Okay, so in other words, you might have uncertainty, but you can quantify what is the level of uncertainty, and this has to be patient-specific and, of course, span-specific. If you achieve and manage to lower this variability, you have really achieved the three objectives that would eventually lead to a better treatment. So just to emphasize a point, the goal is not necessarily to automate everything. The goal is mostly to be more effective and reduce the engagement of the radiologist, so they engage the radiologist in a smarter way. Okay? And nowadays, this has been done in the field of medical imaging and radiology with deep learning methods. And this has become the method of choice. And in fact, there is a lot of buzz about it, not only in our technical community, but also in the radiology community. You see venues like the RSNA or the European Radiology Conference, different companies really are very excited about this technology. It even, as all the hype goes up, goes to the point in which they say, is the future of radiology doomed? We very well understand that this is not the case. We don't believe that AI will replace the radiologist anytime soon. However, I've heard that it will replace radiologists that do not use AI. And the idea is to create the tools that radiologists can do a better work. Okay. So the problem with deep learning is, of course, data annotation. You need lots of them, at least what we need nowadays. And this is, if you wish, the fuel of this technology. We have a great car, a Ferrari, but now it's very expensive in terms of fuel. So what are the main issues with these annotations? Because with no annotations or with poor annotations, you cannot do any kind of reasonable deep learning. So of course, the annotator expertise is an issue. Highly trained radiologists do not want to spend their time annotating images, even if they're paid. I mean, this is not reasonable. So we have to establish some sort of a time budget. The time, of course, also determines the price because the radiologists are going to have to be paid. And of course, in this case, we need to optimize that. We need to understand what is the annotation quality. And of course, because deep learning is based on a sample of an unknown distribution of cases, you need sufficient examples to be able to train a deep network to be able to cover and achieve some sort of robustness. The case distribution is key, and you need to explore that in an incremental way. And of course, the observer variability, which I mentioned, the goal is basically to build a system that is within the observer variability, and we need ways to quantify this observer variability because they change from case to case. So a brief illustration of the observer variability, what we aim for. This is a CT of a lung, and this is a lung tumor. It's upside down for ease of viewing. And we asked 10 radiologists at the radiology department here in the hospital in Jerusalem to annotate this. And this is what you get. Each color shows the annotation of one of these radiologists. And you see that there are areas of very high variability, and this is natural. Why is it natural? Simply because you don't see a clear boundary there. You can see that even the number of components can change. So we understand that the manual segmentation variability on which we're going to base our deep learning models or annotations can have a very wide variability, and we need to understand and quantify that. And this varies very much. It's not only the number, but the range. You see that the range is from 5 to up to 50%, which is very significant in building different models. And it changes by structure, case, and observer, and we published several papers on the case. The good news, though, is that this variability can be quantified and estimated. Okay, so the fact that it's there, you have to embrace the fact that you have the observer variability, and there are different ways to estimate that. But this is, of course, the subject of a different talk. What I want to focus today is on the bottlenecks. So we have this great technology, and we're developing AI-based radiology solutions. What would it require? We know that it does require a large collection of representative data sets. If we're doing segmentation, the two key tasks of the analysis, the technical task would be segmentation and classification. If we're doing segmentations of structures, we need around 1,000 to 5,000 annotations to achieve really robustness and coverage. And if we're doing a classification, a binary classification or classification into a small number of categories, such as healthy, non-healthy, or moderate, severe, and so on, you need about 10 to 50,000 annotations. And obviously, this is going to become very expensive because the manual expert annotations, this would require about 1,000 hours of a radiologist or several radiologists for the initial deployment of the network. And then, because you're sampling this unknown distribution, you're going to need a similar amount for robustness and coverage. Those are very, very rough estimates, which vary very much from case to case. And in addition, you're going to have to do this custom development for hundreds of specific organ structures and pathologies, and also imaging protocols, because what we know already is that these networks are very sensitive to the different resolutions, imaging protocols, and so on. So if you think of a RAD app, an application for radiology for each one of these pathologies or characteristics or the clinical question that you're asking, you're basically going to have to develop one of those from scratch for each one. And this is what is called a narrow AI. And this leads to a lengthy and costly development process. You know that eventually it's going to work. If you have sufficient annotations, you're going to be able to train a network to do the proper job. But this is going to be a lengthy and costly development process. And if you think a little bit wider, this is what narrow AI does. It takes a long time and it incurs in a very high cost. So if you see this matrix in which you see different pathologies, different areas, sorry, of the body, different imaging modalities, and then you can think of the third dimension, you can have the different pathologies. There are hundreds of those. This is a huge matrix. And every RAD app that you're going to develop is going to target one of these entries in this matrix. So this is going to take a very long time. And it's in fact not going to be cost effective for the vast majority of the common conditions. The low-hanging fruits are being picked by research labs and different companies, which do have the budget to develop that. We're talking about several million euros or dollars for each one of these slots. So obviously there are some conditions which it's not going to be cost effective to develop such solutions. Okay. Of course, there are tools that try to address these, such as transfer learning, one-shot image classification, but still this is in its infancy, I would say. So we are faced with this task that to fill this matrix, we basically need to invest a lot of effort and time, and not necessarily us as technical people, but mostly our clinical partners because of the annotations. Okay. So what we see now is that we need to involve the radiologist in this loop. Okay, and this is called the bootstrapping radiologist. You would have to start by collecting and annotating a few scans, because without that, there is no way to build a network. Then you develop and improve the model, you deploy it, you validate and correct. It's not fully automatic, but it has to be sufficiently worthwhile so that you provide useful results earlier. You optimize the radiologist time and budget. It's not the tedious delineation from scratch every single time. And you have to do the software improvement or the network training on the go. Okay. Otherwise, you are not going to be able to make progress, and you have to accommodate rare cases that can be handled in a semi-automatic or fully manual way, but you have to identify those. Without this, all these RAD apps are going to basically remain in the lab. So let's look at the different qualities of the radiologist validated annotations. Okay, and I view this as a pyramid because you're going to have high quality annotations at the top of the pyramid, very few, and low quality annotations, those have not been validated, at the bottom of the pyramid. Okay, so here you would see is the following. You have in this horizontal axis the quantity, and you have the quality of the annotation of these data sets. And of course, with quality, the cost increases. What is the top of the pyramid? You have two independent experts that have manually annotated the data set and reached the consensus. So this is the highest quality of annotation. On the other hand, the lowest quality is those that are automatically generated, that have not been corrected or inspected by an expert radiologist. So you're not very sure about the quality of these. And these you can generate many because you can basically run your deep network on any scan that comes in and get some results. So of course, there's gradings in this pyramid. If you have a single expert, that's the next best. Or if your network generates a segmentation, for example, and it's corrected by two independent experts, that's the next quality, and so on. You can, of course, involve graduate students and different types of expertise. And this way, you're going to get a hybrid set of annotations with which you're going to train your network. So you're going to start with a lower mixed quality of annotations, the minimum required to train the deep network. And then you're basically going to add to that. But of course, this is going to be a very expensive process because the quality of the improvement is uneven. You don't really have a quality control. You don't have a measure for observer variability, and you don't really have an indication of what is missing. Basically, you're expecting data to come in and see what happens. What we're looking at is to involve the radiologist to validate and correct a subset of these, such that with the same annotations that you have, you basically move them up the pyramid to obtain high quality annotations. Because we know that empirically, a network trained with high quality annotations performs much better than one and requires less annotations than one that's trained with less data. Then you train your network, and the goal is to optimize the quality, to reduce the number of data sets, and to identify and add rare cases. So if you wish, in mathematical terms, you're basically looking to optimize in this pyramid. CI is the cost of each radiologist. There are different types of radiologists and expert annotators, and TI is the time. You're basically looking to minimize this time to improve the quality. So this is what we're based at. Large companies might be able to do this in a large scale for a number of selected conditions. But what about those of us who don't have access to this type of annotations, for example, in the different labs? So in my lab here in Jerusalem, we have been doing applying a systematic methodology to optimize with the radiologist in the loop the different the annotation time. And I'm going to show you today the first one, which is fetal development MRI. And the goal here is to basically describe to you very briefly how you can optimize this annotation, how you involve the radiologist and get what you need. So the task we're looking at is a fetal MRI development evaluation. A pregnant woman goes through an MRI, and from this MRI, you can get information which is not available in traditional ultrasound, such as the fetus, an accurate measure of the fetus volume, the fetus brain, and different morphology of the fetus brain, and also the placenta, which feeds into that. And in addition, you want to produce linear measurements, which you can compare with ultrasound-based measurements. And you'd like to be able to do all this automatically, of course, with the minimum number of training annotations, okay? The clinical significance of this work is that you can then generate a quantitative report with measures of variability and uncertainty, and basically determine from the fetal development curves what the conditions are available. So I'm going to focus, of course, only on the aspect of how do you accelerate this pipeline. Okay. So in the initial phase, There's no other choice but obtain those manual segmentations for each structure. Should mention that for these structures, it takes over an hour for an experienced radiologist to annotate these MRI data sets. We train a deep network for these type of structures, make corrections with another network, which I will show, and then basically generate a higher number of annotations, about 50 to 100 in this intermediate phase. You train the network, and then based on the corrections that the radiologist has done, you can do a segmentation error estimation and also segmentation error correction automatically. And most importantly, you can prioritize. If you run the next batch of 100 MRI scans, you can say which ones are worth looking at, which ones should be corrected by the radiologist to avoid going through every single slice and every single scan. So here's the basic idea of the interactive learning from user corrections. You have this network that produces trained with very few scans, in this case, 8 or 10 scans, which is about 800 slices. You train the network, and now you're going to ask, this would be the result. For example, this is the fetal body. You train this, and then you're able to correct. You ask the clinician to correct this segmentation, the manual corrections in a certain slice, and then you propagate, you learn what these corrections are and propagate it to the next slide. So you can see that slice n+1, there's still some errors, but you see that some of the segmentation errors that you see here, for example, in the bottom of the slice, have disappeared because the specific network has learned how the correction should be made. Okay, so the idea then is that if you take the time that's required to produce this validated segmentation, fully manual segmentation takes about over an hour, as I said. This is the volume overlap difference. At the beginning, you have 100% difference, no segmentation. As the time goes, you reduce to the observer variability. If you train the network, you would have to correct about 35% of the segmentation, and doing that manually, as you can see, doesn't buy you much. In other words, even if it's less work, presumably, it doesn't take less time. There are too many corrections to do, so it's not useful. However, if we use the approach that I just described, you can create these corrections and reduce the time very significantly to about 8 minutes, and the end result is a validated high-quality segmentation. Okay, because of this propagation scheme, you need to correct on average 1 in 5 slices, and it takes also less time, and you reach the same observer variability than the full manual. So once you have this initial phase, you train again the network. Now you have these high-quality annotations, and it's going to do relatively well on similar scans. However, the challenge here is going to be the scanning protocol, changes on that, the gestation age in case of the fetus, and where the scan was acquired. Okay, so you can acquire those scans and run it, and you're going to get hundreds of segmentations, but who's going to look at them? All these required validation. There are too many slices to inspect every one. So what you want to do is to do an estimation of the segmentation uncertainty, do a prioritization of which scans can you correct, and then ask to correct only those. So just to quickly illustrate the process, you compute the segmentation uncertainty like here. Some of it is uncertainty and some of it is error. And of course, you don't know this ahead of time. You can see in this, the blue margins show you the uncertainty of the network. And here, some of it is an error, some of it is uncertainty. It's a valid uncertainty. And with methods that I would not describe, basically, you can learn what this segmentation uncertainty is based on the manual corrections, and basically, in some cases, correct some of that. In this case, for example, with a network that has learned how to do the corrections, this disappears. Okay, And this is the network that inputs this automatic segmentation error correction. You input the corrected segmentation and then correct that in the subsequent slice. And based on this, you can prioritize the scans in decreasing order of uncertainty, and then ask the radiologist to test that. So just to briefly give you an idea before I finalize is the following. We tested this on 3 structures from fetal MRI scans: the fetal body, fetal brain, and the placenta. You see here the numbers with different protocols. How we started the initial phase with 13 scans for the body, 12 scans for the brain, and 10 scans for the placenta, and then basically reached this intermediate result. Okay, and the focus was, if you look at the dice coefficient, we know what is the slice correction prioritization. This is the initial for error, the 1 minus the dice coefficient. And as the number of slices, the percentage of slices is corrected from 0 to 100% of the slices, you can have the optimal one, which is if you know ahead of time what the correction is, this is the order. But if you do it sequentially, you get a certain number. And if you do it with uncertainty, you reach this. So what we can see is that if you do it slice-wise, you only inspect the number of slices. After 12% of the corrections, you can already reach the observer variability of 9% in these cases, versus 33% of the slices when you do this sequentially. So basically, you have, in this case, in this study, the inspection and correction of about 12% of the slices achieves the observer variability performance instead of 33%. So the gain is very significant. This is what the dice per slice would look like. You have here the dice coefficient and the slice number. At the beginning, this is the original correction, the manual correction with no propagation. This is what the dice coefficient does. In some cases, it usually goes up, but not always. If you do the prioritization, as you can see here, you reach the same dice coefficient with less slices. Okay, so you save on average about 60% of the manual corrections. Okay. Another aspect is which scans can you add, and in this case, we can add 5 scans. And here we again did a study in which, based on the uncertainty estimation, we can choose, after you have segmented 100 scans, which ones are the 5 ones that are worth correcting and adding. Okay. So just to summarize, the current status of our work is that we created 322 high quality segmentations. By high quality, we mean that they have been validated by a radiologist with a modest effort and the same team. Here are the numbers. We are able to cover different protocols and different sequences of different resolutions. And we're able to do this based on this scheme. And we're now processing an additional 300 for the development of these curves. Okay, and this is the work in progress. We do a similar approach for the linear measurements. I will skip the details, but the idea here is that we produce, without doing the segmentation, these linear measurements, and we want to do that with as few as possible of the measurements. We do this with about 200 linear measurements of manual annotation that include both the slide selection for the measurement and the actual measurement itself. Okay, so you see that with 214 scans, the annotation of 214 scans, we were able to reach the observer variability as desired. Okay. So to summarize, what we can say is that this approach that I have just described to you allows us to reach the observer variability and do a bootstrapping of this methodology on as few as possible scans. The prototype is in use at the Tel Aviv Sourasky Medical Center for the research on 3D fetal development. Okay, and this could not been possible without the radiologist in the loop and this bootstrapping technology. So to conclude, unless we develop approaches similar to the ones that I described to you, we're not able to achieve the narrow intelligence that we're looking by deep learning for specific tasks. Because in the end, the bottom line is the expensive and time-consuming effort of clinicians, which are not annotators. The low-hanging fruits, as I described, are being picked by companies and different research labs. But I believe that in the next 3 years or so, all of those will be picked, and the rest is going to be the next level, those who are less cost-effective. And for this, we need to develop the technologies that we're talking about. And the clinician in the loop is a key component for the bootstrapping here. The long-term viability of deep learning then presents very significant challenges, mostly because of the annotation effort. Just a brief thank you to all the colleagues and collaborators from the different institutions and students. And this is what our lab meetings look like. The good news is that we've coming back to meetings in person. The first one is going to be held next week because we already have a high number of vaccinations here in Israel. All the students have been vaccinated, and we're going to resume the in-person meetings, and we're very excited about that. Thank you for your attention. As Alex mentioned, I'll be happy to answer questions by email or any other means. Thank you very much.
Thank you, Leo. It was a fantastic talk, and I think your main point is well taken. That probably is not only about developing new networks, but also developing new schemes on how to train them more efficiently and get humans in the loops, and that's quite interesting. One thing I'd appreciate if you could answer in the chat
Sure.
is if you have any experience about how the results you show would change with the type of network, because you use the same network most of the times, right? It's CNN. So whether is there any point in improving networks or not, or is it actually most of the impact coming by the sort of training and schemes that you mentioned? And I would be curious to know if there is any publications that you are familiar with or you've done on that space.
Thank you. That's an excellent question, Alex. In fact, what we've observed is that there are different phases. Changing the network might be useful at the very beginning. There are networks that require more training examples and networks that require fewer network examples. But as you move and your dice coefficient and accuracy moves up, then the architecture doesn't matter anymore. You have to focus on the loss function and other parameters. So because we're doing this with about 10 different structures and types of scans, we're beginning to understand when it's worth applying what networks to what efforts. We, for example, know that when you already reached the observer variability, changing the network architecture is not going to buy you much. However, in different steps of the development, it is worth doing. So basically, we're developing the methodology, and still no paper, but hopefully soon, that describes these phases and what is worth doing at every step, backed, of course, with empirical data, because this is mostly empirical science.
Excellent. I think this is fantastic work and really needed to focus the community in the things that actually can make a biggest difference. At least if you are in the clinical translation sort of domain, that's absolutely critical. Thanks so much.
Thank you.
So I'll invite you as well to put your email in the chat so that people can follow up with you. But it was really, really, really good work.
Thank you for the invitation.
Thank you. So I'll invite Eric Myring now to, hello, Eric. So we go now far down south and
hi, everyone.
To the west, hello.
Hi, Alex.
So hello, very late probably for you.
Yeah, it's 8:15 or something p.m. So
that's very good. So this is a great opportunity, to be together, and I'm delighted to be able to introduce another great friend and colleague, Eric Myring. So he's professor of biomedical image computing at the University of New South Wales in Sydney, and he has interest in computer vision and AI in quantitative biomedical image analysis, and he is fellow of IEEE. And without further ado, I'll hand over the floor to his presentation on artificial intelligence in bioimage analysis.
Thanks, Alex, for the kind introduction. Can everybody see my slide? All good?
Yes. Yes.
Yeah, thanks so much.
All right. So yeah, this is going to be about artificial intelligence in bioimage analysis. More broadly speaking, my group is focusing on developing computer vision methods for biomedical imaging. So to emulate or even outperform the human visual system in analyzing and interpreting biomedical imaging data, both for diagnostic purposes, but also in the life sciences, in biological images to help biologists interpret their data. And of course, there are many different types of imaging modalities. Most of you will be familiar with it, I think. Many of these techniques are also combined nowadays, especially in the clinic, but also in biological imaging, because they have complementary properties in terms of, for example, their spatial resolution and the field of view that they can capture, but also in time, the temporal resolution, you could say, and the duration over which you can image, or the sensitivity. This is just one way of presenting the different properties of different imaging modalities. This is already way back in 2003. But if you want to study life more down to the cellular, tissue, cellular, and molecular level, then the method of choice at the moment, and probably it will be for the foreseeable future, is fluorescence microscopy imaging, especially if you want to study live cells. So if you want to study dynamic processes, of course, you can go to much higher resolution and analyze even down to the angstrom level using electron microscopy. But if you want to study, let me get my laser pointer. Can you see my laser pointer? I hope so. So I can actually point at some things. Yeah, so this black square here is a kind of a nice midway resolution, and also temporally has the right properties to study living cells, and even down to the subcellular level, looking at interaction between molecules, for example. So this talk is going to focus more, although we do some more and more work these days also in the medical imaging space. We're going to focus much more on the bioimaging in this talk, because that's what I've been doing mostly in the last decade or more. And a lot of things happened in that space. Fluorescence microscopy is really a very impressive technique, to the point that it has undergone a lot of revolutions in the last 2 decades, I would say, to the point even that the Nobel Prize in Chemistry was awarded to these 3 guys, none of which are chemists, by the way. They're all physicists, I believe. But for developing techniques for which they did use some kind of biochemistry to develop a super resolved fluorescence microscopy. And this has really blown up the field. There's so much going on there. I would say maybe there's even more data generated in these labs, in biology labs, than in the clinic, maybe. I mean, at least certainly if you look at the sizes of individual data sets, they can be really huge. Dozens or even hundreds of terabytes in a single study. So the goal of the kind of work we do, bioimage analysis, is obviously you want to extract information from the image data to acquire knowledge of what is being represented in these images about biological processes in cells, for example. But to get there may be a lot of steps, right? I mean, you may need to do some pre-processing, denoising, enhancement, deconvolution, detecting objects, segmenting them. If you've got time series, which is what we're going to focus on mostly today, there's a tracking problem. How do you follow things over time? But if you've solved all these steps, then you can do quantification, and then that allows you to do recognition, for example, visualization, analytics. Ultimately, what you want to do is model the biophysical processes that are represented by the images. So at each step, you may gain insights into the data, discover something new, but the reverse is also important, I think, that if you have knowledge about the biological phenomena that you're studying, you can use that information to improve the analysis potentially. This is especially relevant if the image quality is very low, if images are very noisy, for example, and you have a lot of uncertainty in the data. And then you need to rely more on prior knowledge. So the clearer the images, the less ambiguous they are, the more you can rely on the images themselves. But the more ambiguous they are, and in microscopy, unfortunately, they can be very ambiguous. I will show examples. You need to rely more on prior knowledge to kind of constrain the solutions in analyzing these images. So the word model is really important both ways. I mean, you try to build models of these biological processes in cells, but you can also use these models subsequently to improve the analysis, all depending on image quality. So what I mean is a simple example, just to illustrate using models. For example, if you've got an electron microscope image like this, and there's a particle in there, or at least one slice out of it. So this is one image out of a 3D data set. And suppose you want to segment this, then parts of the contour are very clear. Okay, so here you could do the detection and localization of the contour. But in other parts, it's very unclear. If you look at the local context there of, I don't know, what, 15 by 15 pixels or something. So this is an example where in some parts you can rely more on the data. You can do the detection and localization pretty accurately. But then for other parts, you have to rely more on what you know about the shapes that you're analyzing, if you know anything about them. I mean, that's not always the case maybe, but for example, here say that you know that the shape is more or less circular. And that's what you can impose then. If you would use, for example, a classical active contour method, you could accurately localize the thing here on this side of the particle, but on the other side you will have to rely on the prior knowledge that the shape is supposed to be more or less circular. So you can require that the final shape is more or less circular, or you can minimize the bending energy, let's say. Okay, so that's an example, but also in dynamic images, time series, tracking can be extremely difficult. So here you see some examples, microtubule tips in the cell cytoplasm. It's very noisy data. If you zoom in, you will see that it's really very fuzzy. So here you may need to rely on prior knowledge about the dynamics of these objects in addition to their shape. At the cellular level, you can also have data like at the embryonic level. So here you see an example of a developing embryo over time. This is of the roundworm, about 1 millimeter in size. And this is probably, I hope this works. This is one of the most crazy data sets I've ever seen. This is from Philip Keller's lab at Genelia Research Campus in the US. It shows the development of a Drosophila, a fruit fly embryo. So every blob here is a cell nucleus. And there's, I don't know, tens of thousands of them. This is time here. So if you want to study this quantitatively, there's just no way that you're going to do this manually, right? I mean, this is the typical example of where you really need to automate the whole process of detecting all the cells and following them over time. And there are some techniques to do that, but there's still a lot of room for further development there. By the way, so this data set that I'm showing here, so this is a nice volume rendering visualization, but the underlying raw data, the microscope data, just for this single embryo is about 1.7 terabytes. Okay, so if you wanna do screening this way, this is an image with light sheet microscopy. For example, screening, if you introduce mutations in the DNA and see what are the phenotypic effects on embryonic development to study certain diseases, you can easily end up with tens or even hundreds of terabytes of data. So there's not just a computer vision problem, how do I detect and track all these things, but also there's a huge data handling problem here, which is more of an informatics problem. But anyway, that's not what we're going to talk about today. So talking a little bit more about the tracking, from simple to more and more complex. So what is tracking? Obviously, the first step is you need to detect objects in a time series, and then you need to connect them over time to build a trajectory, right? So that's kind of trivial here because there's only one object. But usually we have 3D data. So this is just one slice out of a 3D, or actually a 4-dimensional data set, so 3D over time, with tens or even hundreds of particles in this case, and it becomes a big question mark. Where are all these particles, and how do you connect them over time without introducing all kinds of errors and ambiguities? You have to remember, if you make a mistake at one time point in tracking an object, it will just propagate further down the line, right? So you will not be able to correct it anymore afterwards. So one mistake can really, especially if you use it for these embryonic studies, if you want to build the lineage tree of all the cells, if you make one mistake, the whole trajectory down is completely off. Okay, so you're going to introduce errors in your downstream analysis. So it's an extremely critical problem. So when we first started thinking about this problem, which is now more than 10 years ago, we were thinking, okay, how do we as human observers, because we seem to be pretty good at it actually, how do we look at these images? And here is an example of, this is a synthetic example just to illustrate the point, but an image where there's a single particle, and this is one time point out of the series, and it's very hard to say where this particle is, right? But if you play the movie, then you can get some idea. Now, I don't know how well this works because I mean, the resolution may not be high enough online, but I hope you can see something. So the particle is somewhat here. If you look closely, you can see it moving around. If I would stop the movie, then you wouldn't see it anymore, like in this example. So clearly there's some kind of interaction going on between the spatial and the temporal dimension, right? So as human experts, maybe we are not so accurate or reproducible in precisely quantifying these images, pinpointing exactly where these particles are and quantifying their size or whatever. But we are extremely good at integrating spatial and temporal information and also making associations between objects in space, but also over time, and making predictions of where things are going. If you would be looking at this for a few seconds, you would get some idea of the dynamics of these particles, of this particle, and then be able to predict where it's going next, right? So that simplifies the tracking. So the things that we started thinking about in terms of developing computer vision solutions is, can we develop methods that better integrate spatial and temporal information rather than just splitting it into two completely separated problems where you first do the detection in every time frame and then you try to link the detections? Can we incorporate prior knowledge by using models, as I talked about earlier? And can we do things more probabilistically rather than deterministically? Because there's a lot of uncertainty in the data and you want to be able to incorporate that as well, right? So the natural way to do that, and many of you are probably familiar with it, is to use Bayesian estimation techniques. And that's what we've been playing with for a long time. And we're moving away from that now in favor of machine learning techniques, which is what I'm going to talk about in a second. But I want to briefly recap some of the work we did in this space. Earlier on. So the Bayesian estimation framework is that you compute, very generally formulated, you compute the degree of belief in the object state by taking into account all available evidence up to the current time point. So that means the state is basically a vector containing all the variables that you want to keep track of over time. That could be the position, the velocity, acceleration, shape, intensity of the objects. And you express all of that in terms of probability density because of this uncertainty that you have in each of these parameters, in each of the variables. So we're going to solve it completely probabilistically. The evidence that we have is the set of images or features extracted from the images. We call them Z, T, where T is the time dimension. So this framework is that what we ultimately want to know is the posterior, right? What is the probability for a certain state at time t is what we ultimately want to know, given all the observations, all the evidence up to time point t as well. So this would be the posterior for the previous time point. And we're going to make a prediction now based on a transition or a dynamics model. which tells you what is the probability of ending up in xt given xt minus 1. So this is a Markov kind of process. And so you can multiply this, integrate out over the previous state, and that gives you a prediction. What is the probability of ending up in a certain state xt given all the evidence up to t minus 1? And you multiply that then with a second model, the observation model, which is the likelihood of getting a certain observation given a certain state. And that gives you then the posterior, which then becomes the input to the next iteration. So you plug that into this equation again, you multiply with the transition model, get a prediction, which you then update with the observation model, etc. So it's an iterative process of predicting, updating, predicting, updating, predicting based on the models that model the prior knowledge about the dynamics in this case. And the update is based on a model of what the images look like. So this is the mechanism. It's a very general framework that you can apply and that has been applied to a lot of different things in computer vision in general, but we've been playing around with it. We were one of the first, I think, to use this specifically for tracking problems in biology. And yeah, so the trick here is to come up with the right models. To be able to apply this to anything, you need to come up with the right models, the right transition model and the right observation model. And so that's what we've been doing for many years. We've designed these things for particular applications. By the way, so this mechanism works in principle for one object, for one target, is it sometimes called in other computer vision domains. So it's used for tracking one object. You could extend it to tracking multiple objects. For example, you could simply extend the state space by plugging in the state vectors of all the objects that you want to keep track of. But you can imagine that this is very quickly blowing up the state space. It grows exponentially with the number of targets. The computational cost grows exponentially. And this is because ultimately the way you implement this typically is using sequential Monte Carlo estimation techniques. So that means you use samples of the state space. So you make a sampled representation of all these probability densities. And so that means that to properly cover this whole state space, you need to have a sufficient number of samples, right? So every time you add a dimension, you would have to multiply the number of particles or the number of samples with, I don't know, maybe a factor 10 or 100 or something for every dimension. So it's going to very quickly blow up and becomes extremely computationally costly. And so this is not how we implement it typically. What we usually do is to approach it like a single target tracking problem for all the targets individually. And then, of course, you do keep track of the interaction between objects and you represent the overall probability density as a Gaussian, or sorry, as a mixture model. And but this requires doing some kind of heuristics to keep track of the number of targets and their identities, etc. But so this can be done. We've done this, for example, for tracking microtubule tips in the cell cytoplasm. Lots of studies we've done in that area. So here's an example. This was published like eight or 9 years ago. And subsequently, we have been using it for many other things, many other types of particles, focal adhesions, all kinds of proteins related to DNA damage repair, like BRCA2, REP, the REP proteins, REP54, also microtubule tip associated proteins. All of this work is published. The references are given here. I'll be happy to give you the links if you're more interested in reading more details. And we've also applied it to something completely different. We've tried it on many different things. So here's an example from medical imaging, or actually it's actually preclinical imaging. Tagged MRI. I think this is not a human subject, but an animal, just to test the concept. So this is the beating heart that you see here over time. And so here, if you want to quantify the dynamics of the beating heart, you would have to track each of the intersections here in this magnetic pattern introduced by magnetic tagging, magnetic resonance imaging. And so we did that using exactly the same framework, just redesigning this transition model and the observation model to make it work for this specific data. What do the targets look like here? It's very different from these microscopy particle tracking applications. But it can be done. And we published that 9 years ago. And another application that we've been using it for is neuron reconstruction. So what you see here is a three-dimensional image of a single neuron. Neuroscientists are making these kind of images on a routine basis almost to study the morphology of neuronal cells and how they are different in different parts of the brain and how they may degenerate under different conditions. So there's a lot of neurobiology, neuroscience that is generating this kind of image data. But to quantify the morphology of these cells, you really need to change this pixel or voxel data into a much more compact and much more accessible representation, and turn these billions of pixels or voxels into something like this, which is a graph representation of the neuronal tree, of the dendritic tree. And here again, we've been playing with this framework, this Bayesian estimation framework. The way it works is you can, for example, you would need to start with some reliable seed points, which you could extract with a method that Alex is also very familiar with, doing the Hessian analysis, computing the second order image derivatives, compute the eigenvalues and the eigenvectors, which then give you some sense of where there are tube-like structures and what their local orientation is, right? So you can do this, you can come up with measures that give you some kind of reliability index of where to sample reliable seed points. And then for each of these seed points, you could define a state vector, for example, its position, local orientation from the eigenvectors, and also the local diameter estimate. If you've got a bunch of these seed points, you can run this mechanism. Of course, here again, you need to design the right transition and observation models, but then you can use the very same framework for segmenting these dendrites in these images simply by turning the segmentation problem into a tracking problem. So that's what we did here. So you start with a bunch of seed points, you track them all the way through, and then you start with another set of seed points. And this way you can build up a whole network of partially traced dendrites that you then need to put into some kind of graph representation, of course. But it works very well. We've compared this on many different data. So here are some examples. The red pixels are the tracing results. They're slightly offset on purpose, so you can see the underlying image structures as well. We've quantitatively compared that to state-of-the-art neuron reconstruction methods in neurobiology. I'm not going to go into details here, but our probabilistic neuron reconstructor is really doing very well. And that's what we've been using in a number of studies. The data here that we used is partly from the Diadem Challenge, but also from the Big Neuron Project. It's a very big international project that I've been coordinating with a bunch of other people as well in the US and in China. We've been benchmarking here, I think, more than 40 different methods for neuron reconstruction, and we've collected something like 40,000 data sets or something. It's huge. We're still working on this. A big paper is in the making, and we hope to publish that later this year. So this is a paper where we kind of announced this international project, if you're interested in more details. Okay, so what I've been repeating a couple of times now is it's a great framework, but every time it requires redesigning these models, right? So at some point we got a little bit tired of that, and we thought, why are we doing this if probably we can learn these models from the data, right? So use machine learning techniques to deduce the best models from the data. And so that's what we've been doing in the last few years. Not exactly using the same framework anymore, but more generally just trying to learn from data to predict where the targets of interest are and how to link them over time as well. So we've been using deep learning. We've embraced deep learning like everybody these days, simply because it works very well. It's not always easy. You do have to do a bit of engineering work to make it work well, but it can be done. And in many cases, it performs better than these more traditional techniques, although not necessarily. So there's still more work to be done, I think. So here's an example of a network that we've designed, a recurrent neural network using these long short-term memory elements to predict. So this is for online tracking applications. So if you're tracking particles over time, then at any given time point, you've already built up a set of tracklets, as we call them, so partial trajectories. And then for the next time step, the task is to connect the detections properly with these partial trajectories, these tracklets. And you can use very simple models for that. You could say, we're just going to pick the nearest particle, in the next time point, and that's probably the right one. But we want to do this in a bit more sophisticated way, because the motion of these particles can be much more complicated. And you want to take that into account in building trajectories, so solving the data association problem. And so we came up with this network, which uses these partial trajectories, these tracklets, to predict, going from one time point to the next, where the particles are going, to be able to pick the right detection in the next time point to continue the trajectory. And so this works very well. We published it last year. We tested it on data from the particle tracking challenge, which we did a couple of years ago. Well, almost 8 years ago or something. Published in 2014. The cool thing about this is that it's a big benchmark of all kinds of tracking methods for particle tracking. And the data has ground truth because we simulated it. This is entirely based on simulation. In microscopy, you can simulate things quite well, I have to say. At least when you do data analysis down to the molecular level. But even at the cell level, in the cell tracking challenge, which I'm going to mention in a second as well, we've been doing some modeling or simulation as well. But so, for example, if you look at the performance of this technique, it's not better than the state-of-the-art, more traditional, computer vision tracking methods. But it's doing quite well. So this is a lot of stuff here. Let me briefly explain. So here are different metrics, alpha, beta, and the Jacquard similarity coefficient for detections and for trajectories. I'm not going to go into technical details here, but these are metrics that are used in the particle tracking challenge. And in this column, you see the behavior, the performance of the different linking methods listed here, which I have no time to go into details either, but there's just different methods. Our method is the recurrent neural network method, the red curves. So here we're looking at what happens if you increase the number of false positive detections or the number of false negative detections given certain levels of false positive detections. So this is a kind of snapshot of the performance or the behavior of these different linking methods as the data deteriorates. And you can see that our method performs quite well competitive to some of the state-of-the-art methods. We could do better, maybe, so this is still ongoing research, but the most important thing here is that all the other methods, there were years of development behind them, right? All this careful design of dynamics models and observation models and whatever, thinking very intelligently about what are the most important features in the data that you need to extract. We did none of that, okay? We just used a deep neural network to learn all that stuff from the data. So that's a great advantage. So even though we're not necessarily better at this moment, it makes it a lot easier for users. If you want to apply it to a new tracking problem, just provide it with examples or very reliable simulations, and then train the network. and use it. I mean, it's from a user perspective much easier. We've also applied it to real data. It seems to give similar performance as expert manual annotation. Other examples of deep learning that we've been working on in the last few years is detecting nerve fibers in microscopy images, detecting neurons in high content screens, also doing what's called track segmentation, because usually these particles, they exhibit different types of dynamic behavior in different time intervals, and you want to segment these out to analyze them separately. So that is a problem of called track segmentation. So we've used it for that as well. We've used it for critical point detection, for neuron reconstruction, for example, finding the bifurcation points, the endpoints, to use them as seed points for neuron reconstruction. So we just published that, I think last month or the month before. And this is the craziest thing we've done. It's not published yet, but I just wanted to briefly mention it because I think it's really cool, is how to completely optimize the deep networks themselves for a given task, such as, this is the first thing we've been looking into, cell segmentation. So many people have been using whatever kinds of networks, but again, they were manually designing and tweaking these networks, right? And so we wanted to avoid that well, and we used kind of an auto machine learning approach called a neural architecture search to completely automatically find the best deep neural architecture for this problem. And so we did use a kind of base structure, a UNet kind of structure, but it's very different from a UNet because every layer is basically, it's actually not a layer, but basically there's a block. Every block has a number of layers, different types of operations. They can occur in different orders. And this is the degrees of freedom you have in the design of this network. And what the AutoML algorithm does is to figure out what is the optimal design, the optimal configuration of these blocks to make the network perform as best as possible. So we've done that, compared it on data from the cell tracking challenge that we published a couple of years ago. And we got very good performance for very different types of microscopy data. So phase contrast, differential interference contrast, fluorescence, very different cell types, cell shapes, but it seems to be working consistently very well among the top performing methods in the cell tracking challenge. The next edition, by the way, is next month at the ISB conference. Okay, so that's I'm a little bit over time. I'm going to wrap up. So the main topics we're talking about in my group at the moment that we're working on are these neural architecture search methods to find optimal network configurations, how to reduce manual annotation either by simulation or using some form of unsupervised deep learning. Multimodal deep learning, combining imaging and other types of data, genomics, for example. And ultimately, this is the point I wanted to make, interpretable deep learning, because we moved from these explicit model designs to kind of an implicit model extraction from the data, but that is not where we want to stop, of course, even if the methods perform very well. We want to learn what these networks are actually doing. So this kind of takes us full circle back to explicit, at least understanding of what these methods have learned from the data. So that's what we're working on and apply it to a range of problems in biomedical imaging. Okay, I have to thank a lot of people. There's many more people to thank, but these are the people that contributed to the work I showed today. If you're interested more broadly in bioimage analysis and deep learning, you might find this paper interesting that I published last year, which gives a very high-level overview with more than 300 references, mostly other reviews, other review papers about deep learning in bioimage analysis. Okay, thank you very much for your attention.
Thanks so much, Eric. Fantastic job. That also exemplifies the differences. So I think your talk and Leo's talks were quite complementary in terms of the data sets you're working on and different reasons why, in a sense, you do need to automate the process of training and developing these networks. I was just wondering, from your perspective, what is the main distinguishing factor? I mean, you worked in the past in medical as much as now in biological imaging, and in medical imaging we have these huge data sets that Leo explained they need to be annotated, which is a bit of a nightmare sometimes. But in biology, what I tend to find is that you have one experiment is one data set, and the next experiment is almost like a completely new data set. So
yeah,
how do you come about to in that situation utilizing these techniques, right? That require, even if you would have the annotations, big sets, right?
Yeah, that is a big problem. I mean, in biology, nothing is standardized. Every biology can turn the knobs of their microscope any way they like. There are no protocols, nothing standardized. So that is indeed a very big challenge. And so I would say even more than in medical imaging, maybe in bioimaging, it's a really tough job to come up with robust methods that are more broadly applicable than just for that very narrowly defined data set. And yeah, so that's what I don't know if I have a very clear answer to your question, but that's definitely something that we are very aware of, and that kind of pushes us to the limits of, developing both robust, but at the same time kind of generic frameworks that we can apply to multiple things, such as this Bayesian estimation framework that we've been using for many years. And now we try to do the same with these deep learning approaches. And here again, I think this concept of automating the design of the neural networks is very important, because you don't want to manually, you want to minimize this manual tweaking and designing and testing all the time. You want to let the computer automate the whole pipeline, the whole process, basically. But yeah, again, I mean, at some point, you will need to provide example data, right? So that's definitely the bottleneck also in biology, just like in medical imaging.
Okay, so thanks a lot. I'd like to thank both Leo and Eric again. I think Dora, we need your help to be back in track.
Yes, shall we take a photo together?
Yeah, I think Leo, if you could join in for a moment.
Wait a minute. Please turn on your camera. Please turn on your camera. Okay, I will take some more photos.
Nice to see you, Ken.
Good to hear from you. Hello. Sorry.
Very good.
Hello.
So, Dora, I think you're taking over from here, right? Oh, that's great. We have all the speakers from both sessions. That's great.
Yes.
Yes.
Really, yes. Very nice.
And thanks to everyone.
Okay, thank you, everyone. Okay, thank you. And thank you, Professor Frankie. And now let me introduce our next session chair, Professor Yudong Zhang. And he is also the co-conference chair of MICAD. He comes from University of Leicester. Let's welcome.
Okay, thank you, Dora. Can you hear my voice?
Yes, yes, I can.
Okay, thank you. So first, I will briefly introduce myself. And as you know, I'm currently the chair in knowledge discovery and machine learning. And it's an honor for me to hold the session chair for the following 3 keynote speakers. And originally, we planned to, I think we will start at 9:30 a.m. It's a bit later, so I will try to accelerate. The first keynote speaker will be Professor Robin Strand. He is the head of division of the visual information and interaction from the Uppsala University, Sweden. And his presentation title is Large Cohort Analysis in Medical Image Processing. So I will pass over to Professor Robin Strand.
Great, thank you so much. Thanks for the kind introduction and thanks for inviting me. Thank you to Dora and the organizing committee, of course. Thank you so much. So my name is Robin Strand. I'm a professor at Uppsala University. Please interrupt if the sound is bad or if there are any problems with my slides and so on. I'll share my screen. I hope that works out well. So I'm at Uppsala University. I'm both at the Department of Information Technology and the Department of Surgical Sciences. My position is at the Department of Information Technology, but I have lots of collaboration with the radiology division at the Surgical Sciences Department. And what I will talk about today is a bit of general aspects of large cohort analysis in medical image processing, or big data kind of analysis in medical image processing, and some of the projects on whole body MR image analysis that I'm leading. And I'm also leading other projects on neuroimaging and radiation therapy with MR, DNAC equipment and so on. But this talk will not focus on them. So let's move on to the kind of background. The image processing development since the 60s or 70s up until today. So as you probably all know, that there has been a progress towards data-driven analysis since the 60s or 70s. And in the 70s, the image analysis and image processing was mainly based on low-level image processing decision trees kind of algorithms. And this was partly due to lack of computational capacity, or to a large extent so, but also lack of image data. And during the years, the computational capacity and the image data has increased and is still increasing. So I would say that it's an exponential kind of increase for both of them. And the trend today is very clearly towards data-driven image analysis. So looser models and more focus on the actual data to do the analysis. So this is the way I would like to describe the situation we are in today. So the availability of image data is increasing exponentially. The computational capacity is increasing, and the method efficiency kind of hooks onto that and is also increasing. So what we have today is the deep learning kind of hype, as you all know. And this has the availability of image data and the computational capacity, and to enable computation on the kind of consumer hardware GPUs has made that possible. So to focus a bit on the computational capacity, I would like to say that the Moore's law is still in effect. I don't know if it's a law, but still we see this exponential increase. So this is an image from Steve Jurvetson. So this shows the calculations per second per constant dollar over time. And the hardware, as you can see, perhaps now it's GPUs in the last few last few years. And this, as I said before, it's to a large extent actually driven by consumer components and gaming GPUs. Very efficient GPUs are available at reasonably low cost today. And if you focus a bit on the availability of image data, so for example, my cell phone, it's not a fancy one, but it has 4 cameras and a dozen apps that are kind of hungry to get me to acquire image data. So image data is acquired very much today compared to previous years. And this can be seen also in the kind of radiology and in the clinical setting. So here are some plots from a paper that I found that showed up until 2010. So it's actually a bit old now, but there is a dramatic increase in the amount of image data being collected, and this also puts high demands on radiologists. So in 2010, a radiologist needed to interpret an image every 3rd to 4th second, all workday, every workday. And this has also been highlighted in the morning today by Leo, this situation with a huge amount of data in a clinical situation. And also research image cohorts or kind of biobanks, if you like, or data sets available. So cohorts here is a group of subjects who share a defining characteristic. What we can see is that there is lots and lots of image data available. So internationally, we have the TCIA, UK Biobank, where they aim for 100,000 whole body image scans and other image scans as well. So this is MR. There is a German national cohort, 30,000, and these are just some more or less random examples. There are many, many initiatives to acquire lots and lots of image data. And local cohorts in Uppsala, I mentioned them because I will show some examples on that in a while. So the POEM cohort, for example, where the imaging is done on roughly 500 subjects. So this is also whole body MR image data. And method efficiency. So how to illustrate that? We are all aware of the deep learning kind of era we are in now. I wanted to illustrate it in this way. So in 2012, we participated with an interactive method, but it's not a deep learning method, in a challenge, MICAD challenge, PROMISE. So this was a challenge about prostate segmentation. And we performed very well. We made it to the 3rd place, and we did really good in this competition challenge. Today, so this challenge is still ongoing. Now we're at rank 245 out of 327. So it's a drastic decrease, of course, in the rank for our method. And what has happened since then? Well, the deep learning kind of explosion has happened. In 2012, that was the year when the AlexNet won the ImageNet challenge, the large-scale visual recognition challenge or competition. As you probably are aware of. So what we actually see today are methods that are based on kind of finding patterns in large amounts of data. So this is a data-driven approach with no or few predefined features. So we have seen a dramatic kind of development in the image processing methodology. All right, so what I wanted to show in terms of kind of projects today is it's two approaches for analysis of large-scale medical image data, and this is based on whole body image data, as I said, and it's magnetic resonance imaging. So one of them is called Bioimage, and the other one is a more recent initiative. So this is what we call aggregated saliency or cohort saliency. And built into the methods are, to different degree, assumptions, of course. So kind of formalized experts' experience and intuition. And we have the model that represents the assumptions by parameters to kind of different degree. And then the data is also very important here. We need lots of data for these methods. So let me start with the immunomics approach. So this is something that we have developed. So this is an analysis of whole body image data and other biomarkers. And it's an approach where we, from large cohorts with non-imaging data or kind of alternative biomarkers, can do analysis without explicitly doing segmentation in the image data, but do this in a kind of holistic manner. I'll explain the concept in the upcoming slides, but what we can see here in a kind of traditional analysis, what we would do is to derive some explicit measurements from the image data. I don't know, the volume of the liver, for example, or so, and then do statistical analysis based on that. What we do in immunomics is point-wise or voxel-wise analysis, statistical analysis. And it's kind of holistic because the whole human body is analyzed. So this is as opposed to region of interest-based method or segmentation-based methods, where information is extracted from predefined, pre-segmented regions. And all the collected image data is used in the analysis. And also this approach allows relationships to all other collected non-imaging patient information or subject information. So how do we do this? Well, it's based on image registration. What we do is we find point-to-point correspondences. So this is similar to what has been done in neuroimaging for several years, but we do it in the whole body, in a whole body imaging settings instead. So we have a correspondence between the same position for all of the subjects in the cohort. And with that information, we can do the statistical analysis voxel-wise. And in that way, we can get these kind of relationship maps or correlation maps or R maps, if you like, so that we can color code the correlation in each of the position in the human body. So it's essentially one statistical test per voxel. And the kind of key component here is image registration. We use volume images for this, but it's illustrated here on just a single coronal slice. And the image registration problem is difficult in this setting because there is a huge variability in anatomy or morphology in the human body, and for example, the subcutaneous fat repose varies a lot between subjects. So this is something that we have been working quite a lot on to develop. The imaging parameters that we focus on here, it's magnetic resonance imaging, as I said, it's fat content. So this is fat water separated magnetic resonance imaging, so MR images, with the Dixon technique, so that we, for each voxel, can get the fat content or fat percentage, so absolute values, which is really, really valuable in the image registration. And in the image registration process, we get a deformation field, so we can compute the local volume deformation in each voxel. And in some of the analysis, we also have access to PET data, or we also use PET data, typically FDG PET. So here's another illustration of the immunomics concept. So we deform all the whole body volume images to the same reference space, so the same coordinate system. And once that is done, we have the point-wise or voxel-wise correspondences, and we can do the correlation analysis. And in that way, we can get these colorful correlation maps where each voxel is color-coded with a R value or correlation to the non-imaging data or the biomarker that we're interested in here. We will look at a number of examples in a short while. Method development in immunomics. We have developed an image registration method, or there are actually a few different versions of this, where we utilize tissue-specific elasticity constraints. So we make an assumption that bone is relatively rigid and has low inter-subject variation, and that lean tissue is less rigid and has higher inter-individual variation, whereas adipose tissue or fat is highly elastic and has high inter-subject variation. As I said, we map all the subjects, so the whole body volume images to the same coordinate system, to a reference coordinate system. And what we have done in some of the analysis is to just pick one subject and decide that this is the average reference coordinate system. But what we ideally want to do is to actually compute the average reference space as an optimization of the reference space. So we have developed a method to generate the reference space for the whole body image processing that has zero voxel-wise average volume change when mapped to a cohort. So if we map all the whole body volumes to this computed average reference space, then the average deformation is zero. We have also developed methods for multiple comparison correction. As I said before, we do voxel-wise correlations, statistical tests, and of course neighboring voxels are not independent. So there is a dependence between neighboring voxels. So then therefore we have developed multiple comparison correction techniques. Methods based on permutation-based cluster extent correction and threshold-free cluster enhancements perform very well in this. But there are several different approaches for that. One for only is a bit too restrictive because we're doing so many statistical tests. Let's look at an example. So this is a proof of principle analysis, correlations between local tissue volume and the total fat mass, lean mass, and also correlations to waist-hip ratio. So the image data here, this is the Bioimage cohort, the local Uppsala cohort. Lars Lind is the PI. All the subjects are age 50, and in this analysis, we use 326 subjects. All right, so the first analysis, this is tissue volume, local expansion contraction in the image registration. So this is tissue volume, and then point-wise correlations to the total fat mass, how much fat mass the subject has in total. So this is measured by bioimpedance analysis. And here we can see, again, this is a proof of concept. So we can see that there is a positive correlation between total fat mass and subcutaneous fat. So this is in female, coronal slice. Also to the size of the liver, and also perirenal fat. I don't know if we can see the kidneys. It's a bit difficult, but that is the case. And a negative correlation in lungs. So the more the total fat mass, the smaller the lungs. And then we also did in this proof of concept analysis tissue volume versus lean mass. So then we can see that the more lean mass the subject has, the more muscle it has, which is expected. So the lean mass, that is essentially muscles. We also see a positive correlation in the long bones in legs and arms. You see the red color here. Positive correlations in lungs and also in liver. So what I'm showing here is a coronal slice. It's actually a curved coronal slice visualized to the right here, and then a number of axial slices also shown in this illustration. Positive correlations are color-coded with one color, so red is strong positive correlation, and negative correlations are color-coded with cold colors. So blue is strong negative correlation. Waist-hip ratio, we can see as expected that we have a positive correlation to the subcutaneous fat around the waist. And it's also a positive correlation in the liver, negative in the lungs again. So the imaging biomarker that we use here, that's tissue volume. We can also use fat content. This is information that we have from the fat water separated MR images. So this is also point-wise correlations. So fat content versus total fat mass. And here the correlations are a bit weaker, but we can see a positive correlation in liver, for example. And here we can see the perirenal fats more clearly. So positive correlations in liver, meaning that the higher the total fat mass, the higher the fat content in the liver. So this is proof of concept analysis. Let's look at a more realistic and perhaps interesting from medical point of view analysis, immunomics analysis. So this is immunomics in the metabolic syndrome. And the metabolic syndrome is the medical term for a combination of diabetes, high blood pressure, and obesity. If you have the metabolic syndrome, it puts you at a greater risk of getting coronary heart disease, stroke, and other conditions that affect the blood vessels. So it's a combination of the increased abdominal circumference. So this is if you have abdominal obesity. Here it's called waist circumference. Right, so what we see here is that if you have high waist circumference, then you have more subcutaneous fat, also more visceral fat. We see a negative correlation in the lungs again. This is again now in the POEM cohort. The colors are coded a bit different in this analysis, but in a similar fashion. So this is actually based on group comparisons instead of correlation analysis, but that doesn't matter that much here. And then another parameter or criteria for the metabolic syndrome is the HDL cholesterol. So elevated. So this is HDL cholesterol. And here we can see a positive correlation in the liver. Fasting glucose, so this relates to diabetes, also positive correlation in the liver. Blood pressure is also measured as one component or criteria for the metabolic syndrome. And here we can see a positive correlation or positive relation in the upper body, the subcutaneous fat, the liver, and so on. So this is tissue volume all the time. And then we also have triglycerides, so blood fat essentially from circulating biomarkers. We see a positive relation in the liver and also in the subcutaneous fat in the upper body. These are female subjects. So if we add all of these together, waist circumference, HDL cholesterol, fasting glucose, blood pressure, and triglycerides, we can get the metabolic syndrome. So the criterion is that you should have if you have abdominal obesity and two other criteria, then you have the metabolic syndrome. And here we can see the correlations with the metabolic syndrome, so the relations to the metabolic syndrome. And this analysis gives understanding on how the different components actually add to the full metabolic syndrome. Let's move on to another application. So this is anomaly detection. So in immunomics, we do a representation of normality. We have a whole body atlas. And if we do that on normal subjects, then by doing point-wise statistical tests of a new subject, we can see if there are any anomalies from the expected or from the normal material. And this is based on PET data. So the registration is done by the MR data, but then we have PET data for this as well. And the normalization of PET data was done by mediastinal blood pool mean FTG uptake. And so this is normalized PET data. The criterion is a large region of high FTG uptake. So this is in another cohort. And then we can see that we can actually detect anomalies automatically with this technique. And then for the imiomics analysis, we have applied this to several other non-imaging biomarkers relating to obesity and diabetes, and we're also doing genetic analysis now, etc. Let's move on to the second kind of cohort analysis or large-scale data analysis. So this is aggregated saliency, and this we applied to the UK Biobank data, and this is a regression technique. So what we essentially did was to do regression, where the independent variables is the image data and the dependent variable is something else. In this example, it's age, but we will see examples of other dependent variables, liver fat and body composition markers, etc. So what we did here is we implemented a regression task. So this we have used both BDD and ResNet architectures. So from a large cohort, predict for each subject a single outcome variable. So this is the regression. And then we try to train the network to estimate this single outcome variable as well as possible. This is an example on prediction in years. So this is the age, the prediction versus the ground truth. You can see that we get quite good prediction of the age. So this is a basic task, and on top of that, we added aggregated saliency. So this is kind of part of explainable AI, or if you like, this saliency mapping. So we did that for each subject, saliency maps by GradCam, then gradient classification maps. And then we added all of the saliency maps to a single output. So this figure illustrates this. We have a two-dimensional input. We project the saliency to a three-dimensional space. We deform it to the reference space again, and then we project the saliency to the reference space. And this is the kind of result that we have achieved. So this is a preliminary study with 3,000 subjects in the UK Biobank imaging cohort. We have also results now on bigger data sets. So this is what we can see in the aggregated saliency when it comes to visual adipose tissue. We can see that the visual adipose tissue is actually highlighted. DEXA, so this is the total fat mass. Left thigh, we can see that the left thigh is actually lit up here, and right thigh, likewise. Liver fat, BMI, here we saw that the knees and the lungs really seem to be salient for this feature. Pulse rate, then we get response around the heart, and grip strength. So we see a strong response in muscles and actually also lungs. So this is also kind of proof of concept analysis, but we can see that it actually seems to work. Okay, I'm at the conclusions. So we are today in a unique situation with access to so much computing power, algorithms, and image data. I didn't talk that much about AI, but many believe that computer-assisted methods will revolutionize the clinical workflow. And in some narrow tasks, computer-assisted methods perform better than human. Imiomics, aggregated saliency, and other computer-assisted image processing methods can find patterns in the huge amount of data available today as a complement to human experts. And this enables increased disease understanding and automatic disease and pathology detection, etc. So this is my last slide with acknowledgements. Thank you so much, all.
Okay, thanks for Professor Robin's excellent presentation. And I will because due to the limited time, we can have only one questions from our audience. So do you have any questions? You can directly unmute and ask the question, or you can leave the question in the Q&A or in the chat window. Okay, Professor, may I ask you a question? Because I remember you mentioned the metabolic syndrome. So I just want to know, since the metabolic syndrome is sometimes a prosumer case for the diabetes, so do you think your research can help contribute, like contain, let's say, the diabetes and help the treatment?
And help the treatment. So this is a cohort analysis to find patterns in large data sets, so to speak. But this can for sure generate understanding of the disease. And I also want to mention that we have done advanced analysis when it comes to diabetes biomarkers. So we have analysis in that direction with which actually increases the understanding of the diabetes. Direct analysis for the kind of diagnosis. We're not there yet with this technique, but then again, it's more a tool for generating disease understanding.
Okay, thank you. And also, there's one comment from our audience, and he said, "Thanks for the information, very interesting."
All right, thank you so much. Thanks again for inviting me.
Okay, thank you again. Thanks, Professor Robin. So due to the limited time, we have to move to the next keynote speaker. Thank you again.
Thank you.
Okay, so now I will introduce the next keynote speaker, who is Dr. Raphael Snitman. And his presentation title is Self-Instrument Detection During Surgery. So Dr. Raphael is now an assistant professor at the ARTORG Center for Biomedical Engineering Research of the University of Bern, Switzerland. His research interests lies in the fields of computer vision and machine learning with application to biomedical imaging, surgery, and histology. So let's welcome Dr. Raphael. Okay, thank you.
Hi, thank you very much for the introduction. I hope you can see my slides, myself, and here. And if anything goes haywire during the next few minutes, please just let me know. Great. So yeah, as was mentioned, my name is Raphael Snitman. I'm a professor at the University of Bern, where I lead a group in machine learning and computer vision for medical applications and imaging. Both on the side of diagnostics, but also on interventions. And so today, what I'm going to be talking about is a little bit about what we've been doing over the last almost decade when it comes to finding instruments in computer vision, from a computer vision point of view, but finding instruments in surgery or looking at video feeds of surgery. And there's been, as you'll see, a tremendous amount of progress that has been done, which is great. And now we're coming at a point where we start having to really look a little bit inside and say, well, what's the last step that we need to go further? And so that's what I'll spend the last part of today's talk looking at, how do we get over those last few cases that still are problematic? So just to get going, what I'm really talking about when I mean finding instruments in surgery is something like this. So this is a video feed from a Da Vinci surgical instrument scene. So this is the Da Vinci robot. You can see different instruments that are being manipulated by a robotic system where it's a console with a physician operating it next to it and the robot sitting over the patient with the instrument inside the gastric cavity. And so here you can see different instruments are being used. The frame rate here is at about 1 frame per second, so a little bit reduced, but in reality it's around 60 frames per second. You see tool interactions, you see an anatomy which is highly complex, deformable, with shadows. Typically you can have blood, you have change of scenes, scales, focus, and so on. So really a rich environment of things happening. And so over the last, I'd say, decade, there's been a trend to provide computer vision methods that can look at these video sequences and analyze them, either post hoc, so meaning you have the whole sequence and now you want to say something about the content, what were the different things that went on during the surgery, were there problems, or in a live mode, so in the sense in a real-time perspective, what is happening to the instruments, and potentially can you provide some safety measures for a robotic system that is using this information. So are you coming close to a structure inside the body that you should pay particular attention to, and so on. So you might wonder, well, if you have a robotic system, why do you care, right? Why do you care about looking at imaging? So that's a very normal question. And so this is actually a visualization provided by Austin Ryder, who used to be at Columbia, highlighting what is the difference between what the robotic system, so the actuators of the robot, when you overlay them on the imaging. And that's this yellow line, right? And yet you see the instrument is actually somewhere else. And that's to highlight the fact that just using the information from the robotic system to know where the instruments are is often actually really a bad idea, because those aren't precise to the extent that you need them to do anything meaningful within the surgery. So that's why computer vision methods for analyzing video content have really gathered quite an interest in the last few years, and now they're a regular international challenge for detection and segmentation of instruments in this surgical environment. So what we've seen over the last bit, as I mentioned, is sheer progress, and that's fantastic. This is just an example coming not from gastric surgery, but this time from eye surgery. This is a surgical instrument. That's the retina behind. And here again, you want to be able to detect these instruments during the procedures. Now, on the right, I'm showing you performances, and forget the actual methods. That's not important. The actually interesting part is looking at the progress that we've seen. And so over the years, from green, blue, magenta, and now red, what you see is over time is an interesting progress in the development of these methods. They're becoming more and more accurate in their ability to track more and more precisely. So this is threshold error, so pixel-wise threshold errors versus accuracy. And this has been on one side because the methods have gotten better and better, but also on the flip side because there's been more and more data to train them. And that's why these challenges are more and more attended in the recent past. So, but why is it hard? Why is it hard? And so broadly put, the problem comes down to generalization. While it might seem that in surgery, you're basically in a very enclosed environment, things are very controlled, which is true, the reality is that a lot of things can happen and will happen during surgery. So that can go from dealing with blur, simple things like image blur that will happen naturally during the procedures, to shadows, to how do you distinguish the instrument from a shadow, occlusions, from the anatomy, discontinuities from the instrument because of the anatomy, smoke and blood that might appear. So there's a wide range of things that are going on in these video sequences. And so being able to have very resilient and very robust methods that are able to detect these instruments has been and remains to some extent a challenge. And that's what I'm going to be talking about now, is just some methods that we've developed in the group to kind of move us forward along this path. And then I'll show, well, what's really remaining anymore at this point in time, and what are we looking into to achieving the next step. So I'm going to start with something that makes sense into trying to estimate pose of instruments. So when I mean pose estimation, I'm really talking about being able to identify where a surgical instrument is in a field of view. So what we can typically say when we have an image like this is this whole scene actually can be, you can break it down into a scene might have multiple instruments that you want to detect. So you have that already to take into account. And at the same time, an instrument has multiple parts to it. So it has a shaft, it has a wrist, it has tips, it has tweezers. These things can open and close like scissors. So you have these multiple parts that are important in order to understand where they are, both in terms of robotics, but also in terms of what is the general thing that's happening during surgery. What is actually going on? So in the first step, one of the things some years ago that we thought was, well, let's try to have some kind of scene model to understand this entire scene when it comes down to the instrument. Now, when I mean a scene model, I'm really just talking about the instruments themselves, not the much more complex geometry that's happening behind. So you can take a probabilistic point of view, like what we saw earlier, Eric's talk before the break. And really what we were interested in doing is having a mathematical approach to detecting multiple instruments. And these multiple instruments have different parts. So you have the different tools, but you also have for every tool, the different parts that are in this place. And you want to somehow learn this joint distribution, which is highly, highly complex. So one simple way to break this down is to assume that you have a much simpler distribution, which at the time we assumed a fully an independence between the instruments themselves, but also a conditional independence between the joints or the parts given the instrument itself. And so you have a very, very simple representation now of a complex scene. So once you have this kind of scene model, you can start to model. And that's what we started looking at. So this first part is really about a binary representation of whether or not the instrument is there. And that's basically saying image classification, or is this image containing an instrument of type A or B? And on the other side, this conditional distribution that we have of the joints given the instruments, well, this can also be modeled in a likelihood model. So in particular, you can say, well, if my instrument is there, or it's not there rather, in this case, well, you're just going to assume that it's a uniform distribution. And on the flip side, if it's actually present, we're just going to have a 2D representation that's representing this image and a point, right? So a point is representing where now a joint is located on an image. So it's a key point representation. The nice thing about a model like this is you can actually optimize it very well using the binary cross entropy, which breaks down these components very nicely, because these Bayesian factors can actually be very nicely propagated through an entropic function. So what we basically have is a very simple network approach, which on the first part, if you want to estimate the likelihood of the priors, if you want, of whether or not an instrument is there, can just boil down to a standard architecture network that is trying to do classification, whether or not an instrument or another is present. And in order to basically estimate the rest of your distribution, you can actually use a unit-like structure to estimate the joint distributions of the joints given in models. So a very simple approach with a simple function to optimize it. So in practice, when you do this, you can actually have some decent results, being able to do multiple instrument tracking with these different joints. What I'm showing on the left in green are the ground truth points, and in colored are the overlaid estimates of the model. And on the right here is just the numbers actually showing this. In this case, it's automatically detecting whether or not there's one or multiple instruments. That's what that first term was looking to optimize for. And in the second, it's actually all these numbers provided. So in general, this was providing a very interesting approach, but it has its limitations, being that all you're doing is estimating these key points, which often are very ill-defined, and for every instrument, those change, in fact. So that's why a lot of the community, not just us, but a lot of the community started thinking about segmentation in a much broader way, or even beyond that, going from instruments, or from pixels rather, to instrument segmentations and instances as a whole. So the so-called instant classification problem. So in our setting, what's a little bit unique is that we have these surgical instruments like this. And if you're talking about segmentation, well, it's important to specify what kind of segmentation are we talking about. So on one side, you can say, I'm going to segment the parts. So perhaps the shaft of the instrument. And so for this one image here, you can see that you can classify a shaft for two different instruments in the same way, right? This is the same type of structure or part of an instrument, the shaft. And then the neck is a different part, right? But yet at the same time, if you think about it more globally, then really you have two different instrument types that are here. And this highlights the first problem to realize when we talk about detecting instances in these cases, is that for many instruments, actually, their parts look the same, but only very specific parts within those instruments allow you to say something about the type of instrument they are. So what distinguishes these two instruments isn't the shaft, it's this tiny bit at the very end, right? And that's what allows you to ultimately be able to make this judgment. So context, as you can imagine, plays a critical role in being able to make proper decisions on these kinds of cases. So this is something that we've witnessed also over the last few years with challenges, international challenges, both at MICAD and others, is that when we think about binary segmentation, part segmentation, and instrument segmentation, really it's a difficulty going from top to bottom. And so here what I'm showing was an extract of a paper in the community looking at basically the ground truth for these different cases for this one image and how different methods were performing. And so what you can see is that binary segmentation in general does very, very well. When we consider parts, it does pretty well as well. In this case, the results are pretty good, but it's not perfect. So in sense, you have some errors that are propagating. And for instance, here we're missing potentially some parts. And then for the instruments, it's often very confusing. It doesn't really know because the context is what's allowing you to make a decision. So here you can really see that on instrument segmentation itself, the results are quite poor. And so that's what we started focusing on. How can we approach this last part a little bit more effectively? So in particular, we need to overcome a few things. First, that different instruments, as I mentioned, have similar parts to them, and they appear the same way. Some instruments can occupy huge proportions of the image, depending on what the surgeon is doing, and others can be very small. And then also instruments can overlap and form discontinuities. And that makes it really hard in order to say what pixel belongs to one instrument and so on, right? So if two instruments are crossing, it makes that distinction really hard. So many approaches that have tried to go in this way have really tried to first have a method that finds a bounding box around your instrument, and from this, do the segmentation. And so that helps with some of these things, but often one of the issues is that you include, as in this case here, you include information from multiple instruments. And that's where all the errors then come through, because they assume that there's only one instrument in these boxes. And so it doesn't really know how to handle this overlap, right? And so this is where we figured, well, hold on. Instead of using these bounding boxes to do this, what we wanted to do is leverage the instances and the parts at the same time. And so this is what I'll briefly show. This is recent work that was of this year, where we're going to approach it using a network architecture that on one side is going to do very effective mask or part segmentation. As I showed before, we know from the community how to do this pretty well. This is basically doing segmentation with losses that are very standard. This works out well. But then what we're also going to do is try to estimate two other quantities that are related and help actually with the optimization process. And that's the offset estimation. So meaning for every pixel in an image, we want to know how far in Euclidean distance it is from the centroid of the instrument it actually belongs to. So if you're part of an instrument, we want to know how far that pixel belongs to. And then at the same time, we want to estimate the center of the instrument. Okay, so these two quantities, therefore, are codependent on each other, but they're estimated for the moment separately. From this, we can then start to think about how to bring these quantities together. So on one side, we can take this and use it as a mask to combine it with the offset. So this is basically just a dot product allowing for a masking effect. And then combine this with the centroid approach that we have here. And so what you end up having then are piecewise constant instances for a given instrument that uses this mask offset and the centroid to determine who belongs to who. And from this, you can optimize this and then classify each of the instruments or instances that you have into a traditional image classification problem for every instrument part or instance at that point. And when you do that, this is what you get. Basically, this is a video from a challenge data set that was from last year. What you can see is that now we're able to more or less detect the instruments, segment them fairly well. And even in cases where you have some overlap, that's what's happening here, you're able to do something that is fairly reasonable in terms of instance segmentation and classification of these instruments. So we were quite happy with this results and looking very, very positive about the ability to move this forward in practice, of course. But as always, it's really important to understand where your models are making mistakes. So we took a deep dive about a year ago into understanding this. And so we still saw mistakes like this. So here it's a completely blurry image. So most of the cases are correctly predicted, but actually one of them is very far off. And then we had cases like this, where actually we are losing a quarter of the image because of some processing that had happened on the console system. And this is exactly where we stand in a way, where we have lots of cases that are working great. And now if you want to have this running in a critical system, these less than 1% mistakes that we get are due to a variety of facts. And that's what I'd like to talk a little bit about now is some recent work and direction that we're looking into. It's really about the fact that neural networks are fantastic, but fundamentally they are unaware of what they don't know. And what do I mean by that? So I'm going to switch context out of surgery and into diagnostics. In this case, it's in the context of OCT imaging, so optical coherence tomography. So this is eye care mainly. This is an image of a cross-section of an eye scan. And here what you see are parts of the retina. And in fact, what I'm going to be talking about is unrelated to the anatomy. It's unrelated to the application itself. I'm just showing you a generic problem, in fact. So this will translate to MRI, to CT, and so on and so forth. So what happens often is that you take an image, you pass it through your neural network, and you're hoping to get some binary classification. Is this case pathological or healthy? In this case, the model says it's pathological, and you're happy because that's actually true. In this case, you have a healthy case, you push it through your network, and it says you're healthy, and that's great. But the question is what happens in this case where you now push an image that is corrupted. So half of the left side somehow has disappeared. This is coming from the actual machine itself. And you push it through the system, and it's again going to give you an answer. And this is where the danger comes in, because you've predicted something when you really shouldn't have, right? And so we actually applied this on a very large cohort of about 100,000 OCT scans that corresponded to about 50,000 patients that are in our eye clinic here in Bern. And we started seeing mistakes of this kind. So in this case, this turned out to be a real mistake. Our system shouldn't evaluate it. Why? Because this is actually a different part of the anatomy. This is looking at a different part of the eye, which we shouldn't consider. And then we found other mistakes like this one, a shot noise, and then other artifacts. And then the list just kept going and going and going. And these are all artifacts from large acquisitions that are done in the hospital. And so very quickly, it became clear that we were never going to be able to identify these kinds of extreme cases or outlier cases one by one. So finding rules to remove or avoid evaluating these images, we were never going to be able to scale with the complexity of the problem. And that's actually what we started looking at later, which is basically a problem called out of distribution detection. Typically, what you have is a network that's processing an image or a corrupted one, and you have the system, and what you want to avoid is corrupted images being predicted at all. So what a lot of the community in out of distribution has looked at is the following setup. Can you somehow have a module or something in before stop the evaluation when you actually shouldn't be processing it? And now that can be a corruption like a faulty image, but it could also be a different application. So if you have a method that's segmenting or detecting cancer of the lungs, when you run it on a CT scanner looking at the kidneys, well, you shouldn't be making any prediction on there. It should just be saying something of the form, well, this is a different anatomy. My method shouldn't even be applicable here. So this is what we started looking at, and I'll talk about one of the approaches that we came up with. So concretely, the idea is you have a data set, and in our case, our data set actually has no labels. I'm not even going to talk about we want to do classification or detection or segmentation. That's actually completely label free. And so we're going to have a network, and this network is going to take these images and project them into some latent space, right? We're not talking about classification. We're just using this network as a way to project into some low dimensional space compared to the image. And so when you do this over the data set, you can now think of these points in a high dimensional space. I'm just showing them here in 2 dimensions for the purpose of illustration. But at this point, this embedding can be changed, of course, when you train a network. And when you train the network, basically this cloud of point is going to morph and change in shape. And the question that we thought was, can we figure out a way to change the shape of this cloud in order to, whenever you present an image that's corrupted, when you push it forward into this space, well, that it falls outside of this massive cloud of points. So basically doing outlier detection in this high dimensional space. So our approach was the following. So again, we have a training data set. It's label free. So I don't know anything about the data except it's just image data. And we have a 2-stage process. So on one side, we have a network, which is basically going to take our images and project them into a D-dimensional space. That's a typical embedding approach. In our case, we're using a ResNet. That's almost a detail. And then we're really going to have a very simple approach, which is a kernel density estimation, which is going to build a probabilistic distribution over this high dimensional data and provide an R+ space. Now, what does that mean? So in practice, we have our cloud of point, and now we can model any new element as the probability of the observation using the latent representation of an image and all the data, so this cloud, using some kernel function, which is basically going to be a parsin window. And so now when you have a new point and you want to measure of this point in the space. So how do we actually train this in order to get something that's doing well? We are just going to actually maximize the log likelihood of the latent vectors in the data set. So really explicitly trying to optimize this function. So we can do this by replacing the density by the kernel density estimation, and we can have this factor. This term at the end is irrelevant from the perspective of the network optimization. So what we end up having is really optimizing this term here. Now there's 2 problems, as you can imagine, because now our network is being used on one side to define the density itself, P, but also to compute the latent embeddings. So there's a simple approach to avoid this, And that's actually to train by using a copy of the network and updating it at a later stage. So there's many different schemes, and we've tried a few, and in general, this works out pretty well. So what happens when you actually use and train a system like this? We did experiments for both OCT, chest X-ray data sets, and MRI sequences, and compared it to typical approaches in this space. So one of them was a deep one-class classification approach, basically projecting the data and then solving an SVM-style one-class classification approach, or then a generative approach called GLOW as a baseline to show how it would compare. These are so-called bidirectional methods or invertible networks. And so in general, it does very well considering corruptions that we manufactured, basically. These are fake corruptions, but a wide range of potential things that could go wrong in imaging. So in general, it does quite well. But perhaps more interestingly is what happens if you try to use a system like this in practice. So here, what I'm showing you is what happens when you take an image, you add noise to it, so you corrupt it more and more, and then you look at the performance of a classification task in this case. So now saying healthy or not healthy for an image, and training that method to do the classification, feeding it images that have increasing amounts of noise to them, and seeing what happens to my performance when you do that. So when you just pass it through the network unimpeded, it's this blue performance. So meaning that as you add noise to your image, unsurprisingly, your network performs poorer and poorer. And so then what these orange and green curves are showing you is what happens if you actually intervened. So in orange, it's showing you that actually if you used this kind of out of distribution detection first, you, to some extent, can't actually detect very marginal amounts of noise, which makes sense. But after a while, you can actually detect them. And that's what this rejection, this other dotted curve is showing you in orange, is the proportion of images that are being now rejected by the out of distribution. So as the noise increases, you're rejecting more and more and more. And after a certain point, you're pretty much rejecting everything. Right? And the green is an analogous one with a slightly different threshold. So the system is rejecting as we hope and able to identify cases it really shouldn't be applying to. Just some qualitative results to show what happens. So in the top left, for instance, we had a real image that's pathological, but this is being predicted originally by rejected as a healthy, but our system is rejecting it. So that's really the case we hope for, in the sense that our system shouldn't be making those kinds of false positive mistakes. And on the right, you have more examples that are in fact analogous. In this case, it's quite clear. You have a part of the image that's just shouldn't actually even be allowed to operate on this kind of imaging. So I'm coming towards the end of my talk, and really I want to highlight 2 points here. First is, on one side, what the last 15 years has told us is that estimating surgical instruments and saying where they are in these video sequences is getting really to the point of being close to integrating into practice. But we have this problem of dealing with those tiny outliers. And when we looked at what those are, we opened a whole can of worms, which is dealing with this out of distribution detection problem in generic ways. And there's a tremendous opportunity to do a lot more very interesting research. We're seeing this in the community, both in the medical image community, but more broadly in the computer vision and machine learning community. And so it's been a very exciting developments over the last few years, which I welcome everyone else to join into that more generally. So with this, I thank you very much for your attention. Some people I'd like to thank who were participating in this. And if there's interest, there are some openings at both postdocs and PhD levels in the group. So if you're interested in joining, feel free to email me.
Okay, thanks for Professor Raphael's excellent presentation. So I will pass over to our audiences. Do you have any questions? Due to the time limited, we can only ask one question. So you can drop your questions in the Q&A, or you can directly drop your questions in the chat box. Okay, Professor, may I ask you a question? Because during your presentation, you mentioned the safeguarding method. I think you just want to make your model trustworthy, because this is for some clinical and medical things. We do not allow any dangerous. Can you give us more details on the safeguarding?
So here it's really about understanding when these methods can fail. And this is related to what's called data shift. So if you train your method on some data set, and now your test data sets or your test cases are slightly shifted in the statistics of your images and so on, how do you ensure that your method can generalize to them? So on one side, you can try to have robust training methods, and that's fine. But the reality is that if you shift too far, those generalization methods will just simply not hold. And so it's important to understand when once you go too far, or that those test cases are just too far from what you're expecting your model to see, how do you even detect them? And so in this sense, there's a lot of safeguarding to do, or data validation or process validation. And I think that's really something that that's an exciting area to look into.
Okay, thank you, Professor. This is a very good answer. I think this mechanism of the safeguarding can be applied to many of our authors, because, like, you know, the theme of this conference is the medical image. Okay, thank you again.
Thank you. Thank you.
Okay, so due to the time, we will move to the next and the last keynote speaker of this session, Dr. Eilert. So Dr. Eilert is a vice president of the research at the Zebra Medical Vision, where she leads a group of AI researchers. Prior to joining Zebra Medical Vision, Eilert led the medical imaging research technology at IBM Research, and led the computer vision and algorithms team at the MODE. So her presentation title is the Deep Learning Solutions for Real-World Healthcare Applications. Okay, welcome.
Thank you for the invitation. It's a pleasure to be here. I will now start the presentation, and you're welcome to ask questions at the end. Hi, it's a pleasure to be here. I'm Ayelet Axelrod-Balin. I'm the VP Research of Zebra Medical Vision, and together with me is Mark Robbins, a computer vision machine learner researcher from our research team. We will discuss today deep learning solutions for real-world healthcare applications. At Zebra Medical Vision, we bring a large, diversified AI medical imaging portfolio with 7 FDA clearances and 10 CE marked products. Our portfolio includes a wide range of modalities and applications, including vertebral compression fractures identification, coronary calcium burden detection, intracranial hemorrhage identification. Also, we have solutions for chest x-rays such as pneumothorax and pleural effusion, and a solution for breast cancer in mammography. We recently expanded our AI capabilities into new healthcare segments such as orthopedics, where we perform 3D reconstructions from 2D x-rays. I will focus today on what it takes to develop such real-world solutions, touching upon the various applications I just mentioned. I will begin with describing the concept of validation as we see it, and then dive into an example of mammography, where I will bring a state-of-the-art comparative study that was recently published, and also demonstrate the excellent results Zebra achieved in this domain. We will also talk about generalization in the context of ICH, where Mark Robbins will present a recent study we performed on generalization in ICH. We then will talk about scaling up with multimodality, combining images and text, and what it takes to make this work. Finally, we will bring example from the population health domain in applications of vertebral compression fractures and coronary calcium burden detection. We will show how we perform large studies in the wild in these applications. So as we all know, deep learning systems have reported to achieve human or even superhuman performance in the computer vision literature. And also in the healthcare domain, we have seminal papers in a broad variety of applications, including skin cancer identification, diabetic retinopathy, cardiovascular risks, and more. Still, when these systems are deployed in the field, their performance is often far below the expectations set by the benchmark in the lab. In other words, we can find a gap between the benchmark lab performance and the real-world field performance. With more and more companies entering this domain, I think it's important to discuss how to make sure that your system will actually achieve the preferable wanted performance from the lab also in the field. Now, one of the important things to consider, in my opinion, is how you perform your validation. Validation is actually not a validation on a specific test set, as one would tend to think about it when you're developing an algorithm. Actually, validation includes, in my opinion, a broad spectrum of components. The first one is to compare yourself to the prior state of the art, both in literature and previous products out there. Another component is to compare yourself to human performing clinicians and radiologists, for example, to make sure that you can augment their work and bring actual value to their workflow. A third component, when you want to regulate your product, is to consider building regulatory acceptable test sets. And these sort of test sets, when you want to, for example, regulate your product in the FDA, should include specific distribution and representation of specific findings and populations. This is not necessarily what is represented in the real world scenario, where you can find lower prevalence of rare findings and so on. And therefore, it is important to test yourself and validate yourself before deploying the product in a wild scenario where you have authentic real world patient data coming from different institutions which you test yourself on. And finally, the most important thing that one should take into account is to fully embed your clinical workflow in an authentic institution out there, where you will actually see the high variability of the screening protocol and see how you adjust to them. You can see how the socio-environment factors impact the model performance and use in the actual field. And today, in the next slide, what I will give is several examples both that we have come across, and also I think there are some interesting ones coming that you can see in the literature. The bottom line, however, is that I think it's important to perform the full spectrum of validation, including the real clinical world validation scenario. Before diving into the specific paper dealing with mammography, I will briefly give some context about breast cancer. So breast cancer is the second leading cause of death from cancer in women. However, it is well known that early detection and treatment can considerably improve the outcome. And therefore, many developed nations have implemented large-scale mammography screening programs, with the US and the UK alone having over 42 million exams performed per year. Still, despite the widespread adaptation of mammography, the interpretation of these images is very challenging. And you can see here a graph taken from Lehman et al., a paper that came out in 2017 in Radiology journal, where you can see the average radiologist performs around 87% sensitivity with 89% specificity. This, first of all, leaves room for improvement. And additionally, you can see that the variability in the performance of radiologists is pretty significant, where you can find that the lower performing radiologists are quite far away from the 87% or 89% specificity sensitivity. Therefore, computer systems have been trying to tackle this problem for more than 2 decades without significant success, until recently the revolution of deep learning has brought algorithms based on CNNs and pipelines that are based on deep learnings and very large data sets, where we can start to see the performance is reaching the level of radiologists. What you can see here is a table listing some of the recent deep learning approaches that have been reported in literature in the last couple of years. The first line includes the Lehman et al. Radiology 2017 paper, which is a study that was performed on a large data set of patients in the US. And you can see the performance of the radiologists that I mentioned earlier for sensitivity and specificity. The rest of the rows correspond to automatic approaches that have been developed in these last 2 years. And you can see here that in the first column, I stated the size of the training data set that was mentioned. And these data sets range from 30K patients in a multi-center data set to 576K exams, which we included in the Zebra Medical Vision when we trained our data set, our approach for the submission to the FDA. Another important parameter is the amount of cancer images, positive images that are included in the data set. And you can see that these numbers are very impressive, given the low prevalence of breast cancer in the population. Also, it is important to know that positivity for this type of application is actually usually based on a biopsy-proven breast cancer that was detected in the images. The third column brings the information of if localization information was included in this pipeline. And actually, this localization or information is obtained by manual detection or annotation of human radiologists of the data. You can see here that the approaches that did include annotated information actually obtained better performance in general. And this is very important since this tagging and annotation is very expensive, especially in the case of breast mammography, which requires specific expertise. Now, what it is important to conclude and note from these studies, the results are very impressive, actually reaching the level of radiologists, but they are studies that were performed in the lab. It is essential to assess which of these results will translate into a good performance in the clinical practice. And this is what this is exactly what the paper of Salim et al. Coming out very recently from JAMA Oncology in 2020 is all about. So the authors here performed the first independent evaluation of 3 commercially available AI algorithms for CAD in the domain of mammography. And their goal was to assess the screening performance when combined with radiologists. All these claims of AI compared and performing on par with radiologists in a specific domain are evaluated now on conditions which are separate from the lab where the studies and researchers and algorithms were trained in, on a new data set, a held out one with a different population, different vendors sometime. And here you can see that the results are actually very good. However, the lowest performing approaches obtained 0.92, while the best performing approaches obtained 0.956 AUC ROC. And an important conclusion, one of the important conclusions that came out in the study was actually the volume of the cases is extremely important, perhaps even more than the diversity of the vendors or the patient population. This is very important to keep in mind when you are performing, when you're creating an approach and you're aiming to being able to generalize well to different types of populations. So you can see here that the lowest performing approaches trained on 6,000 cancer images and 106K normal images, whereas the top performing approaches trained on 72K cancer images taking with 680K normal images. Finally, to conclude the section on mammography, it is important to note some of the important conclusions that can be drawn out from these papers, state-of-the-art papers. First of all, there are commercially available AI CAD algorithms that can assess screening mammograms with sufficient diagnostic performance. Second, combining the first readers with the best algorithm identified more positive cancer cases than combining the first readers with second human readers. These conclusions have significant clinical impact. They lead to the conclusions that for breast screening mammography, the time has actually come to augment a human reader with automatic approaches, automatic algorithms. And in addition to that, it is important to understand what does it take? What does it take to get to this level of performance? And it was noted in the paper, and you can see very clearly that it takes a huge data set, a large multi-center data set. Of course, there are additional factors, including the inclusion of benign findings, the inclusion of localization information. Still, the best performing approaches are the ones that are trained on large data sets. This is what enables them to generalize well. To continue the discussion on generalization, I'm happy to introduce Mark Robbins, which will present our study and results obtained in the different modality of head CT and in the application of ICH.
Hi, everybody. My name is Mark. I'm an algo researcher here at Zebra Medical Vision. And I'll be talking for a few slides about generalization, and specifically generalization in the context of intracranial hemorrhage, or ICH. So, of course, generalization is something that's really important for all of our algorithms, but ICH will just be the context I'm talking about it in today. So just super briefly, I'm not a doctor, so not the best person to go into any details, but the really quick overview is that ICH are brain bleeds. They can take different appearances based on what kind of bleed it is specifically. Here in these 5 images below are images of different types of intracranial hemorrhages. And the important thing to recognize is that for all of these different kinds of bleeds, they can all potentially require immediate intervention. Okay, so what does that mean for us here at Zebra? So this slide is kind of just like a quick overview of what the model pipeline looks like. So here on the top left, you see as soon as the patient undergoes that scan, that full 3D CT volume is then passed into a 3D convolutional neural network, which then classifies this scan as either containing a bleed or not containing a bleed. If it is containing a bleed, a few things happen. First of all, that scan is then reordered on the radiologist work list to be triaged up top so that they can look at this finding the most quickly before other series that are potentially less urgent. The algorithm will also output a key prominent slice where that bleed is most likely to be located, and a heat map on top of where the bleed most likely is to help the radiologist diagnose even more quickly and for them to understand the algorithm output better. Okay, so that's the super quick overview of what ICH is, what intracranial hemorrhage is, and now just kind of a quick overview of what the issue of generalization is. So the question here is, how well does the algorithm generalize to data not seen in training and validation phases? So of course, the setup here is that we at Zebra have our own training data and our validation and testing data to understand the algorithm's performance. But at the end of the day, the important thing isn't how well the algorithm performs in-house, of course, it's how well it performs on new institutions and new settings not seen in training and validation. And so we can ask this question of why do we expect this to potentially be an issue? Why might we be worried that our algorithm may not perform as well, in the real world deployed at new hospitals as it does on our own data? And these are just, there's a bunch of reasons we might be concerned, but here's just a few reasons to highlight. One reason may be different machines and scanner protocols. So, if a new hospital has a different different settings that haven't been seen in training, we may expect that to trip the algorithm up. Different populations and disease distributions, maybe a new hospital has older patients or younger patients, or more of a specific subtype of diseases. And for that reason, our algorithm may, achieve, let's say, a sensitivity and a PPV different than what we report on our own data. And then another possibility are different technicians, maybe with different amounts of training. Maybe the image quality differs from institution to institution. So again, these are just a few, but just to generally motivate why this is something that we should be concerned about. And just to kind of continue to motivate this issue of generalization a little bit more, here's a slide where we ran an experiment. And in this case, we ran on a smaller amount of data than usual and fewer institutions than usual. And we basically trained an algorithm and then we tested it on 4 different institutions that all had the same scanner protocols, across a number of different parameters that we may expect to be especially important. So in this case, each column here, right, is a different institution where we're looking at the same machine brand, the same KVP, the same spacing between slices, the same convolution kernel. So basically in this case, we're kind of controlling for all of those factors that are the most important factors of that first bullet point before of machine and scanner protocol. And what we see here is that there's still a pretty significant variance from institution to institution. So this is, a big enough variance to be outside the 95% confidence interval. And of course, what the source of this variance is potentially difficult to determine. It could be one of those other reasons I mentioned. It could be, something totally unrelated. But just to kind of understand that, this is more, and this is definitely a bigger issue than just having the same machine. There are really a lot of factors at play here. Okay, so if that's what the problem looks like, what do solutions potentially look like? And in this slide here, I'll present an experiment in which we kept the total size of the training set constant, but increased the number of institutions contained in that training set. And this test set is comprised of institutions that are not seen in any of these experiments during training. So all the way here on the left, this number 1 is the case in which all 3,000 series in the training set were taken from one institution, whereas the case on the right, number 4, is the case in which we have 750 samples taken from 4 different institutions. Again, the held out institutions being separate from all of them. And what you see here is a few things, right? Of course, you see a tremendous amount of variance and noise between experiment to experiment. That's certainly important to take account of. You also see generally speaking, an increase in the generalization ability as you increase institutions. And you also see, generally speaking, a decrease in the variance between experiments, especially as you move on to 4 institutions. So I think there's a few things to highlight here, which is 1, the importance of having a diverse training set and, paying attention not only to how much data is in your training set, but how diverse that data is. That's extremely important. And the other thing, of course, to pay attention is that this alone is really not a fix for this kind of concern around generalization. And there's really no substitute for having a super robust feedback loop with the radiologists actually using the algorithm to understand what the performance is like and how they're experiencing it. Thanks.
According to the generalization example presented, the size and the volume of the data are extremely important. However, the well-known challenge in supervised machine learning algorithm is that annotated data is very expensive. This makes approaches that rely on weak labels and weak supervisions coming from radiology reports extremely attractive. Natural language processing focuses on analyzing text and speech to infer meaning from words in such report and is an important ability to scale up. Previous work in this domain, such as TextRay or Chexpert, works that utilized X-ray reports, have relied on rule-based approaches. However, NLP has evolved significantly in the last couple of years. The recent advancement adopting pre-trained language models such as Elmo, BERT, and GPT. The exploration of these models is now reaching the healthcare NLP domain. Transformer models pre-trained on clinical data not only reach state-of-the-art performance on many clinical NLP tasks, but they also help to overcome the shortage in labeled data that is also relevant in NLP. Still, these methods require a lot of time and resources for pre-training, and they suffer from all the problems of black box algorithms. Additionally, there is a big issue with the inter and intra-expert variability. Clinical experts rarely agree with each other. And here I will present an example, a very recent example, or relevant example in the domain of chest CT. An example to demonstrate the concept of noise and ambiguity that one can sometimes find in radiologist report is taken here from the application of COVID-19 detection in CT. So for identifying COVID-19 in CT, one would first look for GGOs, ground glass opacities, that are a descriptor consisting of hazy opacity that for COVID-19 have a specific distribution in the peripheral lower lobes. Additionally, another relevant finding is consolidation, which are a region of normally compressible lung tissue filled with liquid instead of air. Challenging negatives in this case would include bacterial pneumonia or other viral pneumonia, lung nodules, and COPD. So when you want to rely on weak NLP labels, these are the findings that we would look for, and these are the negative cases that we would be careful from. And now let's view this sentence that was found in a relevant radiologist report. Some small areas of more dense opacities are seen in the peripheral right lower lobe. This appears more infectious, inflammatory than mass-like. Looking at the sentence, first of all, it's very vague. It's not clear how much more dense. Can we exclude mass? Can we label this as pneumonia? It is not clear if the exam falls into the positive or the negative bucket. As you can see below, there are two relevant examples or visual examples that you can compare to. This is one exam consisting of the ambiguity challenge that we come across when developing algorithms and when trying to provide ground truth labeling based on NLP. To sum up this point of the ambiguity and noise that can appear in radiologist report, it is apparently well known that radiologists don't necessarily always commit to findings in the reports, and a lot has been said about radiologists and hedging. Still, utilizing radiologist report is extremely valuable, and utilizing NLP algorithms and weak labels is extremely valuable for generating larger data sets, improving your performance, improving the ability to generalize to data sets in the field and in the wild. It is just important to keep in mind the effect of this noise and to carefully analyze it. And there are, of course, many solutions for it, such as label cleaning, data reweighting, curriculum learning, and so on. An interesting example in this context is our work on osteoporosis and vertebral compression fractures. The annual incidence of osteoporotic fractures in the US is higher than the incidence of breast cancer, heart attack, and stroke combined. The most common osteoporotic fractures are those which are called vertebral compression fractures. In addition to being a source of morbidity, VCFs indicate substantially risk of future osteoporotic hip fractures. 1 in 2 women and 1 in 4 men over the age of 50 will suffer from an osteoporosis-related fragility fracture. Over 50% of hip fractures are preceded by a vertebral compression fracture, serving as an early warning sign of increased fracture risk. Yet despite the burden of this disease in an aging population, osteoporosis screening remains profoundly underutilized. Treatment of osteoporosis are widely available, evidence-based, and cost-effective, but a considerable diagnostic gap exists to identify patients at risks of fractures. There is therefore clinical value for identification of incidental VCFs on CTs as a predictor for future osteoporotic fractures. We have developed an automated VCF solution based on neural networks trained on a large dataset indexed according to the Gennard classification. The device was validated against previously unseen dataset, achieving high performance at detecting moderate or severe vertebral compression fractures, and received FDA and CE approval. You can see here highlighted in yellow 2 examples. One is the case of a 78-year-old male where you can see severe VCF, which is a true positive. On the right, you can see an 83-year-old female. Again, here you can see multiple compression fractures and schmorals. In addition to the type of validation with an unseen data set approved by the FDA, we have performed several studies in the wild. We have seen similar potential for the opportunistic screening model in another large-scale study we published in Nature Medicine earlier this year, wherein close to 50,000 patients followed up for 5 years, CT biomarkers improved the AUC for predicting actual fracture events when compared to utilizing the FRAX alone. In order to further validate the potential clinical impact of this device, we applied the device to over 76,000 chest or abdominal CT scans from the US and reviewed the original radiology report through combinations of human review and NLP. This established the baseline rates of VCF reporting. The device demonstrated a 138% increase in detection of moderate or severe VCFs from the established baseline. The visual sub-analysis of the CTs verified the algorithmic performance and revealed the high NPV and moderate PPV, which you can see here in the slide denoted in yellow. However, review of the false positives showed a large majority to contain mild vertebral compression fractures, which were classified as negative for this study, still conferring clinical value. And this is also denoted here in yellow. The VCFs were identified in 6.6% of the 76,000 radiology reports. The algorithm obtained a similar performance. Therefore, we conclude that there is a clinical value for identification of incidental VCFs on CTs as a predictor of future osteoporosis fractures, and that the device can perform and do this automatically. Another interesting example, also in the domain of population health, to which we have been applying large-scale studies, is the problem of coronary artery calcium burden identification. Cardiovascular disease is the most common preventable cause of death, accounting for up to 45% of the mortality in Europe and 30% in the US. Effective lifestyle and pharmacological prevention is available, but identifying those who would benefit most is an ongoing challenge. Coronary artery disease accounts for 50% of all the cardiovascular-related deaths, making coronary calcium a powerful predictive biomarker for cardiovascular disease. Coronary calcium has been traditionally quantified using dedicated ECG-gated cardiac CTs. However, cardiac-gated CTs are dedicated studies and are typically used to visualize the heart. Thus, this cohort of patients are already under investigation for cardiovascular disease as opposed to non-cardiac gated CTs that are being performed for many indications to which we have been developing our new device. Therefore, we developed a deep learning-based system to detect and classify coronary artery calcium burden on non-cardiac gated CT scans. The system was trained on a large cohort of patients with coronary calcium lesions and classified patients into mild, moderate, or severe coronary calcium burden based on a scoring similar to the traditional Agatston systems. The device showed great performance results with high overall agreement between the established ground truth and the device itself. As you can see here, the flowchart of the system includes several steps. First, the input is a non-gated, non-contrast chest CT. Then we perform heart localization and automatically segment the coronary calcium. After that, we compute the coronary artery calcium score similar to the Agatston system. And finally, we produce an output with an annotation of the finding, as you've seen in the previous slide. We further took this device and applied it to 20,000 routinely acquired non-gated, non-contrast CT examinations. The radiology report of these same CTs were reviewed for documentation of coronary calcium, and we compared the algorithmic results with these reporting. What was interesting to see that the actual frequency of writing reference for coronary calcium was remarkably low in all categories, measuring just 5% even in individuals with high coronary calcium score above 400. This is an example of the use of automatic quantification system that has a huge potential to capture opportunistic cardiovascular scanning in routine CT chest imaging and guide more patients into appropriate care and treatment. To sum up some of the takeaways from today's talk. First, for deep learning algorithms to bring real value to healthcare, they must go through a spectrum of validation. Most importantly, they must be validated in the real clinical workflow. Second, in the breast screening domain, we went through various state-of-the-art papers. It is clear from all of them that the time has come for AI augmentation of the radiologist in mammography screening. Third, in terms of generalization, both the mammography literature and our own ICH research demonstrated that the volume of the data and its variability are the most critical factors to promise good generalization in the field. When developing generalization approaches, it is very important to take into account that the source, the target, and the supervisions are not always available simultaneously. When increasing volumes and scaling up with multimodal algorithms and weak labels, additionally, we presented two examples in the population health domain. We presented large-scale studies evaluating automated VCF identification of incidental VCFs in CTs and automatic coronary calcium quantification software that can serve to capture opportunistic screening for cardiovascular risk in routine CT chest imaging. Both these types of applications have a huge potential impact to guide patients to appropriate and better care. Our work at Zebra Medical Vision is dedicated to bring genuine impact to real-world healthcare. Finally, I wish to thank the entire Zebra Medical Vision team that makes all of these results and projects become possible, and especially to the exceptional research team for transforming healthcare with AI to bring better care with real-world solutions.
Okay, thanks for the excellent presentation from Dr. Eilert. So I will pass over to our audience. Suppose if you have any comments or questions, please drop those comments and questions in our Q&A and the chat box. So we may have only one question. Yeah. Okay, Professor, may I ask you a question? So in your presentation, you said that generalization, I think this can be like generalize your AI model to new test images. My question is, have you ever tried like your model in the clinical situations?
Yeah, so the examples that I presented at the last, at the end of the presentation, demonstrating both two applications for population health are a good example of very large studies that we performed in large HMOs, in hospitals that contain many institutions that were not trained upon. And the idea was to demonstrate the ability of a system that was trained on a large data set in-house, tested in-house, first in the wild, then embedded in a real clinical workflow, and tested in the wild, and being able to generalize well in that scenario. So that was the aim of bringing those examples.
Okay, thank you, Dr. Eilert. This is an excellent answer. I think your method will definitely help other researchers in their future works. Okay, thank you again.
Thank you.
I will pass over to Dora. Okay, Dora?
Yes, okay, thank you, Professor John. And now we will begin our oral session. And it's my pleasure to invite our chair of the session 1, Professor Su Ren, from a laboratory RITIS, University of Rouen, France. Okay, let's welcome Professor Su.
Hello.
Yes.
Hello, everybody. Excuse me. Okay. Okay. So my name is Su Huan. I'm a professor at the University of Rouen, Normandy in France. I'm working with the laboratory Yeast, University of Rouen, Normandy in France. So this is my website, the website of our laboratory. So it's my pleasure today to chair this oral session. Normally we have 5 presentations, but maybe the first one, the Orlando Bello is not present. We can.
Sorry, Professor Orlando Bello is not here. I'm going to
present.
present.
Okay. Oh, thank you. Okay, so you are present. Okay. So we have about 10 minutes for the presentation, so we can start by the session by the first presentation from Orlando Bello, coming from the University of Minho, Portugal. So you have 10 minutes to present your work, and can you share your screen?
Yes, let me share. Oh, I can't because you're sharing your screen.
Okay. I should do. Okay.
Okay, thank you. Are you seeing right now?
Yes.
Okay. So the work I'm going to present, promoting cardiovascular health using a recommendation system, was developed by me and Eduardo and Professor Orlando Bello. We are from the University of Minho in Portugal. In a brief way, the work we developed is about a construction of a recommendation system capable of suggesting a 30-day plan for food and exercise that aims to improve cardiovascular health. In this presentation, I'm going to start to make a brief introduction. Then I will summarize the main motivations and the objectives of our work. And after that, I will talk about cardiac well-being indexes. I will show how the cases were represented and describe the main steps of our work. In this phase, I will describe each of the stages of the CBR cycle that we followed. And at the end, I will talk a little about the program that we created. And then I will present the main conclusions and some possible future work. So in our daily routine, we are constantly testing our decision-making ability and making choices. And these choices tend to be repeated every day and define our lifestyle, which is directly linked with our well-being and our health, particularly cardiovascular health. Although most people are already aware of the importance of healthy lifestyle habits, only a few are able to incorporate habits into their daily routines. Due to the lack of time and motivation, many of the choices that we make are not the result of thoughtful decisions, and consequently, they are not healthy, especially those related to diet and to physical activity. Planning every day what to eat and what physical exercises to do requires a lot of effort. When it comes to food, for example, it is not always easy to think of new recipes that are healthy and tasty at the same time. To make the best decisions, it is necessary to have the ability to conciliate the personal tastes of each one with the best options for cardiovascular health. This planning is not a simple task and requires 4 fundamental aspects: time to exercise and eventually healthy meals, knowledge to know the healthiest options for each person, creativity to think about new physical activities and recipes, and motivation to stay focused on the main objective of following a healthy lifestyle. One of the ways to simplify this task can be through the creation of a food and physical exercise recommendation system. Knowing which healthiest choices are is not a linear process and depends on multiple variables. Despite being a well-studied area, there are still many uncertainties involved. Therefore, to implement a recommendation system, we have chosen to follow a case-based reasoning approach because it is suitable for solving complex problems and it is very focused on real-world systems. Thus, the aim of our work was to implement a recommendation system based on a CBR approach that guides its users towards a healthier lifestyle. The system was developed based on a diet and exercise recommendation plan to be followed for 30 days. To do this, we use databases to store cases. We built an ontology and defined some SWRL rules to structure the existing knowledge in nutrition and exercise. And we also created, in the end, an application to interact with the users. So before starting the implementation, we thought about a way to evaluate the success of the recommendations. In the literature, we found that most recommendation systems in this area do this type of evaluation by specialists or even by the users themselves. But we decided to create a metric, the cardiac well-being indexes, to avoid external validation of the system. These indexes consider the characteristics of each person and allow to measure in the form of a numerical value the cardiovascular health status of the individuals. Thus, in order to assess the success of the recommendations, we measure the index before and after the fulfillment of each plan. So if the value improves, the recommendation can be considered successful. After defining the evaluation metric, we represented the cases considering 4 different components for each one: a description, a justification, a solution, and the results. And then we store them in a relational database. The first stage of the CBR cycle is retrieve. In this step, we use the k-nearest neighbor algorithm to return the most similar cases, and we here included a threshold that defines a minimum similarity for a case to be returned. After that, we considered 2 possible scenarios. A first scenario in which no cases are returned, and a second scenario in which there are cases returned. For the first situation, we defined cold start rules that must be applied in order to obtain recommendations. And in a second situation, we defined a score function that takes into account the values of similarity, index variation, and degree of success. And the best case corresponds to the case with the highest value, with the highest score. So in the next stage, we adapt the solution using an ontology that we built. In the specific case of dietary recommendations, the first step is to return from the ontologies all the menus that respect the necessary calories for each meal. Then we retrieved the menus that users cannot eat because of their food allergies, intolerances, or diet. For example, a gluten intolerant user cannot consume menus that contain gluten, or a vegetarian cannot consume menus that contain meat. In the next step, we filter the menus that the users can eat. That is the menus from step 1 that are not specified in step 2. If we are in a cold start situation, we need to see which of the menus respect the cold start rules. And if we are in a best case situation, we calculate the nutritional similarity between the best case and the return menus, and we remove the menus that do not have a high similarity. To know which menus should be recommended, we also calculate the similarity between the menus in the previous step and the user's preferences. The 3 menus with the highest value for each meal are recommended, so that the user can choose one of them. The menu chosen by the user corresponds to the system's recommendation. For physical activities, we followed a similar methodology. Although the recommendations are based on successful past cases, there is no guarantee that they will be successful. Thus, after the end of each plan, we need to analyze the success of the recommendation. To do this, we calculate the variation of the cardiovascular well-being index, and if it is positive, we add 1 unit to the number of successful cases, and if it is negative, we add 1 unit to the number of failures. We also need to confirm if the solution of the new case is identical to the solution of the best case. And in this case, we should analyze if the case should be maintained in the case base or not. For this, we calculate the degree of success, and if it reaches a low value, we remove the case from the case base. If the solution is similar and the degree of success is high, the case base values are updated, and if solution is obtained by cold start rules or is significantly different from the solution of the best case, we insert a case as a new case in the case base. Here we have the application we developed using Java FX. As an example, in this slide, we can see 3 options for each meal of the day, and the user must choose one of the options. To conclude, here we have the main conclusions of our work. The system we have built acts as a recommendation system in the area of diet and exercise and follows a CBR approach. The metric for evaluating success is through well-being indexes, and therefore no human intervention is required. Structuring the consolidated knowledge in an ontology allows easy adaptation of the cases, and we created a system capable of simplifying daily decisions and promoting the adoption of healthier habits. As future work, it will be interesting to test the effectiveness of the system using all data, consider remote communication and security issues. For making recommendations about food, it would be interesting to include the quantities of each ingredient in the recommendation and allow different workouts in the same exercise recommendation would be interesting too. So thank you for your attention.
Thank you. Thank you for your presentation. And any questions from the audience? No question. Oh, so I have just a small question. So you use k-means to classify your data. So I mean, what value, what k-value that you choose, because k-value can influence the results. So can you tell us how to choose this?
We only 10 for the k-value because we confess we use K-nearest algorithm, and because it is the more used algorithm in this type of works, and we only choose a key value of 10 because we already saw that that value be okay.
Can we choose this value in your software? When you show your software, can we choose this value, or it's fixed?
No, we use as a basis J-Colibri for do that. So we use the K nearest neighbor from J-Colibri, and the K value is for default 10. I think so.
Okay, thank you.
Thank you.
Any other questions? So we can move to the next presentation. The speaker is Michael Novikov.
Okay. Sound is okay?
Hello. So he's come from the Moscow, Russia, and working for the research center, crystallography and photonics. His research focused on information technology in medicine. So you can share your presentation.
Okay.
I don't know, maybe I should cut.
Okay.
No, not just a part of your presentation. No, I cannot see complete your presentation.
Not working. Sorry.
Or maybe I can play the slides for you.
Okay.
Okay.
Wait, that's okay.
Okay, thank you. Sorry. Your next slide, okay? I'm pleased to present of this conference the practical work in the field of medicine made by our group together with the Dr. Sergei Tereshchuk of Burdenko Brain Clinical Hospital, the city of Moscow. I am city Shatura from 120 kilometers from Moscow. Next. Excuse me. You maybe next slide. Thank you. The development of new materials and technology for manufacturing products from them for the replacement and regeneration of tissue and organs is one of priority trends in modern biomedicine. The success of the clinical application of biomaterials requires that their shape, structure, and mechanical characteristic correspond to real fragment of the body. The production of individual model and implant. A high quality implant for tissue replacement regeneration is a prime example of single product. Traditional methods use filling compound technology, injection molding, manual machining. A new approach computer modeling and simulation, additive manufacturing technology. Next, please. Use special computer program in surgery. Program for processing tomography data and building digital models. These models produce in SCTL format file. Programs for three-dimensional modeling, Magic, Trimatic, MICAD, and use CTL format file. Please, next. Next slide. Advantage for using digital models in surgery: individual approach, comfortable 3D representation of the tomographic data, computer modeling capabilities, additional information for the doctor and patient, possibility of use in additive manufacturing, planning in conduction trial operation, production of mold for individual implants, training tool. Additive technology, computer modeling, and maxillofacial surgery. The first item of experimental construction of the lower jaw using a vascularized rib were made in the 2080s. Use special door site. The simple anatomy, the fibula led to the popularity of this flap in the reconstruction of the lower jaw. The first examination of patient and the beginning of planning the operation for the removal and reconstruction of fragment of the lower jaw was carried out in Burdenkamen Clinical Hospital, Moscow. The patient was examined on a computer tomograph. The middle zone of face gave a step of 0.4 millimeters. The fibula with a step of 0.8 millimeters. Next slide. Thank you. Process computer data and creating digital model. First step, tomograph processing, noise clear removal. Next step, virtual separation of upper and lower jaw. Next step, converting graphical data tomography of digital 3D models. Next step, virtual resection of the patients is lower jaw during the online conference between Iplit Ras and the hospital. You remove main task and determine size of the bone defect. Determine correct cut on plane for remove bone defect. Next slide. Planning the position of fibula with a living blood vessel of the patient's lower jaw. Create a model of fibula and reconstruction. Lower jaw. Condition for the correction position of the graft. Next slide. This virtual final version of the bite in comparison with the resection fragment of the lower jaw of the patient. Modeling manufacturing compliance for precision resections. Special shabloon for operation. Produce the stereolithography setup. The positive result of operation depends on exact location, the direction of the receptors of the lower and fibula. To meet this condition, individual plastic plates with a good plane and holes for fasteners and designed in manufacturing. Next slide. A serigraphy model used for reality fit the fasteners. We use it in next operation. The course of operation reconstruction lower jaw. Next slide. The result of operation. Totally 112 patients with maxillary defect underwent reconstruction surgery using computer modeling and laser stereotography in the Budenka Main Military Clinic Hospital by Dr. Sergei Tereshchuk. Next slide. Conclusion. Advantage of using case technology in reconstruction surgery. Reduces the time of operation due to the online planning of the operation and the fitting fastering of the plastic model, and as a result increasing the chance of successful outcome of the operation. Increase the accuracy of machine craft with original contour of the jaw. Increase the accuracy of the alignment of the graft and jaw planes to be joined. Restoration of the full functionality during dental row implantation. Further development used additive technology. Additive technology makes it possible to directly reproduce a model of almost any fragment of the human skeleton based on CT MRI data. Additive technology will make it possible in the future to create ceramic polymers and composite matrix for tissue engineering and individual implants of a given shape and structure. Next slide. Thank you for your attention.
Thank you for your presentation. And any questions? No. So I just want to know when you do your reconstruction for the face, for example, you need to pre-process the images. So is it important for you to have a good result of pre-process? That means give you a good point to do the reconstruction, or you have some other processing states to filter or to clear the data.
Oh, okay, you.
I just know if pre-processing states are important for you to reconstruction.
Percent the payment on the stereography model. You can.
Hello? Oh, I cannot hear you. Hello? Ah, we lost him. Hello? Can you hear me?
Yes, Dr. So you're audible. I think we lost Dr. Michael.
So maybe we can move to the next presentation.
Yes.
Next presentation. So next presentation. So the speaker is Sayun Kahamaha, coming from the University of Arkansas at Little Rock. So can you share your screen?
Yes, I will. let me know once it's visible.
Okay, we can see your presentation.
Is it visible in the slideshow mode?
Yes. Okay.
Okay.
Good.
Okay, then I'll start my presentation. So I welcome you all. And my name is Sayan Karmakar, and with my co-author, Dr. Shishadri Mohan. Actually, my paper is on machine learning based imaging in connected vehicles environment, and it's actually a new area of research and where medical imaging plays a very important role. And currently I am a doctoral scholar at the University of Arkansas at Rock, and simultaneously carrying out my master's at NIT Sikkim in India. So the contents of this presentation would be, since we have seen a lot of literature on the medical imaging, I would straight away start my presentation on the connected vehicles and how this is connected with the medical imaging, followed by the challenges, and how machine learning helps us in like tackling those challenges, followed by conclusion, references, and research team with acknowledgement. So I would like to introduce what actually connected vehicles is. It is actually a concept where the vehicles are communicating, like there is intravehicular communication, and there is communication of vehicle with base station in order to pass on safety messages and their current location and many much metrics rather than the location. So there's one video, very small short video I would like to share you so that it actually gives a visual understanding as to how this connected vehicles is, or what connected vehicles is. Sorry.
Imagine a future where vehicles talk to one another and to critical infrastructure. This connected vehicle technology can change our transportation system as we know it by enabling safe, interoperable, networked wireless communications among vehicles, infrastructure, and personal communications devices. Connected vehicles provide drivers with 360-degree awareness of similarly equipped vehicles within a range of approximately 300 meters. This secure system keeps personal information private and does not track your vehicle. Drivers will receive warnings that inform them of potential hazards through a visual display, seat vibration, or tone. These are only warnings. The driver remains in control of the vehicle at all times.
So what you just saw is just basically in a nutshell that how why the concept of connected vehicles came up, and the safety is the first priority and the utmost priority given in the connected vehicles domain as to why this concept came up. And now this slides that you are going to see right now, it would basically help you in establishing the bridge between connected vehicles, that is a completely technical communication and vehicle dynamics based research into the medical imaging. So this is actually a very small research work that we are carrying out. And so we actually helped in identifying, me and Dr. Seshadri Mohan actually helped in identifying the non-invasive biomarkers as to which biomarkers are specifically can be assessed in order to assess the mental health, cognitive health, and and all the kind of health present in the drivers. So this basically helps you in and establish this research work that in the current slide you're seeing. It's a research work being published in NCBGICT. So you can find there, and pertaining and extending this research work, this video would actually help you understand what driver monitoring system is and how the medical imaging would be actually helpful in integrating with the health of the drivers and integrating with the safety of the vehicles on the road itself, as well as extended this work to like device based approach. So this is a video. Have a look at it. So on the right side that you are seeing, it is ADAS, that is Advanced Driver Assistance System.
Please fasten your
And on the left side that you are seeing, it is DMS, that stands for Driver Monitoring System. And if you can see the metrics on the left side on the DMS, you see what are the metrics. The eyelid openness of the left eye and right eye. And then you have head pose with their roll, pitch and yaw and XYZ coordinates. Now there are specific biomarkers that have shown significant results, which upon the statistics of eye closing and eye opening can detect multiple cognitive health and mental health and the chronic health of a person, of the driver. And what we aim right now is to integrate this DMS with ADAS, specifically keeping center the driver.
Please keep focused. No drinking. No smoking.
So you see how the vehicular automation and medical imaging forms a bridge, and this video should give you a glimpse of what this bridge is actually. Now, under clinical setting, the imaging is very difficult in itself, and but in consideration of feasibility, when you are carrying out this imaging under real-time condition in a dynamic environment, the challenge, there are new set of challenges that I'll be telling you in a bit detail. So the first challenge that you see is the changing luminescence. So under changing luminescence, what problem would be facing by these system is there is actually the direct correlation of luminescence with the time of the day, month of the year, and weather and the road demography. That is, whenever you are approaching in a tunnel. So the changing luminescence and the changing lighting condition creates actually a very chances of false detection of facial cues, because what we are trying to do in the biomarkers paper, in the like we are trying to assess all the biomarkers of the facial biomarkers, and then we are trying to assess the health of the driver. So obviously you would place a camera in the vicinity of the drivers in order to assess. So what would be the challenges like in the imaging? So the changing luminescence is one. The second is mechanical vibrations. Once you keeping the camera on the dashboards itself, the road vibrations, that when a vehicle passes on an uneven road, those vibrations are carried on to the camera, and then it would basically reduce the image clarity, and there is a very high chance of losses of like data on the facial cues, because we are actually tracking the micro expressions. Then the camera's field of view is very essential, is like wider is the viewing angle, more data can be captured. But then again, what problem is that the driver is in a very dynamic place. So the driver itself is moving. So the camera that is detecting that is acquiring the image should have a large field of view in order to accommodate the person whenever it is moving. So these are some of the like very challenging tasks. And then you have the resolution. Like it is actually an intrinsic factor of the camera itself, but higher is the resolution, more accurate are the details. So but the problem is higher resolution would generate a very large amount of data, and then actually you would have to do a trade-off between the resolution and the data volume. So then you have the sharpness of the image. So and it is actually the details of the images that are captured, but it is not same as resolution. It is very mistakenly, very commonly interchanged with resolution. So the sharpness basically would help in medical diagnosis, and based on the facial cues actually requires good detailed image. And the capacity to capture the micro expression plays a very crucial role. And that is actually because it is the essential factor in finding the coherence, the clinical coherence to the images, that to the medical images. And then you have a focusing issue in the camera itself. So you have to keep the driver in focus, driver spaces in focus in order to acquire the proper facial cues. And then you have a tendency of pixelation. So if the if the camera of like low lighting imaging, low light cameras are not proper, like under low lighting, the cameras tend to pixelate a lot. So the selection of camera plays a very important role in this. And then light exposure directly on the camera. So suppose the camera like you have a camera on the dashboard and there's some external light that is falling on the camera itself. So it won't be able to capture the driver space. So essentially it is actually the placement of the camera plays a very crucial role. So how machine learning can be used in this connected vehicle environment? The first thing is by addressing the mechanical vibrations. So the blurriness in the images can be removed. There are research, basically it has been taken from the gimbal system of the camera. So where the estimation of the motion of the camera is estimated, and then it is been compensated for the image. And then you have video stabilization using convolutional neural network. Then you have L1 norm optimization for synthesizing a part consistent of simple cinematographic motions. So these are some ways to encounter mechanical vibrations. Then you have the facial detection that is very essential in order to keep the driver space in the center and keep it as a region of interest. Then numerous papers are there that use SVM support vector machines. Then you have recurrent neural networks, region-based neural networks, and then we have convolutional neural networks. You have multiple machine learning based papers and practical examples for facial detection, and followed by changing luminescence. Now there has been research where this changing luminescence has been tackled artificially without the adding of noise. And then again, there has been significant work done in the light correction using deep learning methods. So these things that I'm speaking right now, you can find the references in the later part of the stage. And then you have the image correction techniques using TensorFlow, CNN-based UNet architecture. Then Duke University actually developed a method called Pulse that uses self-supervised generative models for image correction. So basically, in a nutshell, how I would conclude this, that the connected vehicle paradigm is experiencing a pragmatic shift by the inclusion of drivers for critical decision-making process, as well as automating the driving experience to a driverless automation. And then you have imaging under the dynamic condition that is very challenging, extremely challenging itself. So what would be like this paper actually addresses the challenges that you would face while while imaging under the CVE, and how these intelligent algorithms actually help us in tackling them and resolving them and finding us, giving us a pathway to to resolve them and help us in directing the research to a better position. So these are the references. I took 15 minutes. I'm sorry, I took 15 minutes, but these are the references, some of the references that I've used in my papers. and this is our research team, a very small research team at University of Arkansas Little Rock. And this is the acknowledgement. I would acknowledge my research work to them. And thank you. Over to you, Dr. Su. And if you have any questions, please feel free to ask me.
Thank you. Thank you for your presentation. So someone give you a message. Very interesting topic. Thank you.
Oh, thank you so much. So if you have any questions, Dr. Su, over to you. And if you have any questions, you can email me. I've given it to you. Okay, we have one question. So you have in my email ID in the chat box. You can definitely email me. How expensive is the use of these techniques in vehicles in terms of computational cost? What kind of hardware do you need? Okay. So the answer to your first question is the expensive. Now this factor is actually depending upon the cameras. So you have, like in a commercial aspect, you would have to take care of the camera, and then you have to take care of the onboard computer that would basically serve as a node and a data acquisition system. The entire computational works that we are doing, it would be actually a cloud-based. Now, my professor, Dr. Seshadri Mohan, he is in the field of 5G and 6G, like he's been in the field of communication systems. So what we would do is under 5G and under the 6G communication, we would straight away take all the data and upload to the cloud. And it would basically take less than 2 milliseconds and then process all the data on a server and then download it. And what kind of hardware do you need? The hardware is basically a data acquisition system, a camera, and then a good network receptive communication system within the vehicle itself. So this is how I would like to answer. For more details, we can always collaborate on email. Thank you, Doctor, and thank you for your question. Over to you, Dr. Su.
Okay, thank you. So thank you again. Now we move to the next presentation. The speaker is Jingwei Long, coming from the Hefei Institute of Physical Science, Chinese Academy of Sciences. Please, you can share your presentation.
Can anybody hear me?
Yeah, but we cannot see your presentation. Can you share it?
I'll share it right now.
Yes, we can see it.
Now I will begin. Good morning, everyone. My name is Lang Jingwei. I'm a PhD student at Hebei Institute of Physical Sciences, Chinese Academy of Science. What I'm going to present is actually still on its early stage, but I really think our findings so far are worth telling you. The topic of my talk is about how predicting neurostimulation responsiveness with dynamic brain network matters. I will begin my presentation according to the following outline. First, reintroduce. So first, I'd like to give you a bit of background. When we talk about the non-invasive brain stimulation methods, one of the famous is TDCS. TDCS has great potential in clinical, such as improving neurocognitive performance in people with neurological and mental disorders. In addition, the widespread use of TDCS also benefits from its low cost and minimal side effect. But however, the TDCS also notices that the neurostimulation responsiveness from TDCS varied hugely among participants. Our previous work demonstrates that the necessary of pre-stimulation screen by showing that people receiving stimulation could be classified into two heterogeneous groups, the positive responders and the negative responders. The positive responders whose performance was improved by TDCS and the negative responders whose performance was impaired. The neurostimulation responsiveness was predicted by functional lateralization index, which calculated from task-based fMRI, but it might not be suitable for patient. Resting state fMRI contains rich patterns of brain activity, which can be quantified with graph theory and network science, such as dynamic functional connectivity measures. Compared with static manners and dynamic manners. Dynamic manners can indicate the flexibility reorganization of brain networks, which might be more useful to predict brain heterogeneity. And also, recent studies spotted DFC measures as powerful neuroimaging markers of neurological and mental disorders. Now, let me move to the schema overview of our method used in this research. It contains 5 steps. Step A, extract the time series strategy. We divided the complete time series into sub-windows through a strategy of sliding window. Step C, detection of dynamic communities through a maximum multi-layer community network algorithm. Step D, calculate the dynamic properties of all nodes in the systems. Step E, the last step, predict neurostimulation responsiveness by several machine learning models. The dataset used in our research contains of 45 young adults, and we can classify the total participants into 2 groups: 28 negative responders and 70 positive responders. Our dataset in the right side, the DM network was selected as our region of interest because it's closely related to the TPJ stimulation effect. The default mode network was classified into 3 subsystems: a dorsal medial prefrontal cortex subsystem, a medial temporal lobe subsystem that contributes to memory-based sense construction, and a set of midline cohorts that are especially involved in processing self-referential information. For the ROI templates, we created sphere ROIs using the MNI coordinates listed in this table at the right side, with the diameter of 10 millimeters. Here you can see we distinguish 3 different default model network subsystems with both of 3 different colors. What I want to highlight is the dynamic community detection method in this slide. We applied the Loban algorithm to the series of ROI correlations metrics calculated at the same length to detect network communities. In addition, I want to emphasize that we use gamma equal to 1 and omega equals to 0.4 for balance between community numbers and node flexibility. In this slide, you can see in our research, we take 4 features to the dynamic network statistics. On the top left, the recruitment feature is obtained by calculating the probability that the nodes within the same subsystems are sent to the same community, which reflects the interaction of regions within subsystem. On the bottom left, the integration feature is obtained by calculating the probability that the nodes within the different subsystems are sent to the same community, which reflects the interaction of regions across subsystems. On the right side, we will see that the nodes are constantly switching from community to community throughout the whole time series. So we can calculate flexibility as the probability that nodes change its community allocation within the continuous time window. And the promiscuity is used to measure whether a node participates in all possible communities. In this slide, I will show you some of our main results. First, we can find that there are several significant differences on bilateral AMPFC, PCC, PSR, RSP, and PHC for the recruitment dynamic feature in different groups of window length and step size. Second, we compared the effectiveness of dynamic and static network matters in identifying positive responders from negative responders. 5 different machine learning algorithms was selected as shown in the table. For each algorithm, we compared the prediction accuracy for the model using static methods alone, using DFC methods, and using the combination of them, of both. We are convinced that our results show that the advantages of DFC over static network methods was manifested by all 5 modeling approaches, but the model based on decision tree yield inconsistent findings because the decision tree model is only used a small number of trees in classification task, and it might be vulnerable to overfitting. Moreover, we calculated the ranking of features importance in the case of all features mixed and found that among the top 5 features, dynamic features accounted for 4 when applied neural network model. Similarly, results have been seen have been produced by other machine learning models. Then I'll come to my conclusion and discussion. The results suggested that the positive responders different from negative responders in this core and MTL subsystems on recruitment. DFC alone shows advantage over static networks measures by several learning algorithms. For discussion, the dynamic community analysis can comprehensively consider the rapid interaction among nodes and subsystems. And also, the decision tree model might be vulnerable to overfitting because our sample size is small. Last, our study explores the feasibility of pre-simulation screen program using DFC methods from resting state fMRI. This is an acknowledgement to all our members in my library, and also thanks to the USPC, IHMT, and Science Island. Well, thanks for your attention.
Thank you for your presentation. So we have a question. Can you see the question?
Wait a minute.
Yeah, what do you think that the combination of dynamic and static strategies has a lower performance than the dynamic version?
Because in this research, we use the static methods are too many than dynamic methods. Because we use the all node and we use the balance between the dynamic and the static methods are not balanced. So the combination of dynamic and static strategies has a lower performance than the dynamic version. And we will further to discuss it in the future work. Thanks.
Okay. Okay, another question. So we can move the last presentation. So the last presentation, the speaker is Janine Clément, coming from the GE Healthcare in France.
So good afternoon, everyone. So I'm Luc Cazeles. I'm going to replace Clément for this presentation, or in particular the Q&A session. So we have recorded the presentation, so let me share it.
Okay.
Good morning, good afternoon. My name is Clément Gélin, and this talk for MICAD 2021 is about a data augmentation technique for breast mass segmentation. So, what is data augmentation? Data augmentation is a way to increase the dataset by adding some slight modification of the existing data.
We cannot
data
see
from the
all the
existing.
slide.
You cannot see it? Okay. Oh, that's very strange.
Actually, I see it.
Just a half your presentation.
You see it now correctly?
Not really.
Okay, that's.
I can see the full screen.
You can see. Oh, maybe
Yeah.
it's my problem. So you go ahead. Go ahead.
Okay.
For breast mass segmentation. So, what is data augmentation? Data augmentation is a way to increase the dataset by adding some slight modification of the existing data, or by creating synthetic data from the existing dataset. A standard way to perform data augmentation is classical data augmentation, often composed of geometrical transforms, for example, rigid body motion, elastic deformation, flips, shear, etc., and or intensity modifications, global brightness and contrast changes. You can change the colors, you can add some noise, etc. All those transformation fields aims to create some equivariance or invariance in the model. However, it may add some limited variability in the training dataset, and it could even introduce some bias. You can easily think of a 6-9 classification biased by a flip. So here in our application, we would like to have a perfectly realistic transformation field. How to have a perfectly realistic data augmentation? Well, if a patient were to take multiple exams in the same day, the intensity variations that we would see on the different images would be composed of geometrical transforms, change in the breast position, and intensity variation, because the acquisition system may be different, because the acquisition parameters may be different. However, all those acquired data should not affect the final diagnostic. So we want our model to be invariant to all those transforms. But we do not have access to a dataset composed of a patient taking multiple exams. We have access to the full history of patients in time. Here is an example. You have one breast with 5 different acquisitions. And between the different acquisitions, you can see some intensity variations and geometrical transforms. So we will study all the history of patients we have in our screening dataset and design a realistic transformation model. This is the first part of this talk, how to design a breast transformation model. The first part is to extract all the transformation fields. This is performed through a registration procedure that is able to extract both the geometrical transforms and the intensity transforms. So on the left part of the slide, you have the measured kinematics and the measured intensity fields for 3 different breasts. So we performed this registration on our entire dataset composed of 583 patients with priors each time. So we extracted 583 fields for the MLO configuration and 583 fields for the CC configuration, MLO and CC being 2 different views in mammography. They are treated independently. So it's a lot of fields. So we decided to reduce it in a principal component analysis reduction technique in order to have a reduced transformation model. This reduced transformation model is composed of space components, patient components, and eigenvalues. We will first start with the space components. Here on this slide, you have 4 components of the displacement field in the CC exams. There is component 1, 2, 3, and 4. So they are quite complex to read. However, component 2 is a zoom-like mode, because the vertical displacement is the vertical gradient, the horizontal displacement is an horizontal gradient. And component 4 is more a rotation-like mode. So this is interesting, because in standard data augmentation, you would have used zoom and rotation. Here, we found that indeed zoom and rotation are relevant. Second, in standard data augmentation, you would have to select an amplitude for the zoom and the rotation. Here, you don't have to select anything. Everything is obtained from the reduced transformation model. And finally, this is not a perfect zoom and perfect rotation. This is a more complex field that is perfectly adapted to our dataset. Okay, so all those fields are the spatial components. About the eigenvalues, we can see the eigenvalues depending on the number of components. In fact, this is the error depending on the number of components. And we selected 6 in order to have a highly reduced transformation model. We talked about the space, we talked about the eigenvalues. What about the beta, the amplitudes? The amplitudes can be modeled by a normal distribution. And on the right part of the slide here, you have all the distribution of the 4 first beta values. And indeed, it follows a normal distribution. So because principal component analysis provides from linear coupling, we could have non-linear couplings that would have required some manifold learning techniques. However, here, with the 583 dots that you can see on each plot, we do not see any non-linear correlations. So finally, the generated fields can be obtained from those 2 equations, x being the normal law, gamma being the space fields shown above, and lambda being the eigenvalue. So we can generate some augmented data from one patient acquisition. So here it's a fixed one patient image, and we can generate new data. Here you can see the pectoral muscle is being larger, sometimes it's smaller, sometimes you can see the inframammary fold, sometimes not, as in real applications. Okay, so we have our augmented data sets. Now we can test it with segmentation. Here the goal is not to segmentate mammography images, but CESM images. CESM stands for Contrast Enhanced Spectral Mammography. This is another technique with contrast agents for the imaging of breasts. But now the dataset is very small, composed of 204 cases. We would like to perform data augmentation on these very small datasets. And what we did, we used the transformation model that we learned from the mammography dataset with priors. So this is a variability transferred to the new small dataset. So everything we learned in the previous slide will be used as data augmentation for another dataset composed of contrast-enhanced spectral mammography data. And finally, we use unit-like architecture to segmentate the lesion. Here are the results. We have 3 different cases. The first one is performed without any data augmentation. This is the red curve. The second one in between is the classical data augmentation performed with rotation, translation, shear, and histogram equalization. And finally, the realistic field. The realistic is better than the 2 other approaches. This is the diagram on the left. Diagram on the right, here you have the efficiency with the dice coefficient with respect to the number of components. Remember that we selected 6 components in order to have a very reduced model. However, if we wanted to select more components, we would have a better dice. So here we see that a larger model may be better to perform the data augmentation. So there is an improvement with both metrics, dice, IOU, on the proposed approach. As an example, 32 images with augmentation is equivalent to 100 images without data augmentation. So there is a huge gain to use data augmentation method. Finally, the entire method is completely automatic. We do not have any hyperparameter to be tuned. Everything is learned from the reference dataset. Almost the last slide. Here is the realistic data augmentation method compared with the standard data augmentation approach. The 2 segmentation results are compared with ground truth. You can see that there is often an improvement, even if some cases are still very complex. So to conclude, data augmentation based on realistic transformation improve the efficiency of the segmentation network, especially when the data set is very small. The augmentation model can be obtained even with very, very small data sets. And this is not the case for augmentation techniques based on generative model, for example. The realistic transformation model does not require any hyperparameter, and it provides augmentation without any bias because it's realistic. And finally, this augmentation technique could be coupled with other augmentation techniques such as GAN or autoencoder. Thank you for your attention, and I would be glad to answer all your questions. Thanks.
Thank you for your presentation. So we have a question. Do you see the question?
So I'm just. I don't see any question related to this presentation.
I see a question, but I don't know where it's.
I can see a question. So the difference between realistic and classic augmentation. So I can answer it. Actually, the classic augmentation, you use transformation such as rotation, such as translation, or also noise addition that are not realistic. So basically, you introduce unrealistic patterns to the image. So the image that you obtain after transformation are not realistic. And therefore, the problem is that you will focus a part of the network discriminative power to learn unrealistic patterns. And the difference with realistic augmentation is that you only apply realistic transformation to the image that really occur from an exam to another. So the image that you obtain after augmentation could really exist in reality, and therefore the network doesn't have to learn unrealistic patterns, and it doesn't have an negative impact on the training. So that's the goal actually of realistic augmentation versus classic augmentation, where you don't really care about the realistic nature of the transformations.
Okay, thank you. So I just one question. So you use four agent space to present the variability. Okay. So can you? I just know, is it surface to present the probability, because like you show, we can just say the shape of the breast, but we cannot say the variability of lesion or tumor. I mean, so it may be limited.
You mean that we use only a few components for creating a displacement field? Yes, actually.
I mean, just shape and globally for the breast, global breast, but we cannot see inside the lesion or tumor.
Yes, exactly. In fact, it's a global model, so we apply the displacement field on a meshing. So this is not really a local. We don't really seek to model the displacement field locally, and in particular around lesions. And we can exactly, as you say, expect that locally the displacement field around, for instance, lesions that have a different texture than the rest of the breast could be different. But what we meant is just to apply at another scale, so at the scale of the whole breast, a displacement field that is realistic. But if you look at locally, as you say, it might be unrealistic around some lesions. And actually, it's a way to pursue the work is to have a finer modelization of a displacement field and intensity correction around lesions.
Okay, thank you very much. I think our session is over, so you can continue the next session.
Okay, thank you.
Yeah, thank you.
Thank you, Professor Su Ren. And now let me introduce our next session chair, Hasma Hejia, who comes from University of Groningen, Netherlands. Okay, let's welcome.
I would like to share my screen, but I can't do it.
Okay, the next speaker is paper ID 14.
Oh, okay. I wanted to share my screen.
Oh, okay.
Yeah, I think I can do it. No, also not. Okay, someone is sharing, so. Okay, so hello everybody. Hello everybody. So we'll start with session 2, which is automated medical analysis, image analysis. My name is Asma Haya, and I'm going to chair this session. So a little bit about me. I'm from Nazareth. If you don't know it, it's a childhood home of Jesus. I studied computer science in Germany, and I'm currently doing my PhD at the University of Groningen in the Netherlands. My research interests are mainly in the field of machine learning, deep learning, and both image and data analysis. In this session, we will have 6 speakers. For each speaker, we will have 10 minutes presentation and 3 minutes question. You can post a question in the Q&A session or in the chat, because I have seen in the previous session people posting their question in the chat, and question will be answered at the end of the presentations. So we will start with the first speaker. So our first speaker today is Professor Ivo Dragunov. He's Associated Professor at the Technical University of Sofia. He will present a generalized algorithm for unsharp masking of medical image. Professor Dragunov, the stage is yours.
Hello, everybody. I hope you can see my presentation on a full screen now.
Yes.
I'll present to your attention today our recent research related to the unsharp masking with a local adaptive contrast enhancement directed towards medical images. My name is Ivo Dragunov, and I'm an associate professor in Technical University of Sofia, Bulgaria. Here is a brief outline of our talk. We start with a brief introduction over the topic, overviewing some of the recent advancements of contrast enhancement of medical images. Then I will present to you the algorithm's description for this implementation that we have now, comparing 3 different ways of unsharp masking. And then the main part of the experimental results will be presented. At the end, we have a brief conclusion over these results. The role of the contrast in medical imaging, as we all know, is extremely important for all kinds of systems that take as input any of the various imaging types. It affects both the accuracy and the overall result in placing the diagnosis as a final outcome of the whole process. The recent studies that we looked at are shown here. We look at the prediction of a contrast enhancement, which incorporates deep learning with a class activation and combining the gradient weight. Also 2 kinds of maps, enclosing the saliency points and backpropagation to form a new map for prediction, which leads to accuracy of over 90%. Another recent approach proposed by Kala and Hamida incorporate the discrete wavelet approach combined with a singular value decomposition and with the addition of a few other techniques such as the adaptive gamma correction. They also achieved a quite high level of the resulting contrast. Clustering-based algorithms are another major group into this field. In reference 6, we investigated how one-dimensional column-wise separation could be done, followed by sorting and clustering of the extracted intensities, followed by a certain labeling procedure, which also leads to very good results. All these three approaches that we've just seen relate to computed tomography images. We are also interested in processing X-ray images and also looked some of the recent methods that lead to satisfactory results, such as the multi-scale contrast enhancement proposed by Herrera and colleagues, the incorporated path-based filtering with parameter-based noise estimation. Morphological operations are also another big group of underlying techniques which could be used for contrast enhancement. Kushel and colleagues use the top hat and the bottom hat operations with an adaptive parameter estimation for structuring element, and they employ the intensity gradients, which turn out to be better than the Clarke algorithm alone. We also looked at the way of combining the Clarke algorithm with high-pass filter, just using a few tunable parameters. Medical personnel achieved to evaluate the resulting images of more than 48% of the test database as more than satisfactory using this technique. What we observed looking at all these approaches is that in most of the cases there are two specific, aiming to process images which relate to a certain kind of a disease or some other kind of direction towards which the medical diagnosis is aimed. We are asking ourselves, is there a way to incorporate very basic techniques for contrast enhancement and then use them into the sharp masking procedure? So what comes to our mind is why not evaluating the performance of the histogram equalization and the image adjustment and the contrast limited adaptive histogram equalization, known as the Clarke algorithm, over both the CT and the X-ray images to apply the unsharp masking. As evaluating parameters, we chose to use the root mean square contrast and the sharpness, and also measure the overall distortion of the resulting images, that is the peak signal to noise ratio and the structural similarity index. Of course, we also made visual inspection of the results at the end. This is the general flowchart of the unsharp masking scheme, very popular into all kinds of imaging, not only the medical one. We use the input image denoted by I, which first is being blurred by a Gaussian kernel, and then a contour mask could be derived by subtracting both these images. Then the actual contrast enhancement phase takes place, leading to the image E. And this is the part where we switch among these three algorithms that were mentioned above. We actually implement this flowchart 3 times in order to see what the final output image with its qualities would be. So we can select in one or the other case one of these 3 algorithms based on the content that we dealing with. This is the flowchart through which we pass in order to find the optimal set of parameters for the histogram equalization. It's only one parameter. It's the number of bins to which the intensity histogram of the input image is being split. Typically, it varies between 1 and 16 as degree of 2, since in the first testing we deal with CT images of 16 bits. So we switch this degree between these values 1 and 16. For the X-ray images, we switch it between 1 and 8, since we are dealing with 8-bit representation. And in each iteration, we measure all the 4 evaluating parameters. Of course, we pay attention mostly to the contrast and the sharpness, but also look for the degradation of the resulting image. And based on these 4 parameters in group, we select the optimal N in this case. For the image adjustment, we have one additional parameter apart from the number of bins of the histogram. It's the clip limit, which typically changes between 0.1 and 0.3, sometimes 0.4, depending on the level of contrast we are trying to achieve. In this study, we've changed it, of course, starting with no clipping at the beginning. CL minimum was 0, then increment to 0.1 4 times. Each time combined with different N, we again evaluate the 4 resulting parameters. And for the Quache algorithm, we have one additional parameter next to the 2 already mentioned. This is the tile size, the window which is being applied to split the input image. We typically work here with tile sizes no more than 64 by 64 pixels. So M, which is the order of the 2, is being switched between 1 and 6. Again, using these 4 evaluating parameters, we try to find this time all 3 input arguments for the Quache algorithm with their optimal values. This is the definition of the contrast and the sharpness, very well known parameters. And below we have the PSNR and the SSM as additional evaluating parameters without their mathematical notations. They are also very well known. Our test database includes 103 computer tomography images and 105 X-ray images taken out from these 2 databases. This is our testing setup, the related hardware and software. Here again, we have all the parameters for which we are looking for the optimal values. And this is the result for the histogram equalization technique applied over the CT images. We find out that the number of bins optimal for this case is 64, so N optimum is 6. We've done that first look at the contrast. It turns out to be extremely high for the very low level of N, which is good, and we should aim to that. But in the same time, looking at the structural similarity with the original image, we see that both the PSNR and the SSIM are quite low. The PSNR is well beyond even the mid-ranges of 25, 26 decibels, even higher for the excellent quality that we typically aim at, 35 decibels. So we tried to go up at least until this saturation area here, where we have the highest possible structure preserving level, both for the SSI and as well. And that's why we selected to use with the optimum of 6 for N in this case. Very analogous was the case when we applied the image adjustment algorithm. Again, N optimum was selected to the 6. And the clip limit, after varying in quite an extensive range, was found out to be 0.01, just at the beginning of the histogram. So we cut out as least as possible number of beams, number of values of the original intensities. For the Klache algorithm, we find this three-dimensional representations of all 4 evaluating parameters, looking primarily on the tile size, the influence of the tile size as parameter, and the clip limit. And again, the highest possible contrast is achieved for as high as possible clip limit, going up to around 0.4, from where further we have such an increase in the contrast that most of the content is practically not visible in the image. It's good to have such high values, but in the same time, again, looking at the structural preserving qualities, you see that PSNR falls down around 20 decibels in this case. And in order to have enough details in the image, we chose to select here with the least possible size of the tile, which is 2 by 2. That's why we derive images with quality around or over 40 decibels, and the structural similarity then comes close to 0.9. The other detailed values of all average measured parameters for both cases, CT and X-ray images. As we can see, as a general comparison, the Klache is just one idea lower in numerical terms than the histogram equalization, while the image adjustment algorithm is quite lower. It's 1 order of magnitude lower related to that parameter. And similar is the case when we put all these 3 contrast enhancement algorithms into the sharp masking scheme. This table here shows the final qualities of the images undergoing all the steps of the sharp masking. And again, we see that in terms of the contrast, the Klache algorithm is relatively close to what the histogram equalization does, but the image adjustment algorithm again is in the order of a magnitude lower about this parameter. Although we could see the standard deviation for the Gaussian kernel that we used when blurring out each of the images into the tests. These were derived also experimentally using the general sharp masking flowchart and looking for the change of primarily the contrast itself, which is the values that we see here, the top possible at these constraints, and that's why we consider these sigmas to be optimal for these tests. Here we can see the visual comparison just for one image of both types, the CT and the X-ray image from both databases. These are the originals, and here we have the resulting images from the histogram equalization. These ones here are from the image adjustment, and this one here are from the Klache algorithm. But all these that we see here are after the complete sharp masking procedure. taking place. The general conclusion, we could say that this simple optimization procedure that we propose, we think is quite practical, could be embedded into databases where the images share similar statistic parameters, and once derived as optimal values over a small part of such a database, it could be later applied over large volumes of data. The Quache yields more detail and contrast-enhanced images. The histogram equalization and the image adjustment follow in terms of evaluating parameters next to it, quite close for the histogram equalization technique. The implementation of the latter two of the testing environment demand more computational time. They are a bit slower. And all three contrast enhancing algorithms, we think that basically applicable within the sharp masking procedure. So depending on the application, such kind of a testing could reveal the most proper one. Thanks for your attention. I would be delighted to answer any question that somebody may have.
Thank you again, Professor Drachenov. I see that there is one question.
Yes. About the computational time, we have a comparison. I'm just looking at the question for details. As to the general unsharpening procedure, we find out that execution times for both the Quache and the image adjustment algorithm are quite similar. Over the machine that we used, both of these algorithms execute in around 7.6 milliseconds per image on average. And for the histogram equalization technique, it takes a bit longer. It's around 8.7 milliseconds. As to the memory consumption, we didn't make any measurements, but this is a very good idea for our future work that we could take under mind.
Thank you so much. Then I think we can continue with the next speaker.
I'm sorry, I just see that there is another question in the QA section.
Oh.
What is the purpose of the contour mask? The contour mask is used in order to emphasize the contours of the most persistent objects into the image. These are typically bigger objects, part of organs, the full contour of the body, the chest, if this is the part that the picture is being taken of. Taking out a contour image and combining it in the end with the other two, the contrast enhanced one and the original, leads to a better edge representation. So the overall detail of the image is being preserved this way.
Thank you so much. Then I will move to the next speaker.
Thank you.
So the next speaker would be me. So welcome everybody. I hope I will not cross the time. I already introduced myself, but I will do it here briefly. So my name is Asma Haya. I am a PhD student at the University of Groningen, and my project is part of PERICO, which is a Marie Curie funded project. This work is supervised by Professor Lambert Schoolmaker. I would like to provide you with an overview of my paper, which mainly focuses on the development of fully automated end-to-end process for segmenting, detecting, and classifying of microscopy images of yeast cells. So let's start by defining the problem. Modern microscopy allows the production of big amount of cell sample images in a short time. The large data help biologists in studying complex aspects. The challenge, however, is to process the data, extract information, and to identify clinical relevant diseases in short period. Manual processing might lead to errors and fatigues. Hence, integrating techniques from the deep learning fields seems to be a promising solution for this problem. The main contribution of this paper is not only to build a fully automated end-to-end process, but also to evaluate a state-of-the-art algorithm for the detection and classification of tiny objects in this field. We evaluated the chosen model on publicly available fluorescence microscopy data of yeast cells. Each image consists of a bright field channel, which is a grayscale image. The second channel is the fluorescence protein channel, which is a protein that exhibits specific color fluorescence when exposed to light. The green color is used here, and this channel is called a GFP. The last channel is the merged channel, which is a combination of the bright field and the fluorescence protein channel, the GFP. The library we used contained different proteins compartment called cell organelle. The image on the right side shows an abstract of cell structure, including the different compartments. The more images we have, the more accurate the model we can obtain. This is why we choose images for the organelle that have more than 300 unique images. ER, mitochondria, nucleus, and cytosol are used to evaluate the model. So just a brief explanation of some of the deep learning applications used in this project. So we have the bright field image I showed you before, and we want to do something called object segmentation. Object segmentation means that we want to group pixels together that belongs to the same object. So we can say this is here an object or a cell in this case, and here is another object. In the object detection, we want to detect where are these objects. So what we do, we surround these objects with the bounding boxes. So we say here is a cell and here is another cell. Object classifications means that we want to classify this object or to categorize them. So we say these two objects are, for example, a cytosol. These two objects are mitochondria. For the object segmentation, we used mask-RCNN algorithm, and for the object detection and classification, we use YOLO4 algorithm. As this paper focuses only on the application of these models, I will not go into details to explain each of these algorithms, but I will briefly present the YOLO4 model. In the traditional deep learning approach, each application, such as the detection and classification, is considered as one individual stage. Most recently, in 2016, a new algorithm was developed to detect and classify objects by going through the entire image only one, namely in one stage. The algorithm is called YOLO, which stands for You Only Look Once. Its approach makes YOLO a powerful and a fast algorithm. Therefore, we decided to employ the fourth version of YOLO published in 2020 and assist its performance on the fluorescence microscopy data. For the evaluation of the YOLO model, we defined 6 experiments and we applied a 5-fold cross-validation for each experiment. In the 5-fold cross-validation, the data is divided into train, validate, and test sets in such a way that in each time, 1 fold is used to test the model and the remaining folds are used to train and validate the model. The presented table demonstrates the defined experiments. The first 3 experiments uses the original image sizes, while the last 3 experiments, the original sizes is divided into 4 quadrants, as shown in the image in the upper right image. We defined a 1-class and multi-class classification problem. In short, the classification of cell images is based on the fluorescence coloring of 1, 2, 4 cells compartment. The number of validation, the number of training, validation, and test images are shown in the last 3 columns. The original images will be downscaled to have the same image sizes as the quadrant. But why rescaling the image? because original image sizes are too big to be handled by the current software and hardware. Additionally, YOLO4 is assumed to handle a tiny object, what we have right now. So we wanted to evaluate its results on the downscaled image with very tiny cells, and also on each of the quadrant of the images, which are in the native resolution. Each of the quadrants, Q1 until Q4, and the downscaled image will be used as an input for the model. In the deep learning field, any kind of task is executed in two phases, the training phase and the testing phase. So in the training phase, we first merge the bright field channel with the GFP channel, so we get the merge channel. In parallel, we segment the bright field channel using the mask per CNN. After this, we create necessary YOLO file based on the segmented and the merged channel. Having all these files, we can finally train the model. To test the model, we first need again to combine the bright field and the GFP channel. I told you from the test images I mentioned before. To emphasize, the model didn't see these images before. This is very important. The last step is to evaluate the model based on the test images. This is done by various analysis steps, including plotting and providing some metrics to measure the model's performance. Here, the evaluation of YOLO model during the training phase is presented. The experiment based on image sizes are shown in the rows, while the columns represent the results the result of the defined classification problem. Although there are more images to train for the quadrant of the images, the total time needed to train the model is less. This is because less cells are detected in the original image than in the downscaled image. In comparison to full-size images, the detection's performance on quadrant of the images is better. This is represented by the mean average percentage measurement. Average loss computed for quadrant of the images is around 3.5, which is way lower than for full-size images. This implies that the classification of quadrant of the images is better than the complete images. Both of these observations suggest that YOLO4 is able to detect and classify small objects best in a native resolution, as opposite to the complete but subsampled image. The following table reports the precision, recall, F1 score, and accuracy on 4 classes on full-size image on the left and quadrant of the images on the right. Obviously, the outcome of all of these measurements shows that the classification of individual cells on full-size images is 1% better than the quadrant of the images. The reasons for this is because less cells are detected on the original image compared to the quadrant of the images. Here we can see 2 figures. Here is the original image size, and here are the quadrant. And as I mentioned before, for some images, here the algorithm misdetects 2 cells, and here it misdetects 1 cell. So the difference between the coloring, I will explain here. This figure shows the detection and classification of randomly selected cell images based on their fluorescence coloring. Green boxes shows the anucleus detection, blue for cytosol, white for ER, and red for mitochondria. Clearly, YOLO4 demonstrates good detection results on these images. It's also capable of detecting part of cells found on the border of these images. To conclude, we built an end-to-end process that can perform segmentation, detection, and classification tasks for fluorescence microscopy images of yeast cells. We also evaluated a state-of-the-art algorithm, YOLO4, on publicly available data. We showed that by using the trick of dividing the original image into 4 quadrants, the training time decreases and the accuracy increases. For the future, we are planning to make this eScience website available for all interested users. Thank you for your attention. If you have a question, please don't hesitate to ask. I'll stop sharing to see the questions. Okay, I see that there's Yeah, there is one question in chat. Why do you use mask RCNN only in the bright field channel? So I'll share my screen again to answer this question. So I think you mean here. So we use mask RCN on the bright field channel because there's two reasons. Let's say there's biology reason and computer science reason. So for the biology reasons, microscopes, there's difference between the microscopes, and but the only thing we always find is the bright field channel and not the fluorescence channel. So fluorescence channel is not always there. So we use it because that's, let's say, the base image we have. And from the computer science point of view is that the segmentation, as I mentioned here, the idea of the segmentation is to group these pixels together. And in order to do that, we need to know where is the border of these images. So we can do that so easy when we look at the bright field channel. Thank you for the question. Oops. I see there's other question. Did you do a comparison of the results using the previous version of YOLO? I did a search on it before, and they do not produce good results. Exactly. So yes, we used also, like now we are using the YOLO 4 model, but yes, we used the YOLO 3 model. And they assumed that this model also worked for tiny images, the cells I showed you. But the problem is that they didn't work, and we had a lot of out of memory problem. So when we used the YOLO 4 and also employ that the trick of dividing the image into 4 quadrants, we got it better result. Thank you for questions. So I don't see other questions. Then we can move to the next speaker. So the third speaker is Mikhail Koncharov. He's pursuing his master's degree at Skoltech in Moscow in Russia. His research interests are the application of medical image analysis of algorithm to real clinical practice. Mr. Koncharov will discuss today the quantification of epicardial adipose tissue in low-dose computed tomography images. Please start.
Thank you for presentation of myself. Let me share my screen. 1 second. So not. I hope yes.
Oh, I think maybe there is a connection problem.
Excuse me. Do you hear me? Do you see me?
Yes, we can hear you.
Excuse me. Yes, it's something with connection, but I hope I fix it now. So do you see my screen?
Yes.
Okay. Again, sorry. My name is Mikhail Goncharov. I'm from Russia, but I'm not a Russian hacker. I'm just a Russian deep learning developer, and I'm very glad to present here our work, which is quantification of epicardial adipose tissue in low density images. You can see epicardial adipose tissue in this picture. I will shorter call it epicardial fat. And the first question is, why do we need to quantify it? And the answer is that epicardial fat volume is an early marker of ischemic heart disease, which is the top cause of death globally. But unfortunately, clinicians do not use this marker primarily because it is estimated in CT, and manual estimation is very time consuming. So now assume that we have an algorithm for epicardial fat quantification, then we need some data on which to apply it. So therefore, I'd like to draw your attention to one very interesting source of data on which you can apply your medical image analysis algorithms, which is CT screening data. CT screening is a curing of CT images with the purpose of detecting some target pathology, for example, lung cancer, in a relatively large population. Therefore, the specifics of this data is that these are most often ultra-low dose CT images because it is bad to irradiate a large number of patients with a full dose. And you can see an example of ultra-low low-dose CT image in the right picture. So you can see that it is of relatively bad quality. So summing up, let's develop and apply an algorithm for epicardial fat quantification in low-dose CT images from screening programs to early diagnose the patients who can potentially have ischemic heart disease. So now let me define what is epicardial fat more properly. In the left picture, you see the pericardium line, and in 3 dimensions, you can imagine the pericardium as a bag which contains the heart. And now epicardial fat is a fat deposit located within pericardium, as you can see in the right picture. And now we see that epicardial fat volume estimation. There are 2 questions. First is how to localize pericardium interior region in such a low quality image. And the second question is how to obtain a fat mask within pericardium from such noisy Hounsfield units. Previously, it was proposed, the 2-step method was proposed for epicardial fat volume estimation in full dose CT images. At the first step, the pericardium interior region is segmented using a convolutional neural network, and at the second step, CT image is filtered via a median filter, and then fat mask is obtained by thresholding the Hounsfield units. And this method showed excellent correlation of 97% between ground truth and predicted volumes in full dose CT images. So we treat this method as a gold standard for full dose CT images, and our experiments are aimed to adapt this approach to low dose CT images. For this purpose, we first collected a data set which contains about 400 low dose CT images and 76 full dose CT images. Then we asked 10 radiologists to annotate pericardiums in these images, and then we trained a UNet model for segmentation of pericardium interior region, and we assess its quality in cross-validation, in stratified cross-validation on this United data set. And here we report the DICE scores separately for low-dose CT images and full dose CT images. And as you see, surprisingly, the quality of pericardial material region segmentation in low dose CT images is comparably similar to the quality in full dose CT images, and moreover, it's comparable to inter-rater consistency. So now we have a model for segmentation of pericardial material region. The last step, but not least, is to obtain a fat mask from the inside the pericardium. So here you see three examples of three approaches of how to do it, and to the standard Hounsfield range within the pericardium region performs really bad. In the middle, you see that the median thresholding, which works well for full dose CT images, also works imperfectly for low dose CT images. And interestingly, in the most right picture, you see that a Gaussian filter applied to the input CT image followed by Hounsfield unit thresholding results in relatively better mask. So to verify this observation, we collected a data set which contains 57 patients. Each patient has both full dose and low dose CT image, and as the period of time between occurring these both images was not very large, we assume that volumes, epicardial fat volumes in full dose and low dose CT images coincide. So we did not annotate pericardiums in these images, and we used the trained network to predict pericardial material regions in both low dose and full dose CT images. And then we did the following. We calculated the ground truth epicardial fat volume for each patient in full dose CT image using the median thresholding as a gold standard for full dose CT images. And then we varied the thresholding parameters in low dose CT images in order to minimize the mean absolute error between the resulting volumes in low dose CT images and the calculated ground truth volumes in full dose CT images. So in these plots, you see the results of this calibration. You see that blue color means the low mean absolute error between the volumes calculated in low dose CT images and volumes calculated in full dose CT images. So you see that the Gaussian thresholding with the standard Hounsfield range performs better than other approaches. So we ended with this approach, and now we have a pipeline for predicting the epicardial fat volume in low dose image. We first apply our neural network, our UNet, and then apply Gaussian thresholding. So to finally assess the quality of this pipeline, we collected one more data set, which contains 25 patients with both full dose and low dose CT images. We asked radiologists to annotate pericardiums in full dose CTs, and then we calculated the ground truth volumes in these full dose CT images based on these pericardium annotations and using the median thresholding as a gold standard in full dose CT images. And then we apply our pipeline in low dose CT images to predict the epicardial fat volumes, and then we report the mean absolute errors between the predicted and ground truth volumes, as well as correlation coefficient, between them and bias in milliliters. Okay, here we can compare the mean absolute error of our method with iterator mean absolute error. We see that the method's mean absolute error is higher. However, it's acceptable for applications. And also, it's worth noting that correlation coefficient of 96% is similar to the coefficient that was reported in previous works by other authors in full dosage images. Okay, so to conclude, I'd like to mention that first we see that pericardium anterior region segmentation quality in low dose CT images is surprisingly comparable to quality in full dose CTs. Second, the interesting insight is that Gaussian filter is more appropriate post-processing step than for low dose CT images than popular median filter. And finally, the final quality of our method in low dose CT images is higher than iterator variability of assessing epicardial fat volume, but it's still acceptable for applications because acceptable quality of the method is about 15 milliliters. So that's it. Thank you very much for attention. Please contact us if you have any questions, and I will be glad to answer all your questions right now. So thank you.
Thank you. I see that there is one question.
Yes, I
maybe I can read it if you want. So which dataset are used here? Would it also work for early detection of the asymptomatic patients?
Okay, it's a good question. We used a private data actually from the mentioned lung cancer existing CT screening program in Moscow. So this is private data, and these patients actually do not have symptoms of ischemic heart disease, but actually we found out a lot of patients with large epicardial fat volume, so they are at risk of having ischemic heart disease in the near future. I hope I answered your question.
Yeah, I hope so. It's not my question.
No,
okay,
your question, yes.
No, I just read it. But I think we can move to the next speaker because of the time. So,
yes, of course.
So the next speaker is Professor Marcelo Mendoza. Thank you. He's an associate professor at the Department of Informatics, Università Tecnica Federico Santa Maria in Chile. Professor Mendoza and his team designed a content-based image retrieval system for medical imaging using the principle of query by example. More about this in his talk. You can share the screen. Thank you.
So hello everyone, can you hear me?
Yes.
Okay. So I will start the presentation. Thank you for the presentation. For this new content-based image retrieval system, we will test this approach or this proposal in the problem of SARS-CoV-2, computer-aided diagnosis. So the idea is to propose a new content-based medical image search system. So, our approach is based on information retrieval. So the main idea is to provide an image, for instance, a CT of a chest of a patient, and to retrieve from the system a number of close or similar images with some diagnosis. And this tool can help practitioners and researchers to define or to look for similar images to an original image that doesn't have a diagnosis. So this search system can be helpful for the search of similar systems and trying to identify some patterns in the content of the image. So the idea of our system is to use deep learning architectures to generate representation of the images indexed by a nearest neighbor query engine. And we use deep learning for two purposes. First, it allows us to build representation of the images in a low-dimensional space. And the second purpose is to incorporate latent information that deep learning uses to build high-performance classifiers. So what did we do? So we combined two deep learning architectures, the CNET, the Context Encoded Network, that is an architecture for the segmentation of the images. And the second idea is to combine and to use these embeddings as an input for a second architecture, that is the exception architecture, which builds a new representation of the images to solve a diagnosis task. So both embeddings, the CNET and the exception embeddings, are concatenated, are indexed in a nearest neighbors query engine to perform the queries. So when the user provides an example image, the system uses the CNET and exception models to obtain the example image encoding, projecting it into the same space in which the repository images were encoded, facilitating the searches in the repository. So the main contributions of this paper are the combination of two deep learning architectures supporting medical imaging nearest neighbor searches, providing valuable information to computer-aided diagnosis systems, and we systematically validate our system precision, comparing our system performance favorably with its most direct competitors, and we use open datasets to favor reproducible research. So this is the proposed architecture, and the idea is that the CNET architecture that extends the UNET architecture incorporates two processing modules, the dense aqueous convolution and the residual multi-kernel pooler, so the DAC and the RMP modules. Both modules were designed to capture high-level characteristics and also preserve more spatial information throughout the encoded-decoded architecture in the CNET. So then we use the encoding of the image generated by the RMP block, here in purple color, to build its representation, the representation of the image. It is the highest level encoding generated by the network before entering the decoder. So the CNET can be trained for medical image segmentation task by showing original segmented image pairs at the network inputs and outputs using masks of segmentation provided by experts. And this requires having a set of medical images together with their segmentation mask generated by specialists. The second architecture, that is the exception architecture, is based on the inception architecture that is used in image classification. So the idea of the inception architecture is to use models based on convolutional operators which manage to capture short-range dependencies in the input image. And these characteristics allow learning a new representation of the input image, identifying patterns between the original image that are useful for a better representation. So then we combine both architectures, trained in different tasks, the first one on segmentation and the second one on classification, to address the medical image search problem. So the main idea is to use the encoding of the CNET as an input for the second architecture, that is the classifier, based on the exception architecture. And then we concatenate, we use both embeddings, the embedding of the CNET, the encoding of the image encoding of the CNET, and the encoder of the exception that was used to solve the classification task that is shown here in green. So both encodings are concatenated to, and then they are fed into the query engine to perform nearest neighbors queries. So the training and indexing data flows is that we use some images. In this paper, we use only images from SARS-CoV-2 COVID images, and also with healthy patients. We combine both classes, and we use CT images from patients to train the CNET and the exception, and then these vectors are fed into the indexer. And then we use an index that is based on the multiple random projection trees algorithm to perform efficiently the nearest neighbors queries. This is the offline module of the system. And then the online module, so we have an expert that provides a new image, a CT image, a chest CT image to the system, and then the system fed this image into the CNET and into the exception architectures, and then we retrieve the vector representation, so the concatenation of the CNET and the exception encodings. And this representation of the image is in the same space of the original images used to train the architecture, the combination of both architectures. And then this vector is used at the representation of the query of the technician to address the nearest neighbors, the nearest neighbor query. And then we provide the results using a graph deployment. So we show to the final user, to the end user, the proximity graph between the results. In this version of the system, we are not using metadata. Just we use metadata to solve the classification task. So our experiments include 3 datasets: one to train the CNET, and the second one to train the exception network, and the third one to make the validation process. So this is very important because we are not using the same images of the first 2 datasets to perform the validation. So we are directly evaluating the transfer of this model to a new dataset with different, with a data acquisition performed in a different laboratory. So we are evaluating this in real world, in a real world context, where we acquire images that are different from the images used to train the original model. And the results show that our proposal achieves the best results in terms of precision for different number of results used in the nearest neighbors query engine, outperforming exception and unit architectures in the COVID class. So it is very important. This result is very important because we can provide better results than the state-of-the-art architectures for image searching using the combination of both architectures. And then if we disaggregate this with health patients and patients that acquire the SARS-CoV-2, we can observe that the performance is due to a good accuracy that is achieved in the target class, so in the COVID-19 class. And there is some confusion that is, or the cost of the process is paid at the precision in non-COVID images. And this is a view of our system where we provide a new image, and then the proximity graph of related results are shown to the end user. And when you click on some of the related results, you can observe the metadata associated to these recommendations. So to conclude, This paper has shown that combining both architectures used for segmentation and classification tasks is useful in image search. And our experiments conducted on images of patients with COVID-19 show that our method outperforms its most direct competitors in terms of precision without overfitting to either class of interest. Thank you.
Thank you so much, Professor Mendoza. If you have any question, you can still ask. If not, I have some questions. Okay, then I will just ask like small questions. Is that system is available for all users?
If it is online, if the system is online, well, not really, because we are providing and we are conducting some tests on the data visualization tool on the front end on the system. What we showed in this presentation is the backend model of the system. So we are working on how to deploy the graph, because in some queries we have many results, and it is very difficult to visualize in a screen. So we are working in this part to provide the end user tool, and the idea is to do this with an open code tool to guarantee the use of this tool for many users.
Okay, then I'll ask just another small question. So you showed your model. So I'm just wondering if your model will be updated after every new image.
So we train using batch learning on the CNET architecture. And then these images are fed into the exception architecture to address the classification task. Both architectures are decoupled during training. So we train the CNET first, and then in a second stage, we train the exception. This is during the training stage of the system. And when you provide a new image during the testing for looking for a new image, we fed this image into the CNET. We retrieve its encoding, and this encoding is used as the input for the exception architecture. This is the complete data flow of the image in the system.
Okay, thank you so much. Then maybe we can go to the next speaker. And next speaker is John Twang. He is a PhD student in computer science at the Indiana University, Purdue University, Indianapolis. His research interests focus on machine learning, graph mining, and medical imaging. He and his colleagues proposed an innovative model architecture called bidirectional adversarial networks to synthesize diversified macroscopy images from multi-source domains with distinct geometric features. You can share your screen, Mr. Twang.
Yeah, thank you. Can you see my screen right now?
Yes.
Okay. So we get started. Hello, ladies and gentlemen. I'm Jun. Today, I'm going to introduce our paper about the medical image synthesis. In the beginning, I want to introduce the background of a little bit. Multi-source observation, it observes the same objective from different source domain. For example, scientists may scan the cell with different fluorescent material. In these images, we use the image as an example. The left side is the membrane and the right side is nuclear. By using different fluorescent materials, we got different images from the one cell. However, sometimes over-scanning may probably cause the death of the cells. This constraint may prevent scientists from acquiring enough microscopic images. So cross-domain synthesis is a potential solution to augment the multi-source observation. Given a source domain A, cross-domain synthesis aims at generating corresponding image of the same objective in a target domain B. However, many existing methods couldn't handle the issue that two domains come from different sources with quite different spatial features. So we propose a new framework to address these issues. Before I introduce our method, I would like to talk about the background of the baseline. Generative adversarial network, namely GAN, is a popular baseline model for image generation. Basically, it has two components, a discriminator and a generator. A generator is try to generate some image as close as possible to the ground truth image, while the discriminator is responsible for file which is the real and which is the fake images. So cycle consistent loss can help the GANs synthesize cross-domain images without pair training data. However, this technique couldn't handle two objectives with distinct contours. Our model aims to embrace this challenge as well. Next, I will introduce the model architecture. And in our paper, our model has three basic components. The first is called a Pioneer. Pioneer is composed of a generator G and a discriminator D. Is the kind of vanilla GANs. And the successor consists of an encoder E and shares the generator G with the Pioneer. And the coordinator sequentially connect two successors. Here we denote the generated image come from the Pioneer and the reconstructed image come from the successor. In this pictures, the yellow box is the Pioneer and the green box is the successor, and the CA and CB represent the coordinator. And next, we'll talk about the training procedure. Our procedure contains two stages. Now let's come back to the previous slides. And on the warm-up stage, two Pioneer are trained with a given random uniform price Z, and then respectively generate images. They help speed up the progress of generation. After the warm-up stage, both two successors and two coordinators join the training to enforce the geometrical relationship between these synthesized images. The successor encodes the input image into the latent space and then reconstruct the new images from the latent space. In these pictures, we can see both the Pioneer and the successor, they share the same generator. So the difference is the Pioneer, they take the random uniform prior as the input, while the successor, they take the ground truth image as their input because they want to encode the ground truth images. And the coordinator use the pixel-wise method to preserve the geometric relationship between the reconstructed image and the original images. In our model, we use three types of the loss function. The first, the adversarial loss. Adversarial loss is employed to enforce the generated images as similar as possible to the original images. So this is the same as the loss of the GAN. And the second is the identical loss. Identical loss makes the reconstructed images close to both the generated images and the original images. In the formula here, small a represent the original images, and the GAZ, it means the generator, it takes the random uniform prior Z as input and then generates some generated image. So the next is the pair match loss. If enforce the projection inside each successors to ensure these two domains are spatially matched. So next we will talk about experiments. In this experiment, we use a set of C. elegans microscopy images. First, we use ImageJ software to split the images, and then we crop out the embryo to membrane and the nucleus. Here we present some samples in these slides. And the first row is the membrane, and the second row is the nucleus. We also propose an evaluation metric to measure the performance. We call it the geometric matching index, GMI. In this metric, at first we will reconstruct the image by the successor. After that, we will extract its binary mask of this reconstruction. And then we compute the dice coefficient between these two extracted masks. After we compute the dice, we will compare the dice to the given threshold. This threshold is decided by the user. If the dice is smaller than the threshold, we say it is good. The intuition is that the overlapping will be lower if two images are matched. Next, we present some results between our model and the baseline models. The first two lines comes from our models. From the result, we can see that our synthesized image has a clean contours, which is better than the other two. Especially in the bottom row, autoencoder fails to generate some clear nucleus. So this result indicates that our model outperformed the other two baseline model. We also evaluate our result based on our proposed evaluation metric GMI under different thresholds from 0.1 to 0.3. And the result shows that our model still get good performance even under a very strict threshold. So in conclusion, we propose a novel model, BANIS, to synthesize geometrically matched images from multiple source domains that exist entirely separated spatial patterns. And the experiments indicate that BANIS successfully synthesized diversified and geometrically matched microscopic images and outperformed two baseline models. And we sincerely thank NIH for supporting our project. Thank you. That's all. Any questions?
Thank you so much, Mr. Tuan. It was a nice presentation. So I'll just give a few seconds for the people who wants to ask.
Oh, okay. What's the questions?
So there's no question. So then I would ask. I like your the BANIS model. I think it's a good one. I'm just wondering if we can use it also for like other data, like non-medical data.
Another data, and yes, our model does apply to other data, but in our paper we only use the microscopic data set.
Okay, but do you think we can use it for other types of data?
Actually, one advantage of our model is to synthesize the image from different domains, while these two domains has distinct contours. So in our data set, obviously the membrane and the nucleus has very different distinct shapes and the contour. So it is challenging and different from the cycle gang. It can, for example, it can shift the style, but it cannot change its the shape. So I think other data set similar to this, I think our model can work on that.
Okay, thank you so much.
Yeah, thanks. I will stop sharing my screen if no other questions.
Yeah, I think so somebody's asking a question.
Oh, okay.
but I think I asked this plus minus same question, but the question is in practice if your BANIS model will also work for proteomic application, genomic, or
I didn't try this. Thank you for interesting. Yeah.
The question is like when the data is tabular and not images. So would it also work for that?
It's not image. Currently, our model is focused on synthesize the image, but if for other data set, we can still explore this potential.
Okay, hope that answered the question for, it's not my question, it's a participant question. Okay, thank you so much.
Yeah, thank you.
Thank you again. And then the last speaker for today is Mr. Kavin Lianaj. I hope I say it correctly. He's a graduate research assistant at the Montana State University in the USA. And his work, he utilized image sparse coding to help classifying COVID-19 CT lung images. The stage is yours.
Hi everyone. Can you guys see the screen?
No. No, yes, I can see, yes.
Okay, so hi everyone, my name is Kavin Lianage. Today I'm going to present our project COVID-19 chest CT scan image classification using LCK-CD and frozen sparse coding. This is a project done by myself, my colleague Sareshte, and our supervisor, Dr. Whitaker at Montana State University. As you all know, COVID-19 has a huge effect on our life last year. So one of the early problems that we had was detection of the problem. Even for now, for the detection of the COVID-19, we have only a couple of options like nucleic acid testing or antigen testing. But now turnout time of these tests have increased due to high demand and lack of on-site testing. So the researchers have pointed out that CT scan images has the potential to be used as a second-line diagnostic tool when the patient is symptomatic, suspected, or high-risk case, especially when PCR testing is unavailable, delayed, or negative. So, but it is not authorized yet due to the lack of specificity, risk of spreading, and resource management. A lot of deep automated systems have been designed for CT image classification, but almost all of them are deep neural networks. Most of them consist of convolutional neural networks, which are known to produce high accurate classifiers. But the problem is they require large computational resources for training and testing. Mainly, their learned features in the inner layers are highly nonlinear. So they are hard to relate to the original input space. So to overcome this, we are proposing a basic touch-based framework using sparse coding. So there are two main advantages of using sparse coding. First is the intuition. So we are learning a dictionary. The learned dictionary elements will be in the same space as the input features. So it will be more intuitive what is happening in the structure. The second is the simplicity. When we transform the data into the sparse domain, it allows us to use a lower order classifier. So it allows us, so it greatly reduces the computational cost. By doing so, we were able to achieve an accuracy of 89%. So as a note, this should not be used for diagnostic because this is not yet clinically verified. So the data set, one of the main problems that we had in the early stages was the lack of publicly available data sets. So this CCCCII data set, which stands for China Consortium of Chest CT Images Investigation Data Set, is a large collection of high quality images from original sources. But later, some other researchers have published the clean version of that dataset by doing some pre-processing, image resizing, and segmentation to isolate the lung area. So we are using that clean subset of the original dataset. They have used UNet to do the segmentation. So each segmented slice is 512 by 512 pixels, and each patient has 64 slices. Additionally, in the original dataset, there are 750 CT images that are segmented manually by experts. They are segmented into background, lung field, ground glass opacities, and consolidation, which are known to have been associated with the coronavirus. So when we look at the related work, the authors of the clean dataset have done a benchmarking with some non-convolutional deep networks. So as you can see, the highest accuracy they have achieved was 87.83 with the F1 score of 87.25. In our method, we were able to achieve a high accuracy of 89%, but our F1 score is a little bit lower than the benchmark set. So when you look at the first representation, it's an emerging technology that is used in the image processing tools, image processing tasks like denoising, restoration, and classification. The basic idea is to represent an input signal as a linear combination of dictionary elements. So while doing so, we are trying to promote sparsity by using a limited number of dictionary elements. So by doing so, this encourages us to use a lower order classifier. So sparse representation can be achieved in two steps. The first is sparse coding, that is calculating the sparse coefficient when a given dictionary D is given. The second step is updating the dictionary when the sparse coefficient is given. So this is achieved through the K3D algorithm, which stands for K-means singular value decomposition. It is an efficient algorithm used for image reconstruction. But since we are using this for classification, we are using variants of the K3D algorithm. First, label consistent K3D, which uses label information also to learn a more discriminative dictionary in a supervised manner. So we are trying to discriminate the dictionary according to the class labels. The second method is frozen K3D. It takes into account the class imbalances in the data set and learn a dictionary in a hierarchical structure. So here we are trying to use that method to learn the abnormalities in the CT images. So the largest class is the normal lung field class, and we have the rare occurrences of abnormalities like ground glass opacities and consolidations. So the proposed dictionary composition is like this. So we are trying to roughly divide the dictionary according to the abnormalities and the class structures. The total dictionary size is chosen as 2000 with a sparsity of 20. Each section is divided according to this. So this is the overall framework of our method. So we have this segmented image from the clean data set. So we are getting image patches from size 24 pixel by 24 with 30% overlap. The size is chosen so sufficient spatial features are captured within the patch. So we are discarding the empty patches, and about 20% of them are used for the LC-K3D dictionary learning. And meanwhile, we are using the expertly segmented images for learning the frozen dictionary. By augmenting these two dictionaries, we are using that combined dictionary to learn the sparse coefficient. After learning the sparse coefficient, we are calculating the statistic of this sparse coefficient, namely mean, variance, and the count of dictionary item utilization. These statistics are the features that we are using for the final classifier training. For this, we are using a SVM classifier. So when we look at the results, these are the learned dictionary elements. As you can clearly see, the dictionary is discriminated according to each class label and each abnormality. Here we can see distinguishable features in each dictionary portion. So this is highly beneficial to study what is going on in the internal structure. So when we look at the results in the 2-class case, the coronavirus is categorized as one positive class, and the common pneumonia and the other normal class is categorized as other. We were able to achieve 89% accuracy. When you do the 3-class classification, we can clearly see a large confusion between the novel coronavirus and the common pneumonia. So this is due to lack of specificity, because the abnormalities are shared, sometimes overlap with other symptoms, other diseases like common pneumonia also. So in conclusion, we were able to achieve similar result as the other state-of-the-art methods, but our method produced some other benefits, namely, especially the learned sparse dictionary elements are in the feature space. So we have a more intuitive relationship. The second is the simplicity. So we were able to use a low order SVM classifier to get the same results as the deep neural network. So in the future, we are trying to use this for other data sets to check the robustness and the effectiveness also. And also we are trying to develop a 3D sparse representation model so we can learn 3D spatial features also. A parallel computational pipeline can be developed, so it will improve the testing time. And finally, we have to study the effect of hyperparameters, so we can better understand how to model the dictionary elements. So in summary, our method is intuitive, simple, and gives like relatively high accuracy. So thank you. If you have any questions, I'll be happy to answer.
Thank you so much for the nice presentation. I will wait with maybe I will wait a few seconds to have questions from the audience. Okay, then I will ask. My question is, you mentioned that your algorithm considered the class imbalance. So can you maybe tell us more about it?
Yes, so if you so that we used to model the structure of the lung images. So you can use the majority of the lung is healthy. So we have only like a couple of rare occurrences of abnormalities. So in order to model that, so we are taking a large amount of area for the normal lung field. So we are first learning the lung field, then adding the abnormalities on top of that.
Okay.
So in the final learn dictionary, we can clearly see these are the features that are associated with the lung field, and these are the ones with the abnormalities. Yeah, hope I answered.
Yeah. Thank you so much. I think we need to end the session. So thank you for all presenters. It was a nice session, and I will handle it to Ms. Dora Zwank.
Okay, thank you. Thank you, Esma, and thank you for your excellent speeches. And now the first day is finished. Thanks to the joint efforts and contribution from session chairs and all participants. And tomorrow we will begin at 7 o'clock in the morning. Okay, and see you tomorrow. See you tomorrow. Bye.
Thank you so much. Have a nice day.
See you tomorrow.
Thank you. Have a nice day.
Have a nice day. See you tomorrow.